um, especially in the in the context of all the change that's happening around us. Gretchen and I were just talking about that, how we're able to pull this off, and with all the changes that are happening. More importantly, is the attendance. I hear that we have over 100 people here with us in Boulder, here in Center Green. We'll get you some Boulder weather pretty soon. Actually, precipitation is good here in Boulder. And we have also something like 500 people online. And this is really great. It's a testament to how important WRF and MPAS are to the community and enabling the work that you do. And so here at NCAR, we are really proud to continue to bring the community together around these capabilities, WRF and MPAS. And the growing community collaboration and the co-development that happens when the community comes together is what really make these models and what makes this community in successful. And I just want to really express my appreciation for that. So talking about change that's happening around us, I know that we have people here that joining us today from academia, from the federal government, and also from the private sector. And I just want to acknowledge that for many of us, NCAR included, we're facing difficult times, right? We are facing difficult times, and I want to acknowledge that and be upfront about that. We're facing cuts to of federal funding to science, and on top of that are looming, and that's on top of cuts that have already taken place, and that's on top of. As part of those cuts that have taken place, the reduction in workforce, that's been, very impactful. The reduction in expertise that we have already lost for many of us, and so that's big, and so I want to acknowledge that. It makes me all the more, again, with this team, appreciative of everyone taking time to gather this week, to share knowledge, to celebrate scientific achievement that we know advance our science, that benefit or stand to benefit public safety, national, global resilience. So again, this is just an appreciation of all that. I want you to know that we are committed to doing everything we can at NCAR to continue to support our community facilities. It's what we do, provide community facilities to enable the academic community, and we're committed to that. And that includes our community models. I think of our community models as an important component of our community facilities. It's not just the airplanes, not just the shiny objects, right? And so, because we know that these facilities, these models, and your ability to access them, openly access them, I think that's the brilliance of NCAR, open access, democratizing science, really leads to scientific discovery that have far-reaching benefits for our society, the public good. And so that's why we're committed to that. We know that these models further our ability to understand and advance prediction of, for example, extreme weather events, and to do so on timescales and in ways that are important to decision makers. We know that the fundamental research that advances hazardous weather prediction for better decision making, that's a top priority for NCAR. We have a new strategic plan that's not out yet. It's sort of at NSF. where it's been for a number of months. It's not necessarily their highest priority, as you can imagine. But when it comes out, you'll see that, these are the kinds of things that are continue to be a top priority for us at NCAR. And it's a top priority for people across the globe and across the country who are being impacted by increasingly frequent extreme weather events. And so we're really proud that MPAS' ability in particular to bridge the global to regional divide and its flexibility to make efficient use of computing resources, that's transformational and making it an important part of our effort towards Earth system predictability across scale, which is an initiative that we've really been advancing for a number of years here. I want to talk a little bit about AI at an MPAS WRF workshop, which, we're making an effort here at NCAR and to advance. And we're doing it in this regard. We want to be strategic. AI is happening all over NCAR and all over your communities. But we want to scale up and we want to be more strategic how we apply AI to our research. As you are aware, the last couple of years, new AI models have proliferated around and have proven to be, in many cases, perform as well as or better than our physics based models, particularly at shorter timescales and larger features. And they've done this, right? They've done this using a tiny fraction of computing resources compared to the traditional dynamical and physical modeling counterparts. We have a responsibility here at NCAR in our mission to really provide leadership in this space and to enable the community in this space. It's our mission is what we're here to do, to help move innovation forward and to take that innovation and transforming it into enabling the university community to advance their research. So that's our responsibility. That's our commitment. And so we have a role to play here. And to achieve that, we've been working for several months now on what we call an AI roadmap, which is really, again, this effort for NCAR to provide leadership and capabilities in what we're calling community AI. And conceptually, it's not really different than community modeling, which we've done for decades, and we're really good at doing. It's the niche area that we're good at, community modeling, compared to anywhere else. And so we're taking the same kind of approach here. And our plan is to build an integrated framework of data, infrastructure, computing resources, software tools, modeling systems, including MPAS, and training as well, workforce training, training here, training across the community, with the goal of enabling researchers to be smarter, to work more efficiently, to work smarter across domains, right? In how we harness this technology, this tool, to advance research. We want to ensure reproducibility, scalability, and again, broad accessibility. I want to underscore accessibility. Accessibility is what we do. In how we apply again this tool for the weather and climate community. And in NCAR, no, we don't think that AI means the death of physical models. On the contrary, we think that physical models have an important role to play as part of this, ecosystem of capabilities and tools. And so that's why. So why am I talking about AI at a WRF MPAS workshop? It's because, again, this is a roadmap that we're developing, an initiative that we're developing. We're doing it internally here at NCAR, but we want to engage the community. And so we absolutely need your input to be successful here. And so look out for communications that come out for engagement in this endeavor. So I'll wrap up by saying that development and research that will be shared this week is significant. It's important. Again, despite all the stuff that's happening, it's what we control. And when we talk to staff about the challenges that we're facing, what we say is that's what we control. Excellent science. And let's continue to do that. And so we know the work that's going to be happening here will be significant. This workshop really represents a community that's dedicated to further national resilience by partnering across research and operations. And that's important, the partnership that we have across research on operations. So again, thank you for my opportunity to share these remarks with you. Again, thank the organizers, and I really wish you a productive week, and I think we'll get you some better weather.
It's amazing to think back that this is the 26th WRF and now the 8th MPAS workshops. How many years we've been having these users workshops. And for the first 2 decades they were all just in person, and then with COVID we went to all remote, and then we went back to hybrid. But this year has been particularly challenging for us in as Everett mentioned, the problems with budgets from the federal government and government employees being under severe limitations of many cannot use funds for registration fees or for travel. And we feel it's really important for that segment of our user population to be able to participate. So we've stewed around and came up with several different possibilities, and finally we figured out a way to tighten our belts and scrape together some M-Cube funds to support the workshop without any registration fees. So this is the first time we've tried to do something like this, and it's really encouraging to see the significant participation we have with both in-person and remote participation. So we hope that this will be successful for everyone, and the main impact that you will see is that most of our budget goes for food and drink, and so it may be a little more sparse this year. If you could, how do I advance slides here? I see it. Okay. In terms of why we hold these workshops, the overall motivation here is to promote a sense of community among all of the different users of MPAS and WRF and the variety of applications. So this is an opportunity for us to get together and learn about recent model improvements and updates. For those of you who want to share your advances in your research with others, and of course to hear about what others are doing in their modeling work. We want to be able to discuss community interests and priorities related to the model development and support, and strengthen our informal professional relationships among community model users. I think that last one in particular is one of the important reasons why we feel the in-person emphasis on these workshops is particularly important. In terms of the, does this work? If you could advance that slide, there we go. In terms of our agenda for the week, there's a couple of things I want to mention. This organization is going to be similar to what it's been in past years. So we'll have 3 full days of sessions with a coffee break in mid-morning and mid-afternoon, a lunch break over the noon hour. We will have a simple lunch fare, but hopefully it'll keep us going. And also during the lunch break, we'll have a help desk. So those of you who might have questions and want to talk to someone about issues you have with MPAS or WRF, there'll be someone you can talk to about your issues. As usual, we're going to start this morning with model development updates and then move on from there to various specific topics. We will be having our first discussion period at the end of the afternoon, talking about MPAS in NOAA and the UFS. So I hope you'll all participate actively in that. In the past, we have had a reception on the first evening that's been catered here at Center Green. This year, as part of our cost savings, we have moved our reception to a place called the Raybeck Collective, which is a converted plumbing store that is now open and has various booths for food and drink and a tent to keep the rain off. And so we'll be adjourning to this Rayback right after the discussion period, and where we can get together, and there will be food and drink available for purchase there. The Rayback location is not that far from here. It's about 7/10 of a mile. If you just go down to the stop sign here at Valmont, take a right turn, so you're heading west at 7/10 of a mile. On the right-hand side, the address is 2775 Valmont. One thing I will say is parking is pretty limited around there. So if it's possible to double up and carpool or something, or even as walking it, depending on the weather, it's not all that far. So you have to keep that in mind. On Wednesday, for the second part of the afternoon, we'll have our poster session and coffee. The boards are all over here. We're encouraging the poster presenters to put their posters up right away, and they can leave them up for the entire workshop, so they can be perused. We have 7 of the posters are remote. And you might ask, how's that possible? So what we're doing there is posting the abstract and then a QR code that you can and use that to access the full poster that you can access remotely then. But the authors will not be engaged in that situation. So we'll see how that works out. We'll have a final discussion session on general topics on Thursday afternoon. And then Friday morning, we have a couple of mini tutorials. One is UX array for MPAS output analysis and model intercomparison, 8:30 to 10. And then the second one is MPAS JEDI, talking about the data assimilation with the JEDI system for MPAS. Just a couple of notes here. We ask the speakers to please limit their presentations to 12 to 13 minutes in these 15-minute time slots to allow a couple minutes for discussion. For remote presenters, make sure there's no background sound when presenting. You can submit comments or questions using Slido. The link is in the email that was sent out. And I should mention that those of you in person can use Slido if you prefer to raise a comment or a question, if you'd rather do it that way. Oh, I guess that's it. Okay, and then if you're having remotely, if you're having reception problems, you could try turning off your camera to improve your connection. So with that, I wish you all have a productive week, and we'll get started with our first section on model updates. Jordan Powers is going to be the session chair. Thank you.
Well, welcome everyone. As Joe said, it's great to see everyone here. This is a healthy turnout despite all the issues that he mentioned. This first session, like in previous years, will cover developments in the MPAS and WRF systems. Just some notes. Here is an advanced remote control for all the speakers. And if you do have any problem in advancing Kelvin and Chris back, just wave to them and they'll advance the slide for you. Our first speaker today will be Dr. Bill Skamrock from MCube, speaking on the model for prediction across scales. We know that as MPAS, the atmosphere component. An update.
Well, good morning, everyone. It is a pleasure to see so many people here because we were very concerned that we wouldn't be having a normal workshop this year, and it's normal as maybe it can be in the situation. I want to talk to you about some updates to MPAS. I'm going to focus on the updates, at least in part, related to the regional capability of MPAS, because that was what caused a lot of discussion and needs for improvements. And I hope you'll see that we've listened from the last workshop last year. And I'll go through the latest release and some tools we developed, et cetera. Okay, first, we have new web pages, thanks to Kelly Warner, who's back there. If you remember this, what you see on the screen, these are the old web pages. If you click on any of the links related to MPAS atmosphere, that will bring you to our new web pages, which look as follows. And what we're trying to do here, these web pages now are based on NCAR servers as opposed to GitHub, is to allow us to more easily update them and to more easily organize them, et cetera. And hopefully you'll see that that's the case. And a lot of the capabilities and updates I'll talk about in the next 10 to 15 minutes, I'll show you where on the web pages you can go to find them, because that's where you can access all these things. So we have these new web pages, and I hope you'll find them to be useful. And again, if you go to the old web pages and just click on MPAS atmosphere, boom, you'll get pushed to the new ones. So we've had a number of bug fix releases since the last workshop a year ago, and also one new feature release. To remind you, the numbering system here, version 8.2.0, for example, that came out on Thursday of last year's workshop. So we count that as actually having come out before the workshop was over. Essentially, we had bug fix releases after that, but just yesterday, last night, a little after 8 o'clock in the evening, Mountain Time, we've had version 8.3, and that's a new feature release. The release notes are all on the GitHub page. You can find them. If you just go to the repository, you'll find the release notes for all the releases going back several major feature releases, as opposed to them being like a PDF file. So that's all accessible to you there. To remind you, last year, we talked a lot about what was coming out. It was only late in the day on Thursday that it actually did come out. Last year, the major feature release, mostly focused on physics. We had the NOAA MP, which essentially advances from the NOAA land surface model. There was an aerosol-aware version of Thomson. There was a shared physics repository, so we were running the exact same physics scheme in MPAS and in WRF for a subset of the physics that exist in MPAS, and a much smaller subset in WRF, of course. And we also introduced a GPU capability for scalar transport in our code. Several years ago, back in 2020, we released a full GPU capability in MPAS, but we've had troubles getting that to work on Duratio. And as part of that process, we realized that we had a lot of work to do, and we really needed to re-implement in a cleaner way to get that capability to the community. So we released some capability back a year ago in terms of scalar transport. Now this year, and here's a partial list of what's in this latest feature release, and some of this are new features. Some of them are bug fixes or performance enhancements that I haven't included here. The first thing I want to draw your attention to up top is that we now have GPU capability in the entire dynamical core. What that does also mean is that we don't have it in the physics yet. So in terms of being usable, it still has a ways to go, but we have it in the dynamical core. It also still needs some optimization work in that core, but it's an advance. We've also got a number of additions here, most of which I'm not going to talk about, but I want to draw your attention to a couple of things down here. In particular, if you go to the bottom, we've just released now from NOAA, our folks across town in the Global Systems Laboratory, they contributed a new gravity wave drag scheme, and that's in its own physics directory. There's NOAA physics. This is for us an important advance because it's pulled directly from the NOAA repository where it's being developed. So this is something we're trying to move forward. We'll be talking more about this. I'm sure you'll hear more about it this afternoon in some of the NOAA presentations, but also in the discussion session at the end of today, because we think this is an important advance and it kind of sets the standard for how we're going to do this going forward. And now we want to accelerate that and bring that physics in, given that NOAA is responsible for most of the physics in our models. Okay, in terms of other things we brought into the release, the first thing is we've now gone from a default 4-point bilinear interpolation to a 16-point quadratic interpolation. We did this after looking for bugs in the regional version. We looked at the horizontal divergence, and this is a horizontal cross-section of a horizontal divergence on a 1 kilometer mesh. This is the California Bight region, LA, and then off the coast, the Catalina Islands. And if you look on the left, what you're seeing is the horizontal divergence with that linear interpolation, and you see the half-degree mesh that it came from. It's very obvious that that horizontal divergence field is not smooth. That's not a good thing, as you might guess. The model will deal with this and smooth it out to give you something like is on the right very quickly. But unfortunately, this is also in the lateral boundary conditions. So it's forcing the velocity fields to this discontinuous divergence, horizontal divergence field, and that's bad. So we've gone to a default now, that 16-point quadratic interpolation, and that takes care of that, and that's now the default. So this is one of the things you'll see. I don't think you're going to see much difference in the solutions because we haven't been able to trace it back to an instability, but I think you maybe, if you look at early times, you'll see significantly less noise. Okay, another thing we fixed related to, in this case, directly to the regional model is some issues with boundary conditions. What I'm showing here is a simulation from based over a little part of Antarctica. Here's the Ross Sea, and you can see Antarctica, the topography on the left, this lower left panel. What you see in the middle panel right now is the vertical velocity at about 10 kilometer level from MPAS, and it's a minus to plus 40, red to blue. And you can see right along the boundaries problems. This is a growing instability, and ultimately this simulation comes unstable. Now, we discovered this only when we went to very high horizontal resolution, down at 1 kilometer or less. 3 kilometers, 10 kilometers, 15 kilometers cell spacing, we don't see these issues. But when we went to very high resolution, we did. This is related to an approximation we made that's sort of WRF-like, but not rigorous enough, I'd say, to a zero gradient in the horizontal gradient across the boundary of the vertical velocity. When we change that to having it be zero, you see that now on the right, you can see the boundary anomalies go away and the simulations are all very happy. I think this is, well, this is now the default in the new release. We're probably going to make it an option when we go back to address that zero gradient condition and do it in a more rigorous manner. So, but now when you go to very high resolution, this W equals 0 will give you stability. There's some indication that it kind of has an impact on convection as it's coming through the boundary on inflows. And that's why we want to also ultimately fix the zero gradient condition. I think that will help in convective cases. Okay, we have released a number of new mesh tools as a result of discussions over the past several years at this workshop, that generating both regional meshes and variable resolution meshes was expensive. Can we take advantage of what we have now and use it in a better way? One of the things we've done is we put together a tool where we take a set of perfect hexagons on a plane and we use the projections to put them onto the sphere. And what you're seeing is an example of that using a Lambert conformal projection. The reason this works is because the projections are conformal, so the angles are maintained, and that's critical in the MPAS discretization. So this works fine. So this is an example of a mesh on the sphere, a conus at 100 kilometers. We have, I'll get to where it is. The nice thing about that is once you have that regional mesh, you can use the grid rotate tool to put it wherever you want. So you're not limited to just making it and having it be where you've originally placed it. You can then move it. So that Lambert conformal projection, which you wouldn't want to use in a polar region, the way it's right now constructed, you can take that, but you can move it, for example, in a polar region. And the Lambert conformal projection, the other projections turn out they're special cases of that. So that's a very general projection that we have that we've allowed to work there. The 100-kilometer mesh over conus took less than 1/10 of a second on a single CPU of Duratio to generate, so it's free. If we go down to a 3-kilometer mesh, it should be about a factor of 1,000 more expensive. It turns out it's not even close to that. It's 18 seconds as opposed to 1/10 of a second. So we're scaling a little better in that regard, but it's 18 seconds on a single CPU. So this is a very economical way to generate regional meshes. And I should also say that the cost just goes as the number of columns, of cells in that mesh. So if you take a 300-meter mesh, for example, here over Massachusetts, where I grew up, it's 18 seconds because it has the same number of cells as the conus mesh I just showed. So this provides, I think, a nice tool to easily generate meshes to get to very high resolution, because you can go to any cell spacing you want to, obviously, meters and tens of meters, etc. Okay, going back to our new web pages, you can go to the web page, and on the left-hand side is a menu of where you can navigate to. And if you go into access code and meshes and mesh utilities, you'll find this utility to project horizontal meshes onto the sphere at that link that I've circled in red there. So that's, again, available on the web pages. And if you look in there, you'll find README files and stuff that will demonstrate what you should, how you can look at that and use it. So the other mesh tool we have is, again, using projections. We can take an existing regional mesh that's on the sphere, project it back to the plane, scale it, make it higher resolution, which means we're shrinking it down in the X and Y direction in the plane, and project it back to the sphere. So that's the other tool. And the nice thing about this is if you cut out a variable resolution mesh, you can then scale it down to make it higher resolution over the whole mesh in a consistent manner. So that tool exists. For example, here's a global mesh, a 240-kilometer mesh. We can scale it to something that's almost 50 kilometers. And this is, when you project it down, essentially the map scale, what it's showing you is the map scale factor here. When we reproject it, we have to recompute all the distances and areas in that, because they change, because now you've used projections to go to and from the mesh. But that's all easy to do, and that works fine. And we hope that gives you some ideas on how to take variable resolution meshes and make use of them at different resolutions. You could also think about taking a high resolution and going to coarser, but I think that's probably not what most of us are concerned with. So here's just another example where we have a variable resolution mesh, 24 to 8 kilometer, and then you can scale it down to 3 to 1 kilometer. And this is, we've done this for some work here over Singapore. We're working with colleagues in Singapore on their forecast needs. So again, that's another tool that's available. It sits again in the same place on the new MPAS web pages. And that's a Python tool. Michael wrote it. The other one that I just talked about previously, that's in Fortran. I wrote it. You can guess what I'm more comfortable with. So that's a Python tool, and you can get it right off the page here and make use of it. So we hope with these two tools that you'll be able to take more advantage of potentially capabilities in MPAS to go to these higher resolution meshes. There are also some things in the new release that make that higher resolution capability more usable, because we've had to make some modifications to how we initialize, for example, land parameters, et cetera, in terms of how we sample them when we bring them to the MPAS mesh. Okay, there's some new documentation. The user's guide is now online on this web page. We are going to also make the PDF available. I don't think it's available yet, but it will be soon for those of you who have used the PDF before. My guess is the PDF actually may be the more up-to-date one, because that's the original one we put together, and then we migrate it to the web, and we're working on maybe how to organize that or have that be more automatic. But it is on the web page under documentation. Another thing under documentation is a first draft of a technical note. For those of you who were here last year, I told you we would have one out, and we have one that's almost there. It has 10 chapters and some appendices. Chapters 9 and 10, which are physics and infrastructure, are still in preparation, so you'll just find placeholders for those. And chapter 6, which describes diagnostics, only describes a couple of them, so that there's much more work to do. The other ones are fairly complete. So again, you find that on page there, the technical note page. You'll see something that looks very WRF-like because it has the WRF technical note template in LaTeX that it was developed in. So, but again, this is not yet referenceable. It's not an official NCAR technical note yet. So hopefully that will happen within this next year as the final chapters come in and we go through the process with an NCAR to make that a technical note that's referenceable. But it is available to you now if you want to understand particularly the dynamical core, I think is the big thing that you'll find most helpful if you want to get deeply into it. And as I noted last year, the technical note, while it looks a lot like what's in WRF, I think it extends beyond what we had in WRF, in that while you'll see the continuous equations and the discretizations we use and the derivations of both, there's also links that are in these pink boxes, which are more pink when you bring it up online. So the projectors are not perfect again, but they're getting better here. Essentially, that directly reference the MPAS code, and where you'll find these operators that are associated with the model or whatever's being talked about in the technical note. It says where you can go in the code to find them. The next step is we're going to be going in the code and saying, go to chapter such and such to see in the technical note to get an understanding of what these equations are that you're seeing in the code. So it's going to go both ways. So right now we have one, and the next step is to write the other. But this is the hard part, going in the code and saying, oh, just go to this chapter. That's easy. Writing what actually the derivations and the equations and stuff, that's the hard part. We've got almost all of that. Okay, I want to conclude with one development effort that that's not going to be talked about in any of the topics or posters, and that's an important extension to MPAS that we've talked about over the last several workshops, and that's chemistry. It goes under the name that's provisional of ChemPAS. I think that's actually a nice catchy name. I wish I had thought of it, but I can't take credit for that. So essentially, we want this to be the successor to WRF Chem. And we want to learn the lessons from WRF-Chem, try to make it more flexible and more runtime configurable, among other things. And this is going to leverage essentially developments in the chemistry laboratory here, ACOM, in a system they call Musica, which ultimately embodies essentially a model independent chemistry that we're going to utilize its interface and utilize its capabilities in MPAS to give a full chemistry capability. Note that you can see on the side here, it's being developed for the climate model right now. And also we're working with folks from NOAA and on their CAT-CHEM system to share things. So how this is all going to come together in the end is still being worked through, but essentially we're leveraging development and support outside of the core MPAS developers here in the chemistry laboratory and stuff too, and our collaborators outside, not only in NOAA, but also in universities to make this capability available. So you can, again, it's model independent and we're working with NOAA folks, but it's also, this will be used in the UFS. So there's a lot of stuff going on. We don't have a big budget. We're in the early development stages, so we don't have a timeline for any initial release, but hopefully we'll have some soon. So with that, you've seen a flavor of what's going on. There's lots of talks in the next 3 days that are going to talk about development that's already happened and coming into the model, or development that's just ongoing. We're going to have two discussion sessions at the end of the day today that'll focus mostly on the NOAA physics, but that last discussion on Thursday is general and wide open. So you have plenty of opportunity to ask questions or to make suggestions or to lobby for priorities, et cetera. So with that, thank you. And if we have a little time, I'll take a few questions. Questions?
Yeah, there are a couple online. The first one is, will the 16-point interp be passed into WRF as well, or is it on MPAS only?
Where's Michael? So my own take on it is it should be, but I don't know if it has been or will be.
Yeah, in fact, it is the same 16-point interpolation code that's used in the WPS. It's exactly the same code, in fact. Yeah.
So, and is it on by default?
It depends on the options in the GeoGrid table or MetGrid table. So it's selected on a per field basis. So in that sense, the WPS is still quite more advanced than what we do for pre-processing in MPAS.
Thank you. The second question is, has anything been done to speed up MPAS?
Ooh, I would say that has not been the focus of our development efforts this year. If you look at the release notes for 8.3, you'll find some mention of optimizations for certain aspects, mostly in the initialization though, not so much in the code. And as I mentioned, the GPU capability is the big one we've been focused on in terms of getting code capability, and that needs some optimization work in addition to, I think, work with obviously physics. But there's been no major optimization effort in the code.
Well, Yang Zhang from Northeastern University, great to see you here. I remember back to 15 years ago, we discussed how to incorporate chemistry into MPAS. When you start MPAS, I'm so glad to see that's happening. Do you have any recommendation what mechanism community can contribute to this chemistry version of MPAS?
I think Gabby can address that better than I can.
I'm happy to take that, and Mary maybe can also chime in. As Bill said, at the moment we are at very, very early stages. It's really still a lot of the design. So we want to, before we really can engage the wider community in the co-development, we really want to make sure that we have a framework in place that is sustainable, that gets us into the future, and that enables co-development. So we are unfortunately not quite yet at the stage where we can say, hey, you know, we can have this group helping with that, this group helping with that. So we still need to get the framework in place.
I'd like to learn all that.
Thanks, Bill. Our next speaker will be Jimmy Dudia, also from NCAR M Cubed. Speaking on the Weather Research and Forecasting Model, WRF, 2025 annual updates.
Thanks, Jordan. So yes, this is the annual update. We've had WRF releases. This is a 26th workshop. So the first one was in 2000 when we had version 1. And at that point, it was the WRF, the MM5 WRF workshop. And some people here may remember MM5. So we've got a couple of model generations since then. As you see, we've been basically releasing every year. The latest ones of 4.6 and 4.7 I'll talk about today. We released 4.6 last year and 4.7. This year, you might have noticed we got a 4.7.1 just now. I'll note it also. The co-authors here are Ming Chen, Wei Wang, Kelly Werner, and Anthony Isles, who's now our software engineer helping us with our releases and software aspects of WRF. So the outline, this is the outline. I'll recap the new features in 4.6 from last year. Bug fix releases since 4.6, a new in version 4.7, and some release verification tests for 4.7, and a little bit on our plans. So in version 4.6 last year, we released the shared physics suite, which I'll talk about next. 3 new wind farm parameterizations, single layer urban canopy model enhancements, ocean salinity effect to modify the humidity over the ocean, down to about 98% because of salinity. NSSL microphysics was reorganized. MYN PBL was updated significantly. The RUC LSM was updated. We've now got a CMake option, which has been developed before last year and is continuously being developed this year. And there are minor changes for the 3DTK scheme and the MP0 out option. The shared physics suite I mentioned, which was released last year, is shared between WRF, MPAS, CM1, and the DTC's single column model, which is CCPP compliant for the NOAA models. And the suite includes what we call the WRF Tropical Suite, which is a revised surface layer, new scale aware TK scheme, WSM6 microphysics and YSU PBL, and also orographic gravity wave drag. It doesn't include radiation, RTMG, or the land surface. So the shared part is the lowest level of the 1D or 2D physics subroutines, which the models have a common version of. Above that is a driver, or the CCPP framework in the case of the NOAA models, which have the linking between that and the dynamical core. And in version 4.7, in version 4.6, we had the shared physics as a subroutine, a directory underneath the physics directory. Now we access it at compile time using managed externals from the external repository directly. So we're actually accessing another repository when you compile the code. In 4.6.1, which was our bug fix release in October last year, we had minor fixes for the single layer urban canopy model. Pressure and height diagnostic outputs now have a proper missing value below the surface. And WSM6 scheme in shared physics was missing the reflectivity option, which we added back in. And the CMake option continued to be updated. Now in version 4.7, which we released in April, there were some new options I'll go into a little bit later. The UFS double moment scheme called UDM microphysics from Songyu Hong, who also developed it for the NOAA models. That's MP Physics 27. Archon, which is Robert Conrick's version of the Thomson microphysics scheme. Cliff Mass will talk about that later in the workshop. That's MP Physics 29. Incremental analysis update, which is really part of the WRF VAR system, where it adds the 3D variational data simulation increments gradually in the model as it runs. So it's a change in the model when you have 3D VAR analyses. And other changes include the shared physics with MPAS is now accessed via managed externals, as I mentioned. and it'll bring in this physics MMM directory at compile time. The MYNN EDMF is now shared with the NOAA UFS and accessed by a submodule in the way that we also already did with NOAA MP. So that's also accessing an external repository for the basic physics part of my MYNN PBL scheme. The tar files with the complete code are provided in the release page. Well, if you do git clone, that only accesses the WRF GitHub code, and the other external directories are accessed at compile time. But if you get the tar file, you'd have all the external directories incorporated in that tar file. So that's the easy way to do it if you want to see all the code at once. One of the new features is UFS double moment microphysics scheme. This is what Sung-Yu Hong has been working on. It's related to WDM7, which was in a previous option we had. Has double moment cloud and rain, so it's warm rain double moment. There are plans to extend this to water-friendly input arrays similar to Thompson. There's a new cloud fraction representation within cloud process rates. Some of the granture and sedimentation is updated to better treat double moment rainfall, and the efficiency is greatly improved by limiting vertical loops to hydrometeor tops. Sung-Yu Hong provided this slide on his updated scheme. It's not yet published, but we have a lot of these updates are listed here that I mentioned already. Also, in number 3, there's stochastic collection-based auto-conversion, which is a new way to do auto-conversion with basically lookup tables. And aerosol coupling is being worked on, especially they're going to add ice inputs as well, climatological ice, similar to the ice-friendly particles that Thompson has. Hong has provided some evaluation slides where it was used in the 2D score line, where this is a time versus X plot of the WDM7 versus UDM convective rainfall, which shows a wider spread convective rainfall in WDM7 than UDM. He prefers the UDM representation there, not having such a large stratiform region of rainfall. The article on microphysics is a talk by Cliff Mass in session 6B from Robert Conrick and Cliff Mass. It's MP Physics equals 29. There's a publication on that one in Monthly Weather Review. It's built on the aerosol aware Thompson scheme, so a lot of the code overlaps with Thompson, with enhancements for warm rain processes. The changes include the cloud drop size distribution, auto conversion, and drizzle. This pictures on the bottom right show a snapshot of the kind of results. It's an improved precipitation correlation with observations in the Northwest United States. Other changes in version 4.7, the K epsilon PBL scheme by Zonato et al. Has been improved. We had to correct the stability functions. The changes affect the unstable cases more. NOAA MP has had several minor bug fix changes. There are plans for more static data updates for soil and urban maps. And SSL microphysics continues to undergo improvements, and it's also being developed in parallel with the UFS NOAA modeling system. ClimeShoe LSM can now account for the urban climate zones, LCZs we call them, local climate zones, which were added in a previous release for the urban models. Incremental analysis update I mentioned before is provided by the IUM in Beijing. Also multiple software changes, including improving testing and testing while we do our updates, and dealing with new compilers as well as extending CMake to WRF Plus, WRF Chem, and WRF Hydro. I'll briefly go through the testing and validation. We do this every year with the new releases to test the new features. It's basically a very cheap test. We run a whole month, 2 whole months, with a grid size of 15 kilometers. May, and in fact, I think this year we did February. And the single domain is used We get the boundary conditions from GFS and initial conditions, and we do verification, basic verification of the surface and upper air compared to the GFS analyses. So the tests we did this time are comparing version 4.7 and 4.6. So they have the same physics options. This is just a sanity test to make sure we didn't change anything we didn't mean to. MYNN EDMF had substantial updates, so we tested that. Archon is a new microphysics scene we tested, UDM, and WDM7 was also run to compare with UDM to see how different it was. I'll briefly go through these. So in February, we noticed that the Archon scheme seems to have a cooler morning minimum. So that's the green line here and the February plots. So the temperature bias is lower, is stronger actually in the night times for that scheme. We're not sure why yet, but that's one of the things that stood out there. If you go to the wind speed profiles, the thing that stands out here is the spring UDM has a higher RMS wind speed bias, or RMS wind speed, but the bias is actually not very different. In the February case, none of those RMS or biases stand out for any of the new options. For temperature, the profiles, we note that the UDM temperature RMSE stands out as well on the right side of the green lines. We're going to look into these. These are recent results that we have to probably look in the future. But the temperature doesn't show a bias, so it's kind of unusual that you have an RMS bias, but an RMS increase, but less temperature bias, or no temperature bias. And February as well, in fact, you don't see the UDM standing out in February. So that was just the spring case, it stood out. I'm not showing vapor, but there's nothing that stood out in the vapor profiles either. We looked at the total rainfall for the whole month, and here is May. For each of these options, you can see at the bottom here, the key ST 47, 4.7 standard versus MYNN, UDM, and Archon in those 4 panels. Nothing really stands out in terms of the total precipitation. And the same in February, where these are the totals. And we looked at the accumulations during the 48 hours of these simulations. And UDM tends to have lower precipitation, and MYNN tends to have higher precipitation, as you can see on the winter side, especially where the green line is, well, MYNN, and the dashed red line is UDM. And we compared UDM and WDM7, and they're very similar. UDM slightly lower precipitation in the winter cases. WRF support, I'll end on what we're doing with WRF support. WRF development has slowed, so timing of version 4.8 may be uncertain. We certainly have things in the pipeline to do for the next year, but we're not sure when we'll put the next release out. WRF support via the forum will continue. WRF user web pages will be updated. There's a snapshot on the right. It's also in a similar format to the MPAS page that Bill Skamrock showed. And we'll have that later in the year. The MPAS WRF workshops will continue to be a place to share the results, of course, and WRF tutorials are already only given virtually twice per year, with the next one in July. Whether to reduce to 1 per year will be based on the registration demand for that. If we do reduce to 1 per year, we probably need to make sure the online self-tutorial serves the needs for beginners. We already have YouTube talks available from during the pandemic, and those are pretty up to date. They're created in January 2021, and we'll be able to update the slides on those as well. So we can keep a pretty good online self-tutorial if we do reduce our regular tutorials. I think that's all I had. Okay, are there any questions?
Questions? Billy, is there anything?
There are several Slido questions. And yeah, you can see them up there on the
Okay.
board now. So the first one is there more difference between MPAS and WRF?
We share the physics, and the dynamics is very similar. So we're not seeing significant differences between them if you choose the same options. Just WRF has a lot more options, but MPAS is the most common ones. So I would say no, not strictly no. Even in timing, there's not a big difference. Second question, European Centre recently released IFS public data for whether using it has caused issues, incorporating it with WPS, and will NCAR prove solution be incorporated? I'm not sure about the answer to that one, the European Centre data.
Jimmy, after this one, you can answer the Slido questions when you sit back down, if you
Okay.
have your laptop. So yeah, presenters, if you run out of time, you can answer questions on Slido afterward. And I just also want to remind all speakers to make sure that you get close to the microphone so everybody can hear.
Okay, I'll just answer that one more question. Is there a future plan for terrain following meshes? No, I mean, because in WRF, we're not really developing the die-core anymore. So there are no future plans for terrain following meshes. There are other versions of terrain following meshes out there from Livermore, for example, that have the ability to incorporate buildings, but we don't have that in the standard WRF. Yep.
The last speaker of the session will be Jake Liu from NCAR M Cubed, speaking on WRF and MPAS JEDI 2025 annual updates.
Morning, everyone. So we are a little bit behind of schedule, so I will say how much I can save with time. Let me go ahead. Yeah. So Jim already mentioned this. The IAO, that's only item related to the data simulation update in the new version 4.7. So I probably will skip of this save little time, but at least this PR message here and also the full paper reference. So you can see this maybe after meeting this, all the slide will be online. So because each year we have a lot of newcomers, so I'd like each year repeat that our lab's resource is transitioning to from WRF-DA to MPAS data simulation. So it's likely that WRF-DA will be kept updated as needed. Like this year, if we have some important contributions from community like IAO this year, so we will help to bring our code into the public release. However, our lab internally have not much resource to do too much support or answering your question for WRF-DA related. So we encourage users to adopt, explore MPAS data simulation based on JEDI. So then what's the MPAS JEDI? There are newcomers. So I like to every time mention a little bit in the terminology. So MPAS JEDI is basically MPAS atmospheric data simulation system based on so-called joint effort for data simulation integration. So the acronym is JEDI. So JEDI is a project led by Joint Center for Satellite Data Simulation. So this kind of a new data simulation software design in that different models can be more conveniently interfaced to some model agnostic DA component, such as background error covariance, observation operator, this observation model, and observation handling. So there are other models hooking up to this JEDI framework. In our lab, we focus on MPAS interface to JEDI. So a bit of history about this MPAS JEDI development. This already maybe 7 years. So we started from early 2018. That's mainly supported by US Air Force. We have a relatively, there's 6, 7 FTEs together with Joint Center. So after 3 years, we made first release, that's back in September 2021. Then we have a first publication that's focused on ensemble variational technique and the all-sky reading state simulation. Then we made another release 2023, that's right before, I think during the workshop. Then we have a second publication that's kind of another technique is EDA that's using ensemble of ENVAR. Then a couple of years ago, we conducted the first in-person tutorial in September 2023. That's in person at NCAR here. Then we have another publication that's focused on multivariate background error covariance, 3D bar hybrid techniques. So last September, we made cut off another release, version 3. Then we have another tutorial. This time is hosted at Harvard University last October. So just so that's okay. It's kind of relatively new, but this already several years. This MPAS system. So this our latest stable version is 3.0.2. That's back in last November. It's not long time ago. It's a few half year ago. So the code can be accessed from this so-called MPAS bundle repository. There is a branch tag. So this version, the good thing that this version of MPAS data is using the official release of MPAS model compared to previous versions using some unofficial version of MPAS model. That's version 8.2.2. Then we also have the MPAS data repository for this version. Then there are some other GSDA lead GitHub repository for other component is model agnostic component. So yeah, so that's the latest tutorial or web page. So we have a 2-day MPAS data tutorial, typically followed by 3-day MPAS model tutorial. So we do together for the 4 week. So all the material, including the presentation slides and also test data set, instruction for practical sessions, all online. So people can download and you can maybe do the practice on your own machine. And also, I include this these slides of the year, each year because there are newcomers here. So for the MPAS data, so what we can do with this new generation DA system. So there are quite a few. I can say there are not necessarily more than worth DA, but basically we have a lot of options for doing data simulation. For deterministic analysis, you can do 3D VAR, the cheaper, easier, and 3D 4D EM-VAR, and their hybrid variant, and the so-called dual resolution capability. So in that, your minimization analysis increment ensemble resolution can be lower than your actual full field analysis. So that's make your computation cheaper. So ensemble analysis technique, you can do EDA and also LETKF and again form LETKF, there this variant of LETKF. So next thing with MPAS data is that the analysis is directly done on the MPAS unstructured grid. That's next thing is whether uniform or uniform resolution, variable resolution, global or regional. So you can do configure MPAS data easily. So the mandatory analysis variable is the UV component, temperature, moisture, surface pressure. And we can also do a kind of advanced capability for doing cloud precipitation affected satellite reading state simulation. In that case, you can also include hydrometer of the mixing ratio of hydrometer is part of analysis variable. You can also do radar DA. For now, it's mostly reflectivity and radial velocity. We also recently include the surface DA for all these 5 variables. So next slide, in the next few slides, I will give you some highlights for our recent new research and development in the past year. So the first one is the hybrid 4D EMR with all-sky reading state simulation. This is by Robert. So basically here we show is the this ETS precipitation score as a function of forecast lead time compared with 4 experiments. There is green, the yellow curve is the 3D technique, and the green curve is the, I'm not sure the, okay, we do have the, okay. The green curve is the 4D technique, then we adding the all sky readings in the 3D technique. So we have 4D with the all sky. So interesting result here is that if you're doing 3D technique with all sky DA, the performance can be better the 4D technique without all sky DA. Okay, so something Robert has a paper I think ready for submission. Another new development is by Tao Sun is the calculation capability to calculate ensemble-based forecast sensitivity to observations. So these techniques can tell you more conveniently, the with observation give you most positive impact or negative impact for reduce the forecast error with different error metric. Okay, this here we can use different metric like kinetic energy, that's for the wind field, potential energy for the temperature, moisture energy is kind of moisture field. So that's mostly looks like we have mostly from all the observation have a positive impact. That's nice, and which observation have largest impact. Another thing, this afternoon, Li Peng Jiang will give a talk about this offline statistic tool for the variational bias correction estimation coefficient and the covariance estimation. He will give a talk, so I may skip this one. And the last thing I want to show you that is we made some good progress for the all sky reading state simulation for zero stationary satellite sensor ABI. So we can simulate 3 watt vapor channels in the all sky conditions, all weather conditions. Here what I this the regional convective scale application over the Western US. Oh no, that's Eastern US, not Western US. So here I show this the root mean square error reduction compared to the benchmark experiment. So benchmark experiment, there is no ABI reading state, 3 watt vapor channels. Then we add 3 watt vapor channels in clear sky condition, and also this all sky in the green curve 3D. Then we have also the right curve is the hybrid 4D EMR using all sky ABI. So you can see that gradually this performance is better and better when we verify against short-term forecast or against ABI itself in the all sky situation. We can also do the radar DA here over US at 3.75 kilometer for the rainfall forecast scale against the stage 4 observation. You can see the red curve is this by adding radar data above the blue curve is the all sky ABI readings. So ABI readings already give you some better performance for the rainfall forecast and radar, for the first shorter term, 12 at least up to 12 hours. We also have some quite significant benefit by adding radar data. So just kind of a little bit concluding remarks. I think MPAS data is mature enough for the community to adopt, explore for the research or operation. There's still a new generation community system. There are some advanced capabilities, different DA techniques, and also the all-sky DA for readings radar. We know there are already several parties were very interested in implementing this in their operation, like U.S. Air Force, NOAA's RFSV2. We also collaborating with Singapore CCRS and Taiwan Central Weather Bureau. Brazil, also the private sector, I know the weather company also doing this. We made some progress for infrared readings in all sky situation. It's still more work to do, but I think this, now we do have some good some result. So there more development is still ongoing. So yeah, so I will stop here, but telling you that yes, they already mentioned this Friday morning we will have a mini tutorial providing you more information. This is about 1.5 hour tutorial, so you should hear more information. I will stop here. Thank you.
There's a microphone.
Are you thinking also to implement RTTOV radiatory transfer model to assimilate radiance satellite data?
Yes, yes. So actually, this already both CRTM and RTTOV already interfaced in JDI. The RTTOV mostly the two versions of RTTOV interface. One is Fortran-based interface developed by UK Met Office. NCAR, we also developed a version C++ based interface. But it's there. We didn't test extensively yet, but we do plan to maybe make also use RTTOV in the future more extensively. Yes. You have the estimation about computational cost, uniform 3 kilometer. Yeah, that's depend. This uniform if the global mesh. Okay, that's a lot of cells. That's basically the cost depending on how many grid cells you have. For the global 3 kilometer cells, that's the if I remember correctly, that's the 65 million cells. That's I think it could be working, but how many nodes you need, we didn't try it yet. But a few years ago, I already tried with 7.5 kilometer resolution. That work seems fairly reasonable. So I think if you have a large machine, I think should be okay. Yeah. Did I take all care? Yes. Yes. Technically, yes. So Zeta UFO, we do have a capability to include correlated cross-channel correlation for some hyperspectral IR sensor and also for all sky or no all sky DA. That's okay. Yeah, we can do that. Okay.
Okay, folks, that brings us to the end of the first session. Thank you very much. Thanks to the speakers again, all very good and informative talks. We'll have a break now and return at 10:15. Thank you.
Well, welcome back, everyone, from the break. This second session this morning, which will bring us to lunch, we're going to start out with a talk about MPAS LES, which will appear in the not too distant future. And Jimmy Duty is going to be giving that talk.
Okay, as you know, WRF already has an LES option, and MPAS is yet to get this, so we're adding it now, based on the ideas or the same schemes that WRF has. So I'll talk about the MPAS LES. It's an incorporation of large eddy simulation physics into MPAS. The LES physics is basically three-dimensional turbulence suitable for grids where delta X is of the order of delta Z. And in MPAS, this provides a physics-based subgrid mixing terms when the PBL is not activated. So this is an overview of why you need or when you need LES. Typically with turbulence, the energy containing scales are around 1 kilometer or less, 100 meters to a kilometer. For grid sizes much bigger than this scale, PBL schemes are adequate. All the eddies are subgrid, and you can do everything that you need to with 1D column model of subgrid vertical fluxes. For finer grid spaces of much less than L, of the order 100 meters to a kilometer, you need a LES scheme, where an LES scheme, all the major eddies are resolved. And basically you're doing three-dimensional turbulence, so horizontal and vertical mixing are unified in some way where they're not in PBL schemes with horizontal diffusion. So we have a few subgrid options that we're adding to MPAS. The 2D Smagorinsky is really just a horizontal diffusion option. 3D Smagorinsky is a diagnostic mixing method where the diffusion coefficient is given by this kind of formula with a deformation d squared, given by these terms I'll show later, but they're basically velocity gradients. And then there's also a dependence on the stability through a Prandtl number and n squared from Weissler frequency. The 1.5 order TKE is the one I've been testing mostly here. And there the K coefficient, diffusion coefficient, depends in proportion to root of the turbulent kinetic energy E, where the turbulent kinetic energy is now a prognostic equation, which has several terms: shear production, buoyancy production, and dissipation. The shear production term especially has these velocity gradients in it. So we need to add also the Moist-Brunt-Weissler frequency n for the 3D Smagorinsky and also the buoyancy production here. So these are what those D terms look like. They're just basically velocity gradients in different directions. And note that these equations are Cartesian velocities, u, v, x, y. And we're on an MPAS grid, which is not Cartesian. You have the hexagons or any general shape, mostly hexagons, where the velocities are defined normal to the faces only. And everything else is defined in the middle of the grid cell. So how do you get from one, from this to this? So that's a lot of where the task is. There's a lot of geometry here. So we transform to Cartesian coordinates using the local angle of the edge relative to a nominal XY direction. And we have the U, which is the edge normal velocity. That's one of the prognostic variables. But we also need a V at the edge parallel velocity, which is not a prognostic variable. It has to be interpolated in MPAS, and MPAS already does this for Coriolis force. And it's not an easy interpolation. It takes many points to interpolate this V velocity. But then once you have these two components, you only need the theta, and you can convert them to the Cartesian one. And to get the cell gradient, such as du dx, there's also another piece of geometry needed, where we sum the projected gradients around the cell and use an identity relating the area of the cell and the du dx to the sum of these terms, which expand to UE and VE in this way. So we end up with a dUdx as a function of UE and VE with these constant parameters AE and CE that are basically geometrical functions of theta E for each edge. So you can pre-calculate all these A, B, and C variables and directly get the UDX from these UE and VE using those. So now we have the D terms required for 2D and 3D Smagorinsky in the 1.5 order TKE. That's given by this set of formulas for the horizontal. The W terms are also derived when we average W to the edges, and you can do the same kind of gradients for W, where you need the horizontal dW dy and dW dx. And that's so with all that geometry, you actually can get these Cartesian terms from the specific velocity locations of MPAS. Okay. Try to advance. It's not advancing. Okay. So the testing so far has been in an idealized case called the Southeast Atmosphere Study 2013 field program, where it's forced with a typical diurnal cycle derived from a field program. There are multiple LES models that were in intercomparison. There was a program, an NCAR program led by Ned Patton, where we had these multiple NCAR LES models taking part. 15-meter grid size, 250,000 columns. The top at 3 kilometers, 200 levels. And the time step we could use was 1 second, which takes 40 sound substeps, and we're doing an 18-hour run. Yeah, I need to advance the slide again. So this is just one result, which I won't show much of, but just showing that the MPAS is in the pack. It's the gray line here. As you have the PBL growth of theta, you have all these different models, and the MPAS one is doing as we expect, growing the PBL at the same rate as the other models there. There are many of these other diagnostics we looked at, and this was the one that I'm showing. We still have to advance again a slide. This is doing it. And another snapshot of the LES simulation with MPAS is here. Vertical motion at 150 meters above at 14 hours into the simulation, showing, as you expect, basically these cells with linear features in the vertical motion. TKE is also obviously active, and the perturbation theta is here. So it's showing it's working. We have a scheme that does what it should do at the idealized LES scale. And the idea now is to, next slide, please. We're testing MPAS now for the idealized supercell case at 167 meter grid size. We can, with the MPAS LES, we can take the idealized or physics-produced surface heat, moisture, and stress. Surface heat, moisture, fluxes, and stress. Currently, no account is taken of the coordinate slope, but we will. The initial step will be to reduce the horizontal diffusion when the slope is steep, using a non-dimensional parameter related to the coordinate slope and the grid size. So this is a non-dimensional alpha. And when the slope becomes very steep, we'll phase the diffusion coefficient down. This should keep the model stable while limiting unrealistic diffusion up hill slopes. So the main code in MPAS is in a new module, which is under the dynamics directory called MPAS ATM dissipation models, and it will be activated using a config LES model. And you have the options here of 3D Smagorinsky or 1.5 order prognostic TKE. And the next, yeah. So the current code is in a branch that's updated to version 8.2.2. The code needs to be merged with other developments. And the plan is to have it at least in a release branch later this year. think that's all I had. Good.
We have time for some questions.
Oh, okay.
No, no, it's okay. Nice talk. You showed just that one result with compared to the other LES models, but that was the mean of the theta. Have you looked at the variance and how the turbulence is?
Oh yeah, there's all
doing?
kinds of diagnostics. There's so many other plots I could have shown there.
No, yeah.
And it does fall in the same band as all the other
Yeah,
LES
okay.
models in that
So
comparison.
it's-
Looked at variances, the U prime, W prime, U prime, W prime, theta prime, all those fluxes as profiles.
Right.
And yeah, the eddy heat fluxes and moisture fluxes.
Oh, great, thank you.
There's a lot of those plots I could show.
Are there any Slido questions, Kelly? None, okay. Geez, Lou Wicker, I knew you'd be a problem. Okay, Lou, do you
there are
have,
some
Lou, do you have a question? Need to use Slido.
He's our next presenter. We're good.
Otherwise in the PBL in the Caribbean. It's for high resolution simulations. So anytime you're running a grid size less than a kilometer. Oh no, is that, or should I look at the first question? Is the LES model in theory working on the global scale? In theory, yes, but in practice, I don't think so. 3 kilometers global scale is currently challenging. 1 kilometer takes more than current computers in most cases. So in theory, yes.
Okay, let's thank our speaker again. And our next talk is our first virtual talk. And it's by Yi Kao. I'm not sure I pronounced that correctly, so excuse me if I didn't. And he's going to talk about developing and evaluating the MPAS urban modeling system.
Oh, yes. Can everyone hear me?
Yes, we can hear you.
Okay. So hello, everyone. I'm Yi Cao from the Hong Kong University of Science and Technology, Division of Environment and Sustainability. So today I'm going to share our work developing and evaluating the MPAS urban modeling system. So I'd like to start my talk by a little introduction. So actually, the population-dense cities like Hong Kong are facing weather extremes. For example, attributing to the global warming and the local urbanization, there is an increasing trend or frequency of extreme heat, both hot nights, very hot nights, and very hot days, and happening in Hong Kong. For example, in the upper panel, you can see the trend of extreme heat, and as well as the extreme precipitation in terms of the hourly rainfall. So actually, we need a very high resolution, both numerical model and weather data to evaluate and assess the impact of weather extremes to the public in cities like Hong Kong. And so traditionally, what we do is researchers actually prefer to use WRF Urban to dig into this topic. And the WRF Urban is a well-developed and a very mature community to do urban modeling. And for these two literature I listed, you can see it generally use a multi-nested dynamic downscaling approach. So I think the most common configuration is we have 4 nested regions, like from 27 kilometer, and that resolution is consistent with the FNL or EI5, that's roughly 25 kilometers. So we use that to drive our model. And we go down to 9 kilometer, 3 kilometer, and eventually 1 kilometer. And within the resolution of 1 kilometer domain, basically what we call is DO4, and we turn on the urban model so that we can use our urban climate model to simulate the effect of urban heat island or urban wind field and the humidity and so on. But actually, since WRF use a uniform longitude and latitude grid, it is not that flexible in terms of the selecting the regions we focused. And for 4 times multi-nested region is basically very computational expensive. So what we're trying to do is we want to use MPAS. So MPAS actually offer us a different point of view because it actually use a unstructured resolution variable mesh, the centroidal Voronoi tensillation. So what we're trying to do is we implement the urban model within the MPAS structure. So to do this, we actually need to overcome 3 main challenges. The first one is how we generate a high resolution mesh. But I have to say, before I joined this meeting, I actually don't know there are already updates about the high resolution mesh and the land use data on MPAS version 8.3. But based on my MPAS, my MPAS version is version 8.2.2. So I'm still going to share what we have done, and maybe in the future I can try to make this work within MPAS version 8.3. So in the left panel, you can see this is the MPAS release, the mesh, global mesh. This is the closest one from 92 kilometer to 25 kilometer. And this one in the lower panel is the 60 kilometer to 3 kilometer resolution. Well, 3 kilometers is already very high resolution for global or mesoscale weather modeling, but we think it's still not enough to represent the urban parts. So what we do is we generate a 30 kilometer to 500 meter global variable resolution mesh. And you can see in thousand China, outside of this refined region is 30 kilometer resolution all around the globe. And we centered in Hong Kong, we let the resolution gradually increase until in Hong Kong, like the resolution is eventually 500 meter. And we make this mesh based on Python with a library of MPAS tool and the Jigsaw Pi. And you can see this mesh in Hong Kong. The red nodes represent the urban region. And the second progress we made in terms of the high resolution mesh is we developed a user specified mesh, arbitrary shape. In arbitrary shape, user can choose a random region and random shape to do some research they are interested in. For example, also in thousand China, I plotted a blue circle. It's not really a circle, it's just a nearly oval shape region. And within a blue circle is 8 kilometer resolution. And you can see there in near Hong Kong, there's a green line. The green line is, within the green line, the resolution is actually 2 kilometers. So between the regions, between green line and the blue line, it's actually the resolution is gradually increased from 8 kilogram to 2 kilogram. And finally, there is a Hong Kong in red shape. So again, the resolution will increase from 2 kilometers and 8 kilometers. So this tool is also based on the Python, Jigsaw Pi, and the MPAS tool. So this the first, we made a high resolution mesh, and the next step is that we need to represent urban. We need to use a high resolution land use data, local climate zone. In WRF, there is already well-developed land use data. For example, the 100 meter CGLC MODIS LCZ. In WRF, we can directly use it. But since the structure of MPAS and the structure of MPAS is different from WRF, even it's global, but we cannot directly use it within MPAS. So what we do is we combine this 100 meter CGLC MODIS LCZ dataset with a default 30 seconds MODIS IGBP NOAA land use. We fill the pole region, because this 100-meter LCZ data actually covers all the cities around the globe, but missing the pole regions like South Pole and the North Pole. It only covers from 60° south to 78° north. So we do a combination of these two data sets. And in Hong Kong, you can see the precise local climate zone within Hong Kong. Here is the Hong Kong airport, and this is the Hong Kong island. So all this urban part is well represented within our model. So the third challenge is how we implement the urban model within the MPAS structure. Here I wrote coupling single layer UCM, single layer urban canopy model. So even though our topic is coupling MPAS urban, but urban model actually contains single layer UCM and the multi-layer UCM, for example, the big band model. But until now, we only developed the single layer UCM. We hope we can develop the big band model in the near future. And so if we look at the structure of MPAS, how MPAS call NOAA MP, we can understand. For example, in the MPAS core, it calls MPAS physics driver, and then it calls MPAS land surface model driver. In the original path, within this driver, it calls NOAA MP driver main, and then calls the NOAA MP column, single column model. So for our coupling, after we conduct the previous two steps, we add a new interface, just as the NOAA MP version, offline version does. We add a new interface called NOAA MP urban driver main. This new interface, and then this interface calls the single layer UCM. If we directly look at the code, you can see in the code, like the core atmosphere physics, MPAS atmosphere driver, LSM, NOAA MP.f. There, default, we call NOAA MP driver main, and then we add a few more lines. If we select we set the surface urban physics to be true, then we call NOAA MP urban. So that means we couple our urban model within the MPAS structure. And then in the name list of MPAS, we can set a config urban physics to be true. So we can use our single layer UCM within the MPAS structure. And after that 3 steps we have done about the coding works, we have done some experiment to see the single layer UCM's impact. And we have performed 2 simulations from the 2013 November 1st to 2013 November 11. So that's totally 10 days simulation prediction run with 2 cases. The first one is MPAS SL UCM. This one uses a single layer UCM model, and the MPAS control run. And the control run don't have a urban model, it uses a bulk model, which means it uses a prescribed albedo and heat properties for urban parts. So there are more details about our model configuration. For example, our time step is 3 seconds, because MPAS have to use a unified time step for all resolutions in the global mesh. So since our finest resolution is 500 meters, we have to use a very small time step for all the grid. So here we use 3 seconds, and our resolution is 30 kilometers to 500 meters. Our initial condition is FNL, and the vertical layers we set 55 layers up to 30 kilometers height. And it's also important to notice that our first model layer height is 75 meters. This is because in single layer UCM, we had to let the first model layer higher than the building. So it's different from multi-layer UCM. We had to set it very high so that single layer UCM can work. And for the parameterization, we use the convection permitting suit, but we have done some modifications. For example, we changed the convection permitting suit of boundary layer. We use YSU, and surface layer we use the revised MM5. But land surface model we all use the NOAA MP. So I will share some initial results about our urban model. So the first one I want to talk is about all the averaged 2-meter temperature over Pearl River Delta region and Hong Kong. So the first column is the MPAS single layer UCM, and the second column is the MPAS control, and the third column is the difference, single layer UCM minus control run. So you can see in the PRD regions, there are a significantly increase in 2-meter temperature. On average, we saw a 2.4-degree increase in PRD. And in Hong Kong, we saw a 1.55-degree increase. And within, you can look at the figure F. Actually, it agree well with the distribution of urban point or in LCZ. You can see the significant heat from the Hong Kong Island, Hong Kong Airport, Hong Kong Island, and Kowloon. And if we separate it into a daytime and nighttime temperature difference, we still saw a significant urban heat island effect. We saw a 3.3-degree increase in nighttime and 1.55-degree in daytime. So that's temperature, 2-meter temperature. The second variable we look at is specific humidity. If we look at the third column, actually single layer UCM generally decrease the humidity, making urban points drier. And for PRD regions, we saw a 3.3 gram per kilogram decrease and a 4.03 gram per kilogram decrease over Hong Kong. And it is an inverse proportionality between Q2 and T2 because we increase the T2 and decrease the T2 because of we add the single layer UCM. And the last variable we look at is the 10-meter wind speed. 10-meter wind speed. If we directly look at the third column, you can see the single layer UCM actually increased the 10-meter wind speed because we think the 10-meter wind speed is calculated above the displacement height. So if following the exponential law, theoretically the 10-meter wind speed should be higher. And you can see the nearly 1.1 meter per second increase in PRD and the 1.26 meter per second increase in Hong Kong over urban points. So that's all the evaluation and development for MPAS urban today. But I want to mention that this model is still under developing. We still have a lot of bugs in terms of the diagnostic variables and other issues. So hopefully we can make this complete and release it maybe at the end of this year. So thank you, everyone. This is my recent work.
Thank you. We have time for some quick questions. So I understand that a release, will that be a release within the MPAS release itself, or is this going to be separate from that?
No. We want to actually merge to the main branch of MPAS. But I know there are some actually, as I said, we don't know that in MPAS 8.3 there are already some updates in terms of the land use and the high resolution mesh. So we still need to develop something more.
Okay, anything out in virtual land, Kelly? No. Okay. Well, thank you. I think we'll go to our next talk. We're actually on time here. And the next talk is going to be by Zushan Lin, and talking about the effects of soil organic matter on WRF NOAA MP simulations of surface air temperature.
Okay, good morning, everyone. So my name is Zhishan Li. I work at Research Application Laboratory at NSF NCA. And today I would like to talk about some of the issues that we found in the couple NOAA MP with the WRF, especially for the surface air temperature. So First of all, if you're not familiar with this, the CONUS 44 is one of the NCAR long-term regional climate simulation using the WRF model version 3.9.1. And in this figure, you can see that actually the model performance for the climatology looks very good compared to the PRISM data, that is the R-scale product from the station data set over the CONUS region around 4 kilometers. But if you're looking at the temperature difference between the May to September daily mean 2-meter temperature difference in the below figures, the CONUS 404 minus PRISM data has kind of the temperature warm bias across the majority of the land areas. And this temperature warm bias mainly happens in the nighttime. So at the same time, the LANSFS modeling group is trying to looking at the NOAA offline simulations compared with multiple sites. The left figure is showing the comparison in the NOAA simulation for the Flasna Tower sites in the blue line and the red line. The blue line is the baseline NOAA simulation without the roughness of layers turbulence physics improvement. The ISL scheme is the recent improvement in the roughness of the layer turbulence physical scheme by Ronnie et al. In 2021. But in this figure, you can show that the NOAA multi-year mean ground heat flux is kind of overestimate no matter what the including of the roughness of layer turbulence or not. And just remind that the downward is the positive of the ground heat flux in the daytime. At the right side, the NOAA side, actually, Mike also looking at quite similar issue in one of the side in the AIM, Southern Grand Plains side, SGP side. The black line is the model, black line is the observation, and the two models, HR1 and HR2, showing higher ground heat flux amplitude compared to the NOAA. And in this figure, the downward negative is the daytime, so the positive is the outward at the nighttime. So can these two problems be linked together? So we hypothesize that if we can reduce the amplitude of the ground heat flux, the overestimation of the nighttime upward ground heat flux, that could be the reason for the nighttime of the 2 meters air temperature warm bias. So if we can reduce the ground heat flux, how do we do that? We can first to reduce the thermal conductivity of the soil that slow down the heat transfer to and from the soil. To reduce the soil conductivity of the soil, that can enhance the insulation of the surface skin layer from the soil. That could lead to the nighttime cooling enhanced and impact the 2 meters air temperature. But how do we do that in the physical meaning? Actually, if you're looking at the soil composition map, soil can compose with the pore space and the solid part. And the solid part includes the mineral parts and organic materials. And we know that the soil with the organic matters has much lower thermal conductivity compared to the mineral soils. So we try to include this in the NOAA offline land surface model simulations. In previous literature, most of the study used the additivity hypothesis that consider the soil thermal and hydraulic properties are estimated as a weighted combination of the values from the mineral and the poor organic source. And the poor organic source can be represented as a pit soil that has a huge amount of the carbon in the soil that has lower thermal conductivity, higher soil heat capacity, higher porosity, and higher saturated hydraulic conductivity. And if you look at the figure in the right, soil layers actually have a vertical profile with most of the soil organic matter is abundant in the first layer compared to the bottom of the soil. That was the background or the subsoil with the mineral composition mixtures. So in order to do that, the past study actually have been also looking at this in the NOAA version in the Canada at the single sites. The right below figure is in their paper. They found out that summer season, the soil organic can reduce the ground heat flux, and the winter season also reduce the magnitude of the ground heat flux compared to the control line in the blue. And Lamar et al. In 2017 also applied the WRF NOAA to study the fire-induced surface and soil organic matter changes on the diurnal temperature in the Colorado. However, this version, and this implementation is not in the official release of the WRF NOAA. And also the 2D maps of and is not available in the WRF NOAA in these previous two studies. So we actually implement the soil organic matter for the spatial distribution that using the data from the soil grids 2.0, the resolution of the data about 1 kilometers. And for the 4 layers that is showing here from the layer 1 in the left to the layer 4 in the right. And then we use this soil organic density map divided by the maximum possible value of the soil is about 130. And we get the organic fraction for each soil layer. Then we do each layer soil properties with the combination of the pro-organic P soil properties and the mineral soil properties using the organic fraction for 10 different soil parameters, including the energy and the water soil parameters. So we first do the offline couple testing of the NOAA in 2 seasons, January 2013 and July, but due to the time only showing you the winter season, now you can see the offline simulations showing the higher reduction of the thermal conductivity in the first soil layer. The figure is showing correlated with the higher soil organic fraction of the region with the reduction of the soil thermal conductivity. And the below figure is showing the NOAA results of the ground heat flux with minus without soil organic matter effects. At the daytime, the ground heat flux reduced, and at the nighttime, the ground heat are outward reduced. So the daytime, again, daytime is the downward positive of the ground heat flux from the air to the soil. Then we're looking at a couple of NOAA simulations in the Southeast US for the project, especially actually this project is looking at the urban in the Atlanta city. We have a 5 kilometer domain and a 1 kilometer domain in the center of the city. And for this month of simulation in 2018 February, the model is compared with the PRISM data, showing the daily minimum temperature has a very strong co-bias in this area. Let me see if I can use, in this area. And also the daily maximum temperature has very strong co-bias. But in the rest of the region, it's showing the warm bias in the daily minimum temperature and the daily maximum temperature. So model is simulate to much lower temperature. In the city region, if you compare with the Masna station data, we're looking at the snow rain partitioning in the NOAA with the temperature stress of the default partitioning is showing a higher Roomy square about 5 and cold bias about -4. And we use the WRF microphysics, precipitation partitioning and snow rain partitioning. The cold bias, because of the snow issue, is gone, but we still see a lot of cold bias about -4 degrees Celsius. So a similar cold bias issue was probably also recently found in the WRF forum that you can see here. So before going to the soil organic part, I would like to address this issue. And this is likely because of the canopy storage changes. So canopy storage changes the evaluation of the heat stored in the canopy layer due to changes of the temperature of the vegetation. And it's based on the aerial heat capacity of the biomass and the canopy water. So in the NOAA, aerial heat capacity of biomass is determined by 3 terms: the parameter CBIOM, plant area index, and the volumetric heat capacity of the water. So CBIOM is the canopy biomass heat capacity parameter in the NOAA table. This default value is about 0.02 for all vegetation types. In this area of the cold bias, we have evergreen needle-leaf forest with the plant area index about 4.4. But we actually know that in this, the forest biomass in the Southeast Asia, Southeast US is about 10 kilograms per meter square from the Goodell 2019 paper. And the range of the specific capacity of the biomass actually depends on if there's a moisture in the biomass or not. The dry wood is about 1700, the moist about 2000 to 3500. So roughly, if we calculate using these 2 terms, the order is about 2 to 4 of E04, order of the 4. So if you use the NOAA equation, we can calculate these 3 terms. Combination is about 3.7 equals 5, which is about 10 times or larger than the probably the realistic conditions. So we decided to change the CBRN from the original parameter 0.02 to 0.02. That does effectively reduce the cold bias region that we found in this area. And at the same time, the rest of the region actually also reduce some of the warm bias for both the daily minima and daily maxima of the 2 meters temperature. And next, going back to the soil organic effects on 2 meters end temperature bias, now we see the model with the soil organic effects actually reduce the daily minima to temperature warm bias, but also reduce the cold bias in the daytime maxima temperature. But in some of the region already have the warm bias in the maxima daily temperature, it becomes much warmer. We benchmark the result with the WRF-NOAA simulation that is showing quite similar. With the NOAA WRF couple simulation has quite similar warm bias in the daily minima temperature, we found the soil organic effect. And with the WRF-NOAA has actually have a cold bias in daily maxima temperature compared to after with the soil organic effect in the NOAA has a warm bias. So overall, I think the NOAA performance gives us confidence that we think the soil organic effects can reduce this temperature bias. And also looking at the soil temperature because those parameters are hard to validate in reality. So the models compare with the in situ soil temperature data. Across majority of the points, the black circle is showing the improvements from the soil organic matter effects with the Rubin scale improvements at the 5 centimeters of the soil temperature. So overall, this study, we actually looking at the two methods to reduce the temperature bias in the WRF couple NOAA that reduce the extreme cold bias in surface air temperature through the changes of the canopy storage, improvements of the diurnal cycle of the 2 meters end temperature and the soil temperature through the soil organic matter effects. And we are going to implement this into the WRF NOAA versions and run the simulations like Corners Wilds at a high resolution around 4 kilometers. With that, I would like to thank you for your attention today and listening.
We have time for a few quick questions.
There is one question on Slido. Could increasing the NOAA MP soil layers to more than 4 layers help with the introduction of organic matter? How is the process going to finally add an option to increase the number of soil layers in NOAA MP? Thanks for an excellent talk.
Yeah, thank you for your question. So yes, this NOAA MP, we actually also have looking at different soil layer combinations, like trying to extend the soil layers, not just for the 4 layers. And then we also can use the same data to consider of the soil organic for the multiple soil layers. Yeah, so there's no conflicts that we at the same time we can increase the soil layer and also using the soil organic matter data, especially the soil organic is mostly covered in the first layer compared to the subsoil layers.
Any other questions? Okay, let's thank our speaker again.
Yeah, for this question, yes, we use the BAP scheme, the urban option 2 for the urban processes. Thank you.
Okay, I've been instructed to remind speakers to please speak into the microphone and loudly so everyone can hear. I don't know how it's transmitting virtually, but please speak up. Our next speaker is Laura Fowler, and she is going to talk to us about implementation of the GoCart 2G aerosol model into MPAS atmosphere.
Okay, first I want to apologize for the state of my voice. I got a bad cold about 6 weeks ago and it doesn't seem to really get better very fast here. So I want to report on some of the results we have on the implementations of the second generations of the Goddard chemistry aerosol radiation transfer model that has been implemented in MPAS atmosphere. So first, a few motivations. We know that aerosols are an important component of the Earth atmosphere system. They affect directly the Earth radiation budget through absorptions and scattering of long and short-wave radiations, hence modifying heating rates. They also have an indirect effect through modulating the life cycle of clouds and precipitations, for instance, through the activations of cloud liquid water droplets, ice nucleations, and they also affect air quality through direct emissions of anthropogenic and natural sources like mineral dust, driving increasing emissions in urban areas. Our motivations, or some of my motivations, to implement a prognostic aerosol model in MPAS includes, first, I wanted to expand the standard MPAS to a more integrated Earth atmospheric systems at all scales, including for numerical weather predictions, adding the first interactions between aerosols, aerosol chemistry, and MPAS physics as a precursor to adding a full aerosol and gas phase chemistry model in MPAS-A. And finally, also, and more importantly, I think enabling new research interests using MPAS-A. For instance, research related to air pollutions and wildfire studies through more realistic implementations of anthropogenics, biomass burning, and biogenic emissions. So what is a go-kart 2G, the second generations of go-karts, which has been fully described in Kulako et al. In 2024. So the first version of go-kart, for instance, the one that is currently implemented in WRF-Chem, included 5 active aerosol tracers, 2 types of black carbon, hydrophobic and hydrophilic, 2 types of organic carbon, hydrophobic, hydrophilic, 5 types of mineral dust in 5 separate bins, sea salt in 4 separate bins, and sulfate. Now, the go-kart 2G aerosols model adds 2 relatively active tracers. We added the brown carbon, which in its hydrophobic and hydrophilic versions, and mainly to account for differences in the absorptions in organic carbon between biomass burning emissions and anthropogenic sources. go-kart 2G also includes nitrate in 3 separate bins, 1 fine modes, and 2 coarse modes falling by and all in 2009. We also added a simple parameterizations of SOA, second organic aerosols, to form brown carbon and organic carbon from what is referred to as volatile organic carbon, or VOC. In addition to the aerosol model itself, go-kart 2G can also compute the aerosol optical properties of all the different species at individual wavelengths, for instance, at 500 nanometers, looking lookup tables for the calculations of the AOPs for each aerosol species. Those spectral AOPs are right now being used for data assimilations of aerosol optical properties measured by the PACE, the NASA PACE experiments, which stands for Plankton Aerosol Cloud Ocean Ecosystem Experiment, using within the MPAS go-kart JEDI system. We can also compute the aerosol optical properties, also using lookup tables for the 30 RTMG spectral intervals, 14 in the shortwave, and 16 in the long-wave intervals for interactions between aerosols and radiations using the RTMG radiation codes. In addition to specific chemistry processes, for instance, oxidations, hydrophobic to hydrophilic conversion, go-kart 2G include a set of physics parameterizations like gravitational settling, dry depositions, and wet removal. And these parameterizations are being replaced by MPAS physics to kind of strengthen the aerosol physics interactions. So in terms of emissions, we added anthropogenics, biomass burning, and biogenic emissions. Those emissions comes into gridded latitude, longitude gridding emissions, and we interpolate them to those unstructured MPAS meshes using a Python-based tool outside of MPAS. And then they are used as input emissions using input streams as in MPAS, as we do, for instance, sea surface temperature and sea ice, or at the stream for that matter. So they include monthly mean anthropogenic emissions that we downloaded from the CAMS global inventory, emission inventory. We included daily mass biomass burning emissions from the fire inventory from NCAR or FIN. And we also added monthly mean biogenic emissions downloaded for CAMS. They were earlier produced by Megan version 2.10 for SOA productions. So the bottom two panels shows the monthly mean anthropogenic emissions for organic carbon for July 2019. And the right panel shows the biomass burning global emissions of organic carbon also for July 2019, which will be used in the results that I'm going to show you later. You can see the maximum anthropogenic emissions over India, as well as over China and other areas of the globes. In terms of biomass burning emission in July 2019, we can see emissions over Southern Africa, South America, and some over Alaska as well. Okay, that's working. Can I have the next slide, please? Okay, so we need to run GOCARD2G as a full system. We also need additional proxy variables. For the static fields, we need to interpolate the fractions of the erodible surface, the fractions of clay, and the fractions of sand, and that is being done within the static field themselves, and mostly used for the emissions of mineral dust. We also needed to add 6 prognostic mass mixing ratio, for instance, SO2, DMS, and MSA for the productions of sulfate, NH3 and H4 plus for the productions of nitrate, as well as an SOA precursor for the productions of the second organic aerosols. So in all, depending on the options that you are using, GOCARD2G may add as many as 26 scalar variables that needs to be advected by the dynamical core. In addition to those fields, we also need to have the global distributions of OH and NO3 for other chemistry processes as well. So first results, we are validating GOCARD2G first without MPAS physics interactions, and we're starting to kind of also validate GOCARD2G with some physics interactions. So we initialized MPAS with the MERA2 GMI aerosol data coupled with GFS meteorological data for July 15th, 2019 at 12 UTC, which is one of the first time where we actually had the nitrate mass mixing ratio available for MERA2G in those three separate beams. So we run MPAS for a full month using the 60-kilometer mesh, and I'm going to show some results in terms of vertically integrated mass mixing ratio for a few of the aerosol species. Okay, can I have the next slide? Thank you. So the left two panels show the monthly mean, shows the sulfur dioxide SO2 initialized on July 15th of 2019, as well as on the right side, two panels for sulfate SO4. Also, the top two panels are at the initial time on July 15th, 2019. The bottom two panels are for the last day of the forecast. So the panels on the left-hand side show that shows that we have a maximum emissions of SO2 over the anthropogenic regions, like for instance over China. The bottom left panel shows that after a 30-day run, we do not see a lot of variations in the global distributions of SO2, although we do feed SO2 with anthropogenic emissions from CANs. On the right-hand side, we see an increase in sulfate from the bottom panel to the top panel, which results from the additions of the anthropogenic emissions, as well as the SO2 oxidations of SO2 to sulfate using the OH, DMS, and MSA aerosol species. Next slide. Thank you. Those 4 panels now show the global distributions of, as an example, another example of the brown carbon. The left 2 panels are for the hydrophobic aerosol mixing ratio. The right 2 panels are for the hydrophilic mixing ratios. The top panels are directly from the are obtained by initializing the brown carbon as 20% of the organic carbon distributions, since brown carbon is not yet available from the MERA2 GMI data. So we have maximum brown carbon, of course, over the areas of high emissions of biomass burning, for instance, Southern Africa, Alaska, South America. And we can see the increase in the hydrophobic version of brown carbon from the top panel to the bottom panel during the 30-day forecast. On the right-hand side, we can see an increase in the brown carbon in terms that comes from the conversions from hydrophobic to hydrophilic with a time lag of about, I think, 2.5 days, as well as the contributions of the horizontal and vertical advections with the dynamical core. Next slide. And finally, as a last example, I'm just showing the mineral dust global distributions for the first 2 spectral bin of the 5 bin distributions. So the top 2 panels shows that we have maximum mineral dust, of course, over Northern Africa for both bins, expanding into the Atlantic Ocean all the way to the Caribbean on the west side, and then expanding into over Saudi Arabia, the Persian Gulf, the Indian Ocean, and the desert regions north of the Himalayas. The bottom 2 panels shows for the simple emission dust of GNU that we are currently using in GOCART 2G. We have a decrease in the emission of mineral dust over Africa and the desert regions. If you look at the bottom right panel, then we have decrease in those emissions, although we do have emission dust on the western part of the Sahara Desert, as well as along the eastern coast of Saudi Arabia and the Persian Gulf and the Indian Ocean. So it seems, looking at all the other aerosol species, it seems that the implementations of GOCART 2G seems to be correctly done in MPAS A. And we're finishing to kind of validate the individual aerosol species using that 1-month simulation. Can I have the next slide, please? Thank you. So I want to say a few words about the productions of the second organic aerosols of SOA. So we know that SOA formed by gas to particle conversions, and we decided to implement the simple SOA scheme that is provided by GeoScam. So first, we need to have productions of what we call an SOA product precursor, which is also related to that VOC I was talking in the first slide. That SOAP is a function of CO emissions from anthropogenic and biomass sources, CO being an additional prognostic variable that is being added to MPAS as a prognostic variables. And it's also, the SOAP is also created as the functions of isoprene, monoterpene, and other terpene emissions from biogenic emissions. The second step is that there is an oxidation process of SOAP with OH to form SOA, with a default first over lifetime of 1 day, which is a parameterization that was developed by Otzix and Jimenez in 2011. And finally, the SOA production that is produced through that mechanism contributes to the hydrophilic organic carbon and brown carbon emission mixing ratio. Can I have the next slide? Thank you. So the right 2 panels now show global distributions of the organic carbon, the hydrophilic version of the organic carbon. The top panels is the last day of that 1-month model run with maximum organic carbon over Southern Africa, as well as over the well-known anthropogenic area of anthropogenic emissions, and including, of course, advections by the MPAS dynamical core. It is obtained with including the parameterizations of SOA turned on. The bottom panel is the difference in the same forecast, but now without running SOA. So we do not include SOA productions to the organic carbon. And you can see the difference plot simply shows the contributions of SOA to the total organic carbon over regions of biomass burning and anthropogenic emissions. Kind of the next slide. So now a few words about interaction with MPAS physics. As I said in an earlier slides, GoCard 2G has simple parameterizations of gravitational settling, dry depositions, and wet removal by the grid scale cloud microphysics. It doesn't include any parameterizations, for instance, of convective transport and wet scavenging by convections. So that's the first set of parameterizations that we use to kind of validate chemistry processes implemented in MPAS. So we have implemented and are currently validating the aerosol radiation interactions. So we are computing the aerosol optical properties using the RTMG lookup table provided by GoCard 2G. And then we are using those AOP as input to the long wave short-wave radiation codes. We also have including a mixing in a PBL and free troposphere for each aerosol species using MYNN, as well as using the dry deposition velocity, which is calculated on the GoCard 2G side using parameterizations from Wilczek et al. In 1986. And finally, we have also implemented the computations of the Thomson water-friendly and ice-friendly aerosols as the functions of the GoCard 2G aerosols for use in the Thomson cloud microphysics scheme, using that new options MP Thomson GoCard 2G, in which now the water-friendly and ice-friendly aerosols are diagnostic variables, while we retain the GoCard 2G aerosol species as prognostic variable. So the two vertical distribution, the two plots on the right-hand side shows the vertical distributions of the area amine, hydrophilic organic carbon, the top panel, and sulfate, the bottom panel, average over Southern Africa for the top panel, and Eastern China and China for the bottom panel, showing the difference in the vertical mixing of the aerosol species with and without MYNN. So the red, let's see, the blue vertical distributions is without the vertical mixing by the PBL scheme, and the red the red lines are for the vertical distributions of the same aerosol species now, including the mixing by MYNN. And you can see a very strong difference in that vertical distributions due to the lifting and mixing of the aerosol species from the PBL and into the free troposphere. So we're currently finishing to implement the convective transport and the wet scavenging of those aerosols in the NTITCA scheme, following earlier work that I've done with the GRAIL-FIDA scheme, using a fully implicit version of the convective transport, including wet scavenging. Can I have the last slide, please? So my future work, of course, is to continue to validate those long-term simulations, as I've shown in a few slides prior, with and with their interactions of MPAS physics, and continue to contribute to the data assimilations of the PACE aerosols using GoCard in MPAS GoCard JEDI. Thank you.
Thank you. We have time for one quick question. Are there any out there? Is there anything in virtual land?
There is one. On the slide where you show brown carbon, there are streak-like features in ER just north of Alaska in the figures showing the final time step. Any idea what is causing this?
I'm not sure if it's convections by the dynamical core or just a feature of the actual plotting routines. I've seen that you can see some of that in other aerosol species as well, or other hydrometeors. So I'm not sure, but I can look at it more details, of course.
Thank you. I think we'll move on to the next speaker. If I can get my phone to. So Pedro Jimenez is going to talk to us about an update on the coupling of behavior to the WRF model.
All right, thank you. So first of all, I would like to thank my collaborators, Anthony Islas, Dan Rosen, Maciej Dami, and Jimmy Dudia. And also, I would like to thank Maria Frediani, Michael Kabulich, and Katie Wilson, who have been actively developing the community fire behavior model. This is the outline of the presentation. I will first provide an overview of the model. We developed the model to provide a fire behavior model to NOAA's UFS model. And we based the developments in the WRF modules, and we on purpose follow the methods closely in order to check for consistencies between our implementation and the original WRF. And what I would like to highlight is the interoperability component that we bring with the community fire behavior model. Then I will move to specifics about the coupling to WRF. We have a couple already in WRF 2, and then provide some summary and future work. And our vision with the model is to make the model available to a variety of atmospheric hosts to foster collaborative development in order to increase our fundamental understanding of fire science, and especially to minimize the adverse impacts of wildland fires. This is how the fire behavior model works. In the middle here, you have the method that we use to track the location of the fire front. Is based on the level set method. This is a consolidated methodology to track the location of interfaces, and we need to resolve a partial differential equation. On the left, you see that we have parameterized the rate of spread, and this is a function of fuel characteristics, elevation, and other near surface atmospheric variables. So we know where the fire front is located with the level set, and we know the rate of spread, so we are able to advance the fire front, and at the pass of the front, we ignite new cells. And this heat release and moisture release is parameterized that feed back the atmosphere, and in this way, we have a couple fire atmospheric system. We also have a tracer of smoke. This is an overview of the model. As I mentioned, we developed the model to provide a fire behavior model to NOAA's UFS, and is based on WRF version 4.33. And the coupling with the atmosphere is done via the Air System Modeling Framework, ESMF libraries. This is a standard way to do the coupling in air system models and in UFS in particular. And this requires having the model implemented in what is called a National Unified Operational Prediction Capability of NUOPSI component. Essentially, is we isolate the fire code in this case, or any component in these NUOPSIs. And we need to provide some communication with other components, and that's done with a lightweight file that we refer to as the CAP. And this CAP is responsible to call an initialization subroutine of the component, an advanced subroutine of the component. And also it defines the grid and the variables that are able to exchange with other components. Then when we have the fire behavior implemented as an NUOPSI, we can couple it to other components to build an air system model. And in this case, we just need to couple the atmosphere with the fire in this first implementation. The model can be run offline too, and it can read in the atmospheric state from existing work simulation. We developed this capability to test for consistency of our implementation, but it could be also be useful for sensitivity studies. More importantly, we have the online version that is coupled to atmospheric host. We have it in UFS and WRF. And also we have an idealized component where we can prescribe the winds and atmospheric variables and the fuels via name list. I will show you an example of that one too. These are some details about how we reorganize the code and we enhance it to create the standalone model that I mentioned. And in the process, we also improve the reliability of the code. The code is self-documented, so it should be or shouldn't be difficult for you. You go to the code and you should be able to understand what is being done. We impose consistent formats across modules, and we had to remove atmospheric dependencies to isolate the fire code in this NOAA component. Some of the process we implemented parameterizations that are controlled via the name list, and the parameterizations are implemented as abstract derived types that are extended. And our idea is these are components that we may want to revisit to go beyond what is already implemented. These are the rate of spread, the fuel model, and the fuel moisture content model. We have also removed some checks and prints to improve performance, and the code conforms the Fortran 2008 standard. We have an expensive automatic test available, so when you are doing development, you can quickly run these checks to make sure you reproduce a known solution, so you don't introduce any bug, or you minimize the time you introduce them. We have also regression tests in the GitHub repository, and these tests are triggered during the night and also in pull requests. I'm going to show you some results and focusing in the consistency with the original model. This is an example, as I mentioned, with an analyzed case. We ignite the fire on the left as a line, and the winds are constant, homogeneous from the west or from left to right. And the fuels are constant too. We run the simulation for a certain amount of time, so we know where the fire front should be located. And that's what I marked there as the theoretical solution. And what you see here in the colors are different simulations using different methods to resolve the level set equation, the partial differential equation. And what you see here is that when we increase the accuracy of the numerical methods, we get closer and closer to the theoretical solution. We did this exercise with Warfire too, and well, it's reconforting to see that we are able to reproduce what is expected. This is the coupling to UFS, and here it will highlight how to use the model as a NOAA component. On the right, you see a very simplified diagram of UFS, and you see the different components. On the right, you see the ocean, and highlighted are the atmosphere, and in the bottom is the fire model, the community fire behavior model, and you see the arrows that are exchanging. Those are the connector interchanges verbal. This is a zoom-in version on the left, where you can see some highlights of the code, and here you see the directories, the folders that we have in the fire behavior model. You see the driver. This is the directory where we have the initialization and the advanced routines that are used by the CAP. Then we have a shared directory where we have some miscellaneous of subroutines and modules. Then a dedicated folder with code for writing the input and output, and another with the state of the model, defines the state of the fire state. And then in the physics, we have the fire methods and the level set. And the code is publicly available. Here is a link to the repository. So how does it work? Here is an example of a simulation where we run Warfire, UFS coupled to the community fire behavior model in blue, Warfire in black, and in green is the offline version of the model, so driven offline by reading Warf data. This is a simulation for the Cameron Peak fire in Colorado, and you see how the perimeter, there is consistency in the evolution of the perimeters, which is what we would like to see here. That highlighted on the left. On the top is the time series of the burn area. You see that in both WRF and UFS have the same evolution, and that's of course because on the bottom you see the winds that are driving the fire. They are closely aligned, and this is on purpose. We have very similar configuration of the two models to check for this consistency. This is implemented as a new NOAA component. Here I'm going to switch now to the coupling with WRF. And the code is available in the WRF official repository in this branch, the 5CFBM integration branch. The compilation is automatic, and you have to use CMake at this point. And this will fetch the community-fied behavior model, which will be available as a submodule in the physics directory. We have the model couple in two ways. The caveat we have right now is we don't have parallelization yet. We're working on that, but for the moment, it only runs in one CPU. And we are using the WRF infrastructure to define the fire grid and refine the atmospheric grid to have a refined fire grid, high resolution. There are some characteristics that are managed by the fire model, like the time step could be independent from the atmosphere, and it also managed to write in its own output in the fire grid. The fire state and the name list are derived types, and they are included in the WRF domain derived type. And in this way, by having these two file components inside of the main WRF derived type, we're able to move all the file code and methods around the WRF model. It's very orthogonal coupling. There are essentially three parts of the code where the models interact. There is a first one that it reads the name list. You need to specify a new name list for the fire. And the second one is initializing the fire state. So we initialize the name list derived type, the fire state derived type, and then we use them to advance the fire state in the third point. So this is some screenshot of the code. To run the model, you need to set up in the WRF fire name list, you need to set ifire equals 1. And then here in the top left, you see the portion of the code where we are reading the name list in module configure, is the name list.cfbm. Then there is this portion of the code in start EM, where we initialize the fire state. There are some statement before this call to derive some of the verbs that I use are passed here as arguments. And then one on the bottom is to advance the state, where we pass these two derived types. And then here on the right, on the top right, you see that we also have to introduce some changes in the registry, not too many. And these are essentially the four main places where we introduce changes. Here you see on the animation is some changes we have to do, well, not animation, the figure, some changes we have to do to include the aerosol optical depth. For the first time, we are able to output the aerosol optical depth of the smoke, which is mimicking the PM 2.5. And this is an example of the kind of things we are doing now, going beyond the methods available in WRF-Fire. This is a consistency check. We run a simulation with WRF-Fire and WRF coupled to CFBM. In this case, we start the fire as a point ignition at the location of the start. And we run the model for 26 hours. And at the end of the simulation, here you can see the two perimeters. In black, the one from WRF-Fire, and in red, the one from WRF coupled to CFBM. And you can see that after such a long time of the simulation, there is consistency on the simulated fire perimeters. There is a documentation available, the user guide, and here is the link of the website with the documentation. So far is mainly focusing the coupling with UFS, but it's our intention to extend it and to provide some information about the coupling with WRF. This brings me to my last slide, the summary and future work. We have the community-fied behavioral model, which has been designed to facilitate interoperability with atmospheric models. This is done taking advantage of the ESMF libraries. And in particular, we have implemented the model as a NOAA component, and the code is publicly available. This is the website of the Community 5 Behavior Model. We have coupled it to UFS, and you can do also automatic simulation using the short range weather app. And we have also coupled it to WRF, and we have seen, and that's what I saw in the presentation, consistency between CFBM run offline or coupled to UFS or WRF and the original implementation in WRFire. And this is the starting point to improve the realism of the simulation going beyond the current methods in WRFire. Show you something that related to the aerosols that we're looking. We are mainly working now in the parallelization of the code. We are going to start with OpenMP, and because it's easier, and then MPI should follow. And then highlight that coupling to MPAS shouldn't be difficult once MPAS is available as a NOAA component when it's integrated in the UFS, and will be love to have the coupling with MPAS in the future. Thank you. I'll take questions if there is time.
Thank you. Questions from the audience here? Relatively quiet the last few talks. Kelly, do we have anything out in virtual land?
Yes, there's a question that asks, can AI models realistically replace WRF and MPAS in weather prediction given their reliance on fundamental physical laws and the challenge of generalizing to untrained regions and time periods?
I'm not quite sure that's relevant to this talk. So I'll take it and just say we don't know.
So there is one here at the bottom.
So there's another question that might be something you'd be able to answer. Are there any, oh, wait, I'm looking at the wrong one.
There's one that says, do I need an implementation of WRF to run CFBM?
Yes.
So the answer is, you just need to download WRF, the official repository. You need to go into the branch that I showed in the slide. So you need to check out that branch, and then you need to compile with CMake. And once you compile with CMake, you will have the code compiled in a way that fetches the CFBM code, and you will be able to run it. We will provide more details of the specifics of what I said in the website with the documentation, so everybody will be able to do it. It's not very difficult. It's only a few set of commands.
Jan Mangal. Very nice talk and call.
Thank you. Yeah.
I was wondering if it's running as an ESMF interface component.
Called what?
Well, okay, so you are using ESMF for coupling. Does it know about registry? I thought you mentioned registry.
For WRF?
No, the fire model. Does the fire model know about WRF registry?
Yes, yes.
How?
For
part of ESMF
interface. Well, I didn't highlight that. Yeah, for the coupling with WRF, we are not based on the ESMF. We are using the functionality we had to develop for the ESMF, the modularity. So this initialize and advanced routines, and the code that I put there is where we have to put how we modify WRF to call these subroutines. So short answer, no, is not using NOAA for WRF. So you have to use the register. You can still use the register.
Thank you.
Thank you. The next talk is virtual. It's going to be given by Jacqueline Pereira. Hi, Jacqueline. And she's going to talk to us about integration of a wildfire smoke plume rise scheme into MPAS-A and a case study on the 2019 Williams Flats fire.
Yes, hello. Can all you hear me?
Yes, we can hear you.
Okay, and can you see my share screen?
Yes, we see your slide deck and we see your slides. Thank you.
Okay, thank you. Thank you, Bill. Hello, everyone. My name is Jaqueline Pereira. I am a PhD student at the National Institute for Space Research in Brazil. And I have spent a couple of months last year visiting NCAR to implementing MPAS, a plumerize scheme, and also a fire module for emissions. So I would like to begin, thank you. I would like to begin to thank you, acknowledging a lot of people that have been contributing to this work, especially my advisors, so Saul Freitas, Mary Barth, and also Bill Scamrock, and a lot of many people at the NCube and also at the ACOM Lab that have been contributing to this work. So it's a pleasure to be here today to share the current status of this research. So just a brief overview, wildfire smoke is one of the most significant concerns of human and environmental health due to its substantial implications on a diverse set of Earth system processes, including Earth's radiation budget, biochemical cycling, atmospheric chemistry, as well on air quality. So when we have a fire occurring on the vegetation, a convection process is induced by intense heat released by the fire, which generate a positive buoyance that transport the emissions upwards. So the atmospheric and also the burning conditions can determine the altitude at which this plume will go reach the atmosphere, which we call the plume injection height. So because of that, this plume injection height can vary a lot in the atmosphere. So the ability of atmospheric models to accurately simulate and forecast the smoke transport is critically dependent on the plume injection height. So thinking about that, the main goal of my PhD research is provide the state of science of wildfire aerosol module for the model for ocean, land, atmosphere prediction Earth system model, which is called MONAN, which is the next generation of Earth system numerical modeling for South America and the Caribbean. And this model is being developed by the community and it's led by the INC institution. So right now we need to include an aerosol model and also wildfire aerosol emission fields and their effects into the physical formulation of the MPAS-A, which is the atmospheric driver for the MONAN model. So the current research stage is implement an inline smoke plumerized model to estimate the plume injection height. So this work is the first implementation of the Freitas plumerized model algorithm in the MPAS-A standalone version. So what is the plumerized model? The plumerized model that we have been implementing is the parametrization developed by Freitas and colleagues in 2007, which was updated in 2011, that estimate the smoke plume injection height. So this model consists on a one-dimensional cloud resolve model that solves the equations for vertical momentum, the first law of the thermodynamics, and also the equations for water phases. So this model has his own microphysics, his own advection, and integrates the plume along the layers of the atmosphere to give us the plume injection height. So the plume top height is determined by the height for which the vertical velocity of the in-plume air is less than 1 meter per second, which means the level of neutral buoyancy. So the plumerized model needs as input data the active fire size and also the fire intensity, both retrieved by satellite data, and also information from the atmospheric host model, in this case the MPAS, which is the thermodynamic conditions such as temperature, pressure, moisture, and wind velocity, and also the land cover information. So here is a diagram for the model organization that we have right now. In blue is the included modules, and in yellow is the modified modules. So we have implemented the plumerized model standalone version inside the MPAS model standalone version, in the version 8.2.1. So here we include the plumerize itself, the model itself, inside the physics WRFs, inside the WRF physics of the MPAS directory. Also, we included a module to calculate the emissions, and also a module to do the dry mixing of these emissions in the PBL. And here I just left in yellow the other modules that we need to change to do this implementation. So this methodology includes the plumb-rise model in each column of the three-dimensional MPAS-A. So here is another diagram that I'm going to explain how this implementation is work inside the model. So for each time step, for each grid cell with an active fire, the MPAS-A is going to feed the plumb-rise model with the environmental conditions and the land cover type. So the land cover type right now is come from the IGBP modes NOAA and have 20 land cover types, but the plumb-rise model grouped those types into 4 categories, which is tropical forest, boreal forest, savanna, and grassland. So also for each time step, for every grid cell with an active fire, we need to feed the plumb-rise model with the input data, which is the emissions flux and also the active fire sites. And the plumb-rise model code has capabilities to work with FRP data, but right now we are using the prescribed heat flux values that's dependent on the vegetation category. So those can generate the boundary conditions for the plumb-rise model starts to run. So the vertical extent of the plume is resolved explicitly, defining the lower and the upper injection height for the emissions. Then the range of the final rise of the plume are returned to the host model and are taken into account into the source emission field, releasing the emissions during the flame phase equally between these two levels, and the emissions for the smoldering phase is released on the surface. So after that, this mixing ratio tendency is updated inside the module boundary layer mix scalars that we have also added to the model. And then automatically the tracer is updated in the advection scheme. So for this presentation today and this step of the research, we are looking at the Williams-Flex fire case. So we investigate the plume injection height. We focus on the fraction of smoke release in the flaming phase that is related to the plume rise model, along with the representation of downwind PM 2.5 distributions. And this PM 2.5 distributions right now is just treated as an inert smoke tracer. And we are looking at the Williams-Flex fire case that occurred in August 2019 in Washington State. So this event was ignited by lightning strikes on August 2, and the fire going on until the August 10, when we have a rain event. In the Colville Reservation in Washington State, the total burned area was 180 square kilometers, and the biomass burned was shortgrass, tall brush, timber, and also a coniferous overstory. And this case, it was chosen for 2 reasons. There was a field campaign, the Fire Execute, that sampled data. And also on August 8, we have a pyrocumulonimbus formation in this event. So here is the configuration for the simulation that we are running. So we are running the standard configuration of the version 8.2.1 of MPAS with all the implementations for plume rise. From August 2 to August 10, so 8 days of simulations. We are testing right now 2 different data for the initial model, so GFS analysis and the ERA5 analysis. And we are using the 60 kilometers resolution with 55 vertical layers, and also the mesoscale reference for the physics suites. So regarding the plumerized model input data, we need the emissions flux and also the active fire size interpolated to the MPAS grid. So to do that, we are using the fin emissions with the fin inventory emissions, which are provided in lat-long grid. And then we interpolated that using the ESMF capabilities with a Python tool to interpolate those data to the MPAS grid. And then we have the emissions flux and also the burned area in the 60 kilometers resolution. So here is just two figures to illustrate that. And here is are the preliminary results. So we are looking at the plume injections. So this figure, we can see here the days of the simulation from August 2 to August 10. And here we can see the plume rise injection height in meters above surface. In orange are the simulations with the WRF data, and in blue are the simulations with the GFS. And those data are shown for the Williams Flats fire grid cell inside the MPAS simulations that is marked here by a black star. So in this grid cell here, the vegetation category was classified just as grassland areas. So it's not accounting the forest areas that we have in the real event. And for plume rising grass, in the plume rise, fires burning grassland areas just have one value for the heat flux, which is 3.3. So because of that, the lower and the upper injection height are the same. So here, the first pattern that we can observe is the strong diurnal variation. So the simulated plume injection height presented a strong diurnal variation with maximum values occurring around 0 UTC, which means 5 p.m. local time of the day before. So right now, we don't have the fire diurnal cycle inside the model. So this pattern is basically driven by the atmospheric conditions, especially the PBL cycle. So comparing the injection height values at 0 UTC, there was a slight increase along the simulations day. So around 1 kilometer from August 4 to August 7. And on the August 8, we can see stronger free through projection injections here, around 7 kilometers and 8.5 kilometers. So on the subsequent day of the strong injections, we can see that the model comes down again for the injection height. So right now we are trying to understand this pattern, and some behavior can be related to the model sensibility to the atmospheric conditions. So when we look to the atmospheric thermodynamics for the August 8 here and August 8 here for GFS and R5, and here August 9 for GFS and R5, we can see that this pattern can be related to a deeper boundary layer and formation of convective clouds on August 8 in both model simulations. And on August 9, the simulation with R5 presented a boundary layer closer to the surface compared to the GFS data. So this can explain a little bit of the pattern that we have here for the plume injection height, but we also need to check the sensibility to the model, the sensibility of the model to the burned area, for example. Here are the preliminary results for the simulated PM 2.5 that was treated like a inert tracer. So here we can see the black star marking the Williams-Flats flyer grid cell, and here are the PM 2.5 in concentration. comes from 0 to 40 micrograms per microscope. So we can see here high concentration near the surface, which decrease with altitude. And here's the surface. Here's around 2 kilometers. Here's around 7 kilometers, and here's 8.5 kilometers. So here around 6.8 kilometers, you can see concentration shows a significant increase comparable to surface values. It's higher than the surface values. And this is probably because of the plume injection height that allocated the plume in this altitude. See here, we can see the ERA5 experiment. So it's the same analysis, but now for the ERA5. And we can see that we have higher concentration near the surface that decrease with the altitude due to the mixing the PBL. And also we can see that here around 8.5 kilometers, we have some concentrations of the PM2.5, which also is responding to the plume injection height behavior. So when we compare the two experiments, we can see that the simulations with ERA5 produced higher PM2.5 concentrations. Here it's come from 0 to 70, and here is 0 from 0 to 40. So to better understand the causes of this difference, we are going to analyze later the boundary layer, the wind speed, the 2-meter temperature, and also the formation of water, cloud water. So additionally, the ERA5 and GFS present different PM2.5 concentrations at the same vertical levels, which corroborate to the plume injection height, which is different on this day here for August 8 for each experiment. And this can lead to different long-range transport patterns for each one of the experiments. So we're also gonna look at this analysis in the future. So here we can conclude that this implementation is an advance and improved wildfire smoke forecasting. And also the model can capture the key features of plume injection height, and also for the emissions tracers. In that case, is the PM2.5. So now we are working on carry out the simulations on a fine resolution, so 30 kilometers and 15 kilometers resolution. Also, we are looking at the sensitivity to the active fire size, and we are going to evaluate this data with the Fire Execute Field campaign. And also, we have a team working on the prepare the Brazilian emissions inventory for fires into the MPAS grid. And in the future, we are going to include the diurnal cycle in the plumerized model, and also bring this implementation to the GoCart MPAS version. So thank you.
Okay, I think we have time for one quick question. Do we have one from the audience here?
Hi, Jacqueline. Thanks for the nice talk. One quick question. Although I know you listed on the ongoing work, were you able to compare your modeled plume injection height with the Fire XAQ dial measurement? And if so, did you see intrinsic overestimation from the Freitas polymerized algorithm? And one last quick question is, are you also plan to look at the adjacent fire, like horsefly fire, in the same episode, Fire XAQ campaign?
Okay, thank you for the question. Yes, we start the evaluation with the Fire Execute Field campaign. So right now we observed that the plume injection height simulated by the model have a similar pattern that the observed data. Otherwise, the model is simulating the pyrocumulonimbus on the day before. So the strong free tropospheric injection was on August 9, 0 UTC, and the model is simulating on the August 8. So we are going to move on to the 30 kilometers and the 15 kilometers to see if the resolution can respond better to this behavior. And I'm sorry, can you repeat your second question?
Are you also planning to look at the adjacent fire event, like a horsefly fire in Montana?
Okay, thank you. Right now, we don't have plans to move to this specific event because we still need to working more on the implementations on the code. So I don't know if we're going to have time, but I will be happy if we have time to move to this another case.
Okay, thank you, Jacqueline.
Thank you.
The final talk of the morning belongs to Mary Barth, and she's going to talk to us about towards global convection permitting simulations in an Earth system model.
Thank you, Bill. Yes, so thanks for sticking around to the last talk before lunch. I hope you find it entertaining enough to keep you here. As the leader of the System for Integrated Modeling of the Atmosphere project, I'm really mostly a spokesperson. My co-authors, Adam Harrington and Brian Dobbins, really did most of the work that I'm going to be showing you here. Let's see if this works. Good. So it's now possible to perform global convective permitting CAM simulations within the Community Earth System Model, CESM. And that happened through a collaboration between the SEMA project, the CESM project, and Earthworks, which is an NSF-funded project led by Colorado State University. There are many, many people who helped out to make this possible. In addition to Adam and Brian, you can see a number of teams that contributed to making this possible. The CSM version 3 configuration is listed here. It's using the MPAS grid mesh, which is running at global 3.75 kilometer grid mesh. It has 58 vertical levels to about a 40-kilometer model top. It's utilizing the MPAS non-hydrostatic dynamical core and CAM7 physics. But the CAM7 physics have been modified for mesoscale applications. Those modifications primarily address the cloud fraction, switching it to a 0 or 1 cloud fraction in both the cloud physics and in the macro physics. And that's can be seen here in the figure in the bottom right, where it's showing a squall line case that was examined. On the left panel are the observations from the NexRad radar of the squall line. In the middle panel are results using CAM7 physics without any modifications. You get convection, but it really doesn't look like the squall line. And then in the right panel, you see the results when you do have the modifications, primarily with this cloud fraction effect. And you see a much more realistic squall line. And I think Bill might have showed you this really even a couple of years ago. So this is really nice to have those improvements to the model. What's really unique is that the CESM model also includes an aerosol model, the modal aerosol model with the prescribed chemistry. And so now we're able to not only have the aerosol representation, but you have the interactions of the aerosols with both the radiation and with the cloud physics. The configuration has an interactive land model running and a prescribed ocean model and such. So there were several technical challenges, and I just want to highlight and acknowledge some of the work that made this possible. One of the biggest challenges that happened was a scalability issue that affected the initialization timing of running the model. In the initialization, the state reconcile part of ESMF is called multiple times. And it turned out as the number of processors were increased, the time it took for the state reconcile call took longer and longer. And you can see that in the blue line here in the figure, where the number of processors is on the x-axis, timing on the y-axis. So Brian worked a quick workaround, but really the ESMF team took a deeper dive into this and figured out how to fix it. And now they have what's resulting in the red line, where you have a near zero timing for doing these calls to state reconcile, and there's no degradation of that timing with the number of processors. Another place where improvements were made was with the input and output part. The CGD software engineering team took a look at the IO and discovered that you could reorder the variables and get a 4 times improvement in performance of IO. They also ran into a 32-bit Q-sort issue. If you do the math on number of grid cells for the simulation, it exceeds 2.4 billion grid cells. That exceeds the 2 to the 31st compute threshold for 32-bit signed integers. And the CGD software engineering team found an issue that did happen in comparing numbers and had to deal and fix this issue as well. So that resulted in improving the writing of restart files to be less than 5 minutes instead of much longer. And then lastly, I want to just acknowledge all the science fixes and tunings. One of the recent examples that we came across was an incorrect pressure level at the surface for certain situations being fixed. But there were a number of other physics and errors fixes to physics and aerosols that were addressed. And I just want to highlight that because it really took a team effort of working with CGD, MCube, and ACOM to get these fixes put into place. Okay, so what the CESM configuration is being run on is a DIAMOND simulation. And the DIAMOND project provides a framework for the intercomparison of global storm resolving models. There have been 3 phases so far. The DIAMOND 1 phase, or this is a 40-day summer simulation. The DIAMOND 2 phase is a 40-day winter simulation. And the DIAMOND 3 phase is a 1-year annual simulation. The CESM run, or MPAS run, is complete for the summer simulation. 30 of the 40 days are finished for the winter configuration. And then they're planning to do the annual simulation later this year. On the bottom, I list how the model is initialized with AR5 meteorology, the whole atmosphere community climate model output for aerosols and prescribed oxidant fields, anthropogenic emissions, and land initialization, which is based on more of a climatology. Okay, so let's look at a few results. So now we can get to the pretty pictures. On the left is showing the cloud water path over the Pacific region. And on the right is shown the 10-meter wind speed of that same area. You can see in the Eastern Pacific, a tropical cyclone that's formed. In the Western Pacific, is the beginnings of a tropical cyclone. You can see a lot of fine features. So let's zoom into that Western Pacific area and look at that a little more closely. And you can see in that wind speed that there are regions that kind of mimic convective outflows, and those are aligned with cold pools that you can see in the potential temperature at the lowest model level. This is probably the first time CESM has resolved a cold pool, so that's kind of exciting for the climate community. Okay. There's only been a little bit of evaluation done because these are really results coming hot off the press. Here's a comparison of the August cloud radiative forcing between MPAS and the series observations. What you can see from these maps here, series is the left panel, MPAS is the right panel, that really the brightness of the clouds by the model is not nearly as bright as what we see in the observations. So that needs to be addressed. And also that the marine stratocumulus layers are a little bit different are not matching observations as well either. So besides the cloud brightness factor, there's also the extent of the cloud deck. It's not reaching quite far south as you see in the observation. So you can see a lot of cloud down here in the series, but not nearly as much in the cloud reflectivity in the CAM MPAS simulations. So there are a lot of other things that could be dug into with, this is the usual halfway through the talk, it stops advancing. So if I could get some help, please, with advancing. So there's a lot of other things you could do with clouds and the meteorology, but coming from a place where I study chemistry and aerosols, I wanted to show a few results on the aerosols, looking at dust, sea salt, and sulfate. And could you please advance the slide? Thank you. Here I'm showing the dust aerosol optical depth. I just want to remind you that dust emissions are calculated online. It's based on the wind speed, land use, and other characteristics of the model simulation. Shown on the left are the results from the CESM run of the dust aerosol optical depth. And on the right is really a climatology of the annual mean from the MIDAS reanalysis. And so what we're seeing is that we have a reasonable spatial distribution of the dust compared to the climatology. It was also compared to a 1 degree CESM baseline run for a 10-year period. And what we learned there is that the dust concentrations are probably about 30% too high compared to that baseline simulation. If I jump over to sea salt, this is sea salt concentration in the lowest model level. And again, sea salt emissions are predicted online. It's based on the wind speed. The levels are actually lower than that climatology CESM run that was mentioned before. And that's actually due to Adam changing the scaling factor in the name list. So it's not something wrong with the model. It's actually something good with the model, because when you compare the levels of the sea salt concentration to the range of concentrations in the AERCOM model in comparison, that they are right in the middle. And I think it makes my cohort, Danny Lung, happier to see those kinds of sea salt levels. I also want to show you sulfate concentrations in the lowest model level. Sulfate's mostly coming from anthropogenic emissions, but it does have some sources from oceanic emissions and an oxidation of dimethyl sulfide. What we see here in these results is that the spatial pattern is as expected, with high values over Eastern Asia, South Asia, the Middle East, and then also over the North African area related partly to Europe. We really haven't had a chance to do any evaluation to either model other model results or to measurements, and this is our next steps. And I'm really excited by this because there is actually an opportunity to compare these kind of results to an aircraft field deployment that occurred during the same time of this Diamond summer simulation. That's shown in the bottom right, where the atmospheric tomography mission flew north to south over the Pacific and south to north over the Atlantic in September 2016. So I'm going to finish with this slide here, mentioning the outlook for global convective permitting simulations in an Earth system model. These are really words that I showed you earlier, but I really want to emphasize that middle bullet point about transitioning to evaluating and assessing the realism of the extreme precipitation, the tropical cyclones, the convectively generated gravity waves, and the aerosol distributions. And I will end there and be happy to take any questions. Thank you.
Questions?
A good talk, Mary. I think that your radiation results to me suggest that going to strict 0-1 binary cloud fraction is probably not the right thing to do for 3.75 5 kilometers or whatever, because I mean, we've been modeling at 3 kilometers for quite some time, and we
Right.
know we need a full spectrum of cloud fraction still, even down to sub 3 kilometers.
Yeah, so that's kind of a conundrum, right? About, when you look at something like a squall line where you're looking at the structure of convection and precipitation, and you're looking at global cloud amounts, what is going to end up being the right approach? I don't have the answer. I don't know if you have any comments on that, Bill.
I don't have the answer either. Although if you go back to the cloud fractions that are produced by Club, which are typically used in the microphysics here, you get that middle result for the squall line if you saw it, and you don't get cold pools. The lines don't look like lines. The convection is really messed up. So,
Right, but there's got to be something in between though, right? I mean, you could still have some type of cloud fraction that's just not as aggressive getting into the subsaturated range. I think that.
but perhaps that's a good thing to talk about over beers this evening.
Yeah, sure.
Okay.
Okay, we got a date.
Rosie?
Very cool stuff, Mary. I couldn't help but notice that there is essentially no ITCC. I saw it on the Cloudwater path as well as on the series. So I'm curious if there are any plans to look at what the physics are doing over the tropical oceans.
Yeah, that's a great question. You want to help us? No, we have, right, these are all brand new results, so I don't know what the thoughts are in addressing the ITCC yet, but I'll follow up on that.
Okay, thanks.
Thanks. There is one question here asking about the model top height. Yeah, so it says, I was a little surprised about the model top at 40-kilometer altitude. Was there a reason for setting it so high in the stratosphere? So the quick answer is that this is the low top version of the CESM. So they want to get into the stratosphere. So you have that interaction between stratosphere and troposphere, especially for longer multi-year simulations where that becomes important. Certainly the climate group wants to have even higher simulations, model tops, so you can look at the middle atmosphere and its eventual interactions with the troposphere as well.
Okay, thank you, Mary. We're at lunch. Thank all our speakers again, yes. We're at lunch. Lunch is right outside here.
Hey. Okay, let's get started. 1 minute, 1 o'clock. Okay, so welcome back. This data simulation session. We have 6 talks, each have 15 minutes. Hopefully everyone can keep your time, maybe leave 2 minutes or 1 minute for the question. This remote control, there are 3 patterns. Okay, if you want to do the this pointer, there is a pointer, so you can point just to the screen. Make people easier to see your figures. So the first speaker is the Alberto Ortolani from Italy.
Hello to everyone. Thank you for the opportunity, and I have to apologize for the state of my voice. I've probably lost in the travel from Italy. And anyway, I will do my best. I have to say that I'm not going about achievements, but work in progress in this talk of different things made by different persons listed here, and all working totally or partially at the National Research Council of Italy. But some of the activities are already, let's say, are developed with a broader group, which involve also some universities, especially the University of Bologna and of the Basilicata. Just for your information, not especially within Llama Consortium, we have a long experience with WRF in the sense that more than 20 years that we use WRFs, not only for research, but also for operational objectives, because Llama Consortium has an operational duty in Tuscany. And at present, we are in the process of installing a new operational chain based on WRF in the Italian Agency for Meteorology, named Italia Meteo. And it will be one of the three reference, let's say, forecast system of this Italian, let's say, not newborn, but that's going to be operational from this year, essentially, of Italy. So this gives the measure of the importance of work for us, and so of the work that here at NCAR you are doing. But we are not speaking about past achievements, but about the future. So what is Forum? Forum is the future satellite mission, is the European Space Agency 9th Explorer mission, whose main goals are about climate. So let's say is focused on, let's say, measuring parameters of climate interest and related to climate feedback and to reduce climate uncertainties in climate projections. But as you can see here, that is, Forum is going to cover for the first time with high resolution a spectrum up to the very end of the far infrared, and an area which, let's say, cover about 40% of the Earth emission budget, never systematically measured before, and is going to fly in tandem with the YASI new generation sensor. Forum is going to be launched at the end of 2027, more probably at the beginning of 2028. And but of course, even if it's a mission related to climate, it's going to bring a lot of information potentially of interest or relevant, I mean, in meteorology, because of, let's say, the relationship of this spectrum with the temperature profile, with water vapor profile, and also, let's say, cloud, and especially cirrus clouds, so, and also some other things related to, let's say, the emission of surface were clearly visible. The activities I'm going to speak are developed within especially two projects. One is MC Forum. MC stands for Meteo and Climate Exploitation of Forum, funded by the Italian Space Agency. And the second one is the Hard Moon Mars project, which is project funded by the National Recovery and Resilience Plan. So this, let's say, initiatives that followed the COVID pandemic. And I mean, this project has a broader, let's say, objective, but for what concerns the part related to the Earth, is still focused for a large part on Forum, because I mean, there is a sort of sensor which be an analogous of Forum designed to be, let's say, installed over the moon for observing the Earth from the moon. So from this point of view, I mean, there is the interest to understand on which extent Forum is able to provide information also relevant for meteorology. One of the first things that we are doing, we start doing, is to, let's say, evaluate something about, I mean, the capability of Forum of providing additional information in some cases. And we start from, let's say, processing ECN WRF ensemble forecasts. In fact, I mean, we assume in a certain way that the uncertainty of the atmospheric state at the moment is essentially contained by the ensemble spreads, especially at the beginning of the ensemble simulation, so at the time zero. And so from this point of view, the interest is to say, is able for Forum to make observation that can, in a certain way, change the probability of the different ensemble forecast members. And from this point of view, to address this issue, we have, let's say, extract some ensemble profiles from the footprint of Forum, let's say, simulated, of course, with an orbit here along Italy. This is our origin place. And from these profiles, we have built an ensemble of, spectra. Of course, let's say, using these profiles, processing these profiles with a radiative transfer code, and then, convolving with the forum instrument response, and eventually adding noise. But let us focus on two things that I'm going to show. So the standard deviation of this ensemble spectra and the spread intended like the difference of the higher and the lower value in the spectra for each channel. So here, this is not a spectrum, but this, let's say, is the picture of these parameters that we have to, let's say, compare with the instrument error of forum, which is this line blue that you can see here. Okay, and so the idea is that if this spread, and moreover, especially if the standard deviation is higher than the instrument error, when I make an observation, I can distinguish between one member and the other. And so from this point of view, I think that forum is going to have to bring information. Okay, so have a look to some examples. These are two footprints. This one is, let's say, the worst things we have found, and this one, the best one. In this case, as you can see, the standard deviation is almost always under, except in this place, the instrument error, but the spread not. And of course, if we move 6 hours later, the spread and also the standard deviation increases. So from this point of view, an observation could bring information and changing the probability of the members. On the bottom panel, on the contrary, you see that there are some part of the spectrum which are already, let's say, here are individuated by the continuous line circles, sorry, which are where we have the standard deviation over the instrument error. But anyway, we have the ensemble spread that in several places is over this error. So from this point of view, this is a motivation to say, okay, if in just one case, and this is a clear sky case, this happened, we can imagine that we can find several other conditions where this really happened. And why we are clear sky? Because, for the moment, let's say, AC and WRF provide not the microphysical information that are necessary to process these kind of things in our sky condition. We are ready to do it, but we have in the process of understanding with AC and WRF how to get these values when they are simulated before they cancel, because they are not contained in stored and released for common use. Okay, so this is one of the things we are doing, and we want to extend to other situations. The other one is to going on with making observing system simulation experiment. I don't want to let's say, speak of this kind of things to you, because for sure you know this better than me. But what we want to do in this optics is to use not only the sound radiative transfer code, which is RTTOV, but also I don't want to say a new code because it's sound this one too, but another code, which is the Sigma Yasi forum, which has specifically developed to cover the far infrared part of the spectrum, developed by an Italian group of the two universities I mentioned at the beginning, and that has been extensively used in the implementation of the forum mission, and also, for example, for the end-to-end simulator. So we would like to understand how to build an observational operator with this transfer, radiative transfer code. And another, let's say, line of activity we are following is to reduce the lines available in the forum spectrum, because forum is going to provide more than 5,000 spectral channels. And of course, not all these channels are really relevant for meteorological reasons. And so, of course, we want to select the more informative channels about, let's say, bring information about air temperature, surface temperature, water vapor content, and maybe less on gases types that are not variable in an atmospheric model. So, and in addition, we don't want to select lines, channels that are looking very high in the atmosphere, too high with respect to what is really of interest in atmospheric modeling. So from this point of view, this last information can be, let's say, obtained by looking at the weighting functions, while, the other aspect is to select channels which at the same time has the less correlation as possible. So we don't want high correlated channels, and the algorithm we are testing is the Macmillan and Goldberg algorithm. If you want details, I can say maybe offline later. And the test we are doing is with, for the moment, clear sky and 80, let's say, reference profiles. And for example, this is one of the results where, we put different tolerance. It means different level of correlation, and so selecting different numbers of channels, and then looking at the information that we miss on this aspect in order to understand, let's say, what we gain from the point of view of the assimilation, let's say, velocity and simplicity, and what we miss about the precision and about the channels. So let's say another aspect is still related to speeding up the observation operator, is to build an artificial intelligence-based simulator of Sigma-Yasi forum. Sigma-Yasi forum with respect to RTTOV is, let's say, it's more precise, but it's not as fast as RTTOV, and it's more flexible. So from this point of view, we can work directly from, let's say, a line-wise analysis. And here, let's say, the approach is of using recurrent neural networks and long short-term memory. Because of the similarity of this approach, very well developed in, let's say, artificial intelligence for natural language processing, with the radiative transfer problem, because also radiative transfer problem in a certain way build up at different levels, like a sentence build up with different words and so on. So there are a logic similarity that seems very promising. Okay, the last things we are doing is also working on, not on the radiative part, but also on products. And so on, let's say, fusing data from the YASI with forum. We are speaking about all synthetic data with the processing, which is somehow sound for other platforms, which is a complete data fusion, which works on products that are obtained with the optimal estimation method. So the interest is also to compare assimilating, let's say, this kind of products, which are in a certain way prognostic variable with respect to assimilating radiances. And this is another line of activity. So concluding, we think that forum is going to provide information. We are looking at ensemble in order to see under which condition, under which phenomena this is going to happen. Then we are working on channel selection. We are, let's say, setting up observing system simulation experiments to make tests. And then, let's say, we are also working to produce an observation operator or the Sigma-Yasi forum, and also, let's say, experimental assimilation of fused products, like sort of super observation solution. Up to now, we have used WRF for other experiments. We want to move to MPAS because of the recommendation of this morning, but also because, we think it's more flexible and it can address different scales. That in the case of forum, which is an Earth exploring mission, could be very interesting because we guess that the higher impact should be not in the, let's say, limited area model, but probably on the global model. So from this point of view, we think that MPAS should help on this. What we have done installation of MPAS. We have made some tests. Not everything is working. Also, RTTOV, we have just put the question this morning, but some other things are still to be solved. And from this week, we should have also operational a new platform, which is based on CPU and GPU power capabilities. And so also from this point of view, we would like to understand how to optimize the MPAS run using this capability. So any help is very welcome. Thank you for the attention.
One quick, this sensor, what is their timeline to launch?
Timeline is the launch is foreseen formally, officially at the end of 2027. But I mean, from let's say private information, we know that probably it should happen at the beginning of 2028. Okay.
Next speaker, Samantha Baker from U.S. Air Force. Okay, Ivan.
Thanks. Yeah, Sam Baker unfortunately couldn't come today, but these are her slides. I'm going to do my best to present them. So this is our efforts to use MPAS JEDI for rapid refresh modeling. It's a work in progress as well. But I wanted to say just at the beginning of this talk, I've been in this group for a long time. You know, as mentioned earlier this morning, that this is the 26th version of this for WRF. And we have gotten just so much out of WRF and the Air Force over the time of this collaboration. Berkeley Gallo, my colleague, will be giving a talk on our WRF efforts tomorrow. But I just wanted to mention, especially given all the uncertainty right now in Thrash, of just how valuable this has been. The people that have worked on this over the years, you've undoubtedly saved lives. You've certainly saved money, and you've helped the United States Air Force with their missions across the world over time. And so just wanted to give everybody a little bit of a positive, given all the challenges that we're under right now. So like I mentioned, Samantha Baker, this is her presentation. She's been working on this primarily. Also, Berkeley Gallo is leading the effort here, and I'm just talking. So a little background on what we do in the 16th Weather Squadron in the Air Force. So we are the operational unit doing weather modeling in the Air Force. And so 24/7, we are cranking out models, and I'll get into a quick overview of that in a little bit. But hopefully the picture collage here that's shown gives you an idea of what we're supporting. It just runs the gamut of everything you can think of information-wise within the United States military. And moreover, we have a mission to rapidly adapt information. The main use case for that for us is standing up high resolution WRF domains where people need it, because things pop up in the world, and we want to make sure we're giving our supported users the best possible information we can. So we typically turn that sort of a thing around in like a day or two, depending on the situation, but also packaging information so that users can consume it in a way that they understand, whether it's specific for a weapon system or what it may be. So some of the capabilities that we have, global modeling, we are in collaboration with the United Kingdom office on that. We call our version of the unified model GALWEM. And we also collaborate with NASA to do land surface modeling and the land information system. Those forecasts and analyses go out to 16 days. And then, as I've mentioned, the fine scale things that we're working on right now, you've got some 1 and 4 kilometer ensemble capabilities within the WRF framework. And so one of the main messages I wanted on this slide for everybody is that we very much collaborate with anyone and everyone. Our job is to make this work for the Air Force. We are not the experts in any of these things. And so we definitely want to partner with folks who are interested in the same sort of things to get these out there. On there, I note the rapidly updating global cloud analyses and forecasts. Historically, that was just an analysis and simple advective technique. We are moving in the direction, obviously, of more numerical techniques in that regard, and that's kind of the direction of this talk, is replacing some of those capabilities with MPAS and JEDI-based capabilities. So this is one of Sam's slides that she wanted to mention, that we are, because she does a lot of technical work here, that it's a challenge for us in the military and the government. We have a lot of rules and regulations we have to follow. We have to have all of the code into our own repositories. So we have to do the initial work to get things set up, and then we have to carry it over, kind of hand bring it in. We're not allowed to connect to the internet, from our systems. And so there's a lot of work there to sort of reconstitute all of this thing on our side, to include a lot of the work to document and scan for cybersecurity. And so Sam's done a lot of work to get all this set up for us, so that we can have a sustainable capability moving forward. And she kind of aligns, or outlines all of the things that are on here. But the main point for us on this is that it's a little bit more complicated for us because of this, a little bit more work, collaborating with folks because of this as well. So the first thing we've done, this is kind of counting our steps over the last couple of years. The MPAS Jedi tutorial that NCAR has, we kind of mirrored that into our own space, and then we kind of worked through all of that, all of those things, just to get a sense for what this was going to work like in our environment, get the kinks worked out, and also start thinking what it looks like from an operational workflow perspective. That's very important for us. Being an operational organization, we have to have a sustainable workflow, one that we can train people on, and hopefully something that works easily. I wanted to note as well that this is mostly the computer system referenced on there is HPC 11. So this is our main supercomputer that's at Oak Ridge National Laboratory in Tennessee, another collaboration there. But we also have a separate team, and some of those folks are online, I believe, that are setting this up in Amazon Web Services as well. And so we've got two different efforts, to learn and grow our MPAS Jedi capabilities. So we use Silk for our workflow. Silk 8 is the version we've just migrated to. And then also the ROSE extension, if you're not familiar with this, ROSE is kind of the configuration options for Silk. And I'm not an expert on this. Again, these are Sam's slides. But this is how a lot of our other operational stuff is orchestrated. And so we just are trying to keep everything similar, again, for a sustainment point of view for people that have to keep these things running. The mode that we're gonna go into with this is not to just cycle MPAS Jedi forever on its own. We're gonna use our global model, the GALM as the first guess, and then we'll bring our own observations in for Jedi. So for now, we're doing more of a 6-hour traditional thing for our initial capabilities. We want to get that down to hourly, of course, but we're doing it this way for now. And then including in that then post-processing capabilities, we're very interested in all things clouds and really anything that affects electromagnetic spectrum, either distorts it or disrupts it or anything in that regard. So that's where we're at right now. This is something that's recently been set up. We're hoping to get some real-time runs that we can get out to our customers with this capability soon. And then we will start working our way towards improving that, which I think I'm getting ahead of myself on the slides. Sam also wanted to mention the data assimilation monitoring that we're utilizing the scripts that are available from JCSDA, and this will enable us to do some accounting for this. I really should mention that our capability that we run from the Met Office, they send us their analysis file every cycle, so we don't do any data assimilation on that. And then for our WRF runs that we do high resolution, those are all just downscaled off of global models. And so we don't really do any atmospheric data simulation right now operationally. So this is something that we're growing into and trying to learn with the tools that are available within the collaboration that we have. So I've mentioned a couple times, we're really going at cloud forecasting here and related types of applications. The best of this, of course, is the all sky DA types of cloud information. This, of course, is going to be more costly. So when you're trying to run rapid refresh, there might be some trade-offs there. But this is going to get you the best quality, theoretically, to be able to get as much information as you can out of that. As sort of a middle approach, then we're still very interested in direct insertion cloud analysis. As a quicker way to get cloud information in from a rapid refresh capability. And we're really looking to invest a lot of time into tailoring this system to just try to find the sweet spot of all the different data simulation, all the different observation types and everything to try to get as much improvement in short-term cloud forecasting as we can. So a little bit then on where we're going, since we're really just kind of at the outset of this for us operationally. We're going to implement some kind of very basic capability, like I say, kind of a 6-hour 3D VAR sort of thing, just so we can get our operational chops going a little bit and also introduce this to users that we're doing this. And we've just recently been scoping out future things that we want to do. Regional is going to be big for us. We always have needs to have higher resolution refinements in key areas of the world that we're supporting. Looking into additional observation types, particularly there's observations from commercial platforms that are increasingly becoming available that we want to look into. I mentioned before, getting a frequency, from 6-hourly to hourly, and then also refining, exactly what the techniques will be for that. Continuing to work on this capability in the Amazon Web Services to give us more options from a computing standpoint. Sam's been having a lot of issues with CRTM not working as expected, and so that's something we're going to have to dig into a little bit more. We've noticed these issues both on our supercomputer at Oak Ridge and in Amazon Web Services, and so there's something going on there that's not unique to the system or the setup that we need to dive into, and then getting the full post-processing capability going for our users. And so we really anticipate, just having talked to our user base quite a bit about where we're going with modeling, that we're going to have a lot of interest in this, and collaborating with them to try to prioritize where we're going with this will be a key thing. So thank you. Appreciate your time. Any questions?
One quick one maybe. Yes, I can imagine you want high resolution, but if globally you like to do the variable resolution math at different occasions.
Yeah, we've thought a lot about this, that we probably will have, I don't even know what we'll probably do. We're thinking about it. Have a global domain with regional meshes for places that we're always going to be interested in, like CONUS and maybe Europe and other places where we have a lot of people stationed, right? But then we'll probably also want to have a capability where we just have a single regional mesh with a really coarse global that we would just throw down, in whatever part of the world happens to be interested in to us at a certain period of time. So, but yeah, we're still kind of talking about a lot of that kind of stuff. So. For those online, we're trying to get a question in the room with tech.
Okay, here we go.
We're good now.
From a developer's point of view, you mentioned a number of things you have to do to bring it into your system for security purposes and everything. Is there anything you could tell us about maybe how we could redesign things and make your life easier? Because a lot of the ways we do things are, I won't say arbitrary, but have a lot of flexibility. So perhaps if you have some ideas on that, you could communicate back to us and we could make your life easier.
Yeah, I definitely appreciate that sentiment. That's great. I'm not the right person to give you that information, but I can certainly get the right people that do. I think they in my world they talk about shifting security left, if you've ever heard of that before, and that's pretty much what you're getting at. And I think on other projects where the Air Force has collaborated with NCAR that we've given, like, hey, this is what our standard is, and then we give you guys the tools and the information to do that yourself, so that as you're writing the code, it's just it sort of gets baked in. And then of course we got to figure out, that obviously adds some overhead too to the costs. And some of the challenge there is that we wouldn't this is obviously a large collaboration with more than just us. And so you wouldn't want to get too drilled down into our specific needs and then overwhelm, the developers dealing with all of that. So there's a sweet spot there where it's can you do some stuff at the outset that makes things easier? And then we're always going to have, to take it the last mile, into our situation. And the other challenge there is that our goalposts are always moving, because obviously the cyber landscape is not fixed. And so yeah, there's a long answer. There's a sweet spot there, and it's great to have that conversation with you to figure out what that sweet spot should be. So the question from Mark Stillinga: for Jedi simulations, are you using primarily global MPAS or regional MPAS? Currently global. We intend to, at this time, to just use regional refinement and not do the actual lateral boundary condition regional version. But once we start getting in there and running these things, we reserve the right to change our mind. So. All right. Thank you.
Next speaker is Lipeng Jiang, NCAR Cubed.
One moment, let me just find your presentation.
Okay, good afternoon, everyone. It's my pleasure to be here to sharing our recent work about the offline estimation of RBC coefficient and their covariance. This is actually a part of our recent work on satellite readings DA in global and regional MPAS data system. So variational bias correction, RBC, is widely used in operational NWP centers to correct the observation bias dynamically. So considering the bias of observation, so the observation operator can become h of x plus a linear combination of a series of predictors multiplied by their coefficient. So together,
please. Apologies, one moment. We're just having some technical issues here. Just get it back up. Thank you so much for your patience. Okay, you should be able to go now.
Okay. So okay. So together is the predictor and the coefficient. It is called the bias correction model. So for data assimilation with FAR-BC, it's actually to minimize the cost function with respect to the state variable x and this RBC coefficient beta together. So it also consider the background error covariance of x and also the error covariance of beta. Not forward. So there's the challenge for the use of RBC still exists in MPAS data. So the RBC is highly dependent on the initial values of the predictor. If the initial bias estimations are not accurate, RBC may convert to a wrong direction or incorrect values. So previously, we have two options to provide this initial estimate of RBC. The first option is to use global estimations directly, for example, to use INSEP operational results. But this may be not suitable for regional DA or even for global DA because of different model physics or model type. Another option is to conduct a long-term assimilation cycle to convert to a stable bias estimation. So here I'm showing you an example of using GSI converted estimation as the initial condition for RBC. Here you can see that the bias is still not stable even after 1 month cycling data assimilation. So here, this example led us to consider how to get optimal estimation of RBC coefficient effectively. So if we looking into the cost function again, the online RBC formulation, it minimizes the cost function with respect to x and beta together. But here we thinking about if we remove x to the we keep x fixed. For example, using external read external x directly, then we can switch to an offline RBC mode. In this mode, it actually minimizes the cost function with respect to beta only. So in this way, it makes the problem much simpler. So here I give the solution of beta and its analysis error in this two formulas. So here you can see that the beta is dependent on the prior estimation and the observation information used in each cycle step. So at the beginning, we can start with a quite large beta error. In this case, it actually setting the inverse of this error to be 0. In this case, beta 0 and its analysis error can be computed just using the observation information and its corresponding predictors. So to be clarified, I just listed the detailed procedure to estimate to estimate beta and its error in a cycling mode. We firstly get the prior estimation of beta and its error just using observation information and its corresponding predictors and observation errors. And then we can update beta and its error in a iterative way. Yes. So all the information here can be read from the JEDA OBS out file, which contains all predictor values and all the h of x values. So here it still it's worth to mention that in practice we still need to apply inflation to the prior estimation of the beta error. If you do not apply this inflation, the B beta will going to be smaller and smaller during the cycling process. So by applying this inflation, we can get even we can balance out this decreasing trend and get to a stable estimation of the error of the beta. Okay, so because all the information are saved in the OBS out file, we can perform this offline estimation outside JEDA. Actually, we developed a Python-based tool to perform this cycling estimation. It's just 300 lines of code. So to evaluate the performance of this offline estimation tool, we firstly calculated 1 month h of x using INSEP GFS analysis as a background. Here I'm showing the result of AMLCA channel 9 from METOP B satellite. Here you do see there the a notable warm bias in the simulated observation minus h of x. So here I'm showing the evolution of RBC, the coefficient and from the coefficient from the left plot and its error in the right one. So here you do see that the error of this estimation becomes stable after several days cycling. Yes. And then we can apply the final estimation to the predictors and to check the contribution to the total bias from each predictor. Here we also checked the mean of O minus B as a function of satellite view angle. We know that satellite view angle is an important bias source in microwave satellite observations. Here, the green line shows the dependency to the view angle before bias correction. But the blue line shows that after the bias correction, these dependencies are removed very nicely. So here is the final result. From the left plot, you can see that the mean of observation minus h of x after bias correction is quite closer to 0. And you also do see that there's a significant reduction of standard deviation. Okay. So to summarize, a Python tool has been developed to generate RBC initial conditions for MPAS data for both global and regional applications. The tool depends only on the OBS out file that can be obtained by MPAS data. This enables getting rid of reliance on external information. And we of course, we hope to improve satellite data assimilation in cycling DA. And I also want to mention that currently we do not consider the bias from model. That's all my talk. Thank you.
Thank you so much. I'm Shima Shams from Anchor. I have two questions. One is that through this progression of iterative solution, could you also resolve the seasonality that you might see? And is that considered in the bias, in the covariance error?
Sorry, in the signal. Currently, yeah, I think it should work. It highly depends on the predictors you selected, but we not yet perform through long cycling
into that cycle?
Yes, we do perform some experiments in the regional data assimilation. Yeah.
I mostly meant, like, for instance, if you were comparing vias or simulating vias, are you doing assessment of variability for that region in particular, and then you that view before going into your cycle for the covariance error?
We compare. Also tried to use the INSAP result from global models directly to regional data assimilation experiment, but it seems not to work very well.
Probably we can discuss offline.
Sure, sure.
Okay, thank you.
Let's one next. Okay. I'm not sure that's
I'm Otávio Feitosa. I'm PhD student for INPE. And today I'm going to present about a neural data simulation for neural weather prediction. Questions after. We face with traditional data simulation methods have a lot of complexities, and with the growth of observation data volume in the near future can be hard with our traditional or the methods we have today to incorporate all data you have. And one solution we bring here is use data simulation for make the using neural networks make data simulation. Our approach is create the analysis direct from the observations without, and this is the first approach. We try to use pseudo observations with old models, but I will show for you both cases. But basically is from the observation create one analysis. Our reference analysis here for the training is error 5. And for do that, we use some kind of conv-LSTM architecture. This is allow the neural network capture spatial and temporal dependence simultaneously. It's very important because we go out direct from the observation, and a lot of points on the globe we don't have observations, and have this time and space ability to understand close observations and radiance, because you use basically most of data come from satellites data is important. That's why you use conv-LSTM. But inside this conv-LSTM, use some kind of mixture of experts. I have a lot of sub-models. It's basically a lot of conv-LSTM, and I divide here, I have 8. And each sub-model will basically, I have a router. This router learn alone, like they make here like a clustering. They divide the globe in different domains. In this figure, you can see how the more activate models, each color is one side model, but every sub-model is one kind of conv-LSTM. And this is important because I can generate a global for analysis, not just for one big model. I can divide in very small sub-models and create. This is important because after that, I don't need to run one big model. I can divide in very, very small models and run everything separately, and different machines have a lot of computational abilities we can gain from this technique. But basically every subdomain here, I learn one specific region and reconstruct the features, atmospheric features from these regions. Our input data coming for GTS network, have operate data from soundings, aircrafts, have a lot of things inside the berths. We have surface information too from the stations, airports. For radar data, we use just for America to make a test. This model have some channels, but we train just for America because we find available for our training periods just for America, North America. And satellite data come from MSUA, HERES4, and GeoMosaic. We have a historical from 2008 until 2020 for training. After that is our test. And at the beginning, we try using Voronoi mesh like MPAS, but we migrate in this first approach for help peaks, because it's more easy to generate the grid, but in the future we need to pass for the same MPAS grid, because if you generate in the square grid, normal lat long grid, have a lot of problems in the poles, and using spherical natural grids, we gain a lot of we reduce the error. When I pass to the model, don't create spurious structures, and a lot of things come from the projection, not for physical phenomena. And basically, I use the last 20 hours, each 6 hours for this model and for the LSTM before the analysis. Our output in this moment, we have five variables in 13 levels. These variables go to the MPAS like a grip2 file. And in this moment, we don't have the surface variables. They come from the reanalysis, but after we finish the train, the 3D model, we go to surface variables. But for the results I'm going to show for you, everything comes from a 3D estimation for these 5 essential components to initialize the model. And we choose one case for see the performance is outside of train. It's basically 4 years after train. We have one case of stream precipitation. Have a lot of human and material destruction. In this case, you can see here all the dirty water basically come for. This is normal. This is how this event destroy a lot of cities and bring a lot of problems for this region. For every model I'm gonna show for you, use the same parameterization. It's the same model, it's MPAS model, but with different initialization files, different models. It's global. And for the first results, here I have GPM emerge as my reference for precipitation. And I calculate fraction skew score for 3 threshold. And first thing, for the global precipitation, we have a group partners of position of the accumulate precipitation. This is 10 days of accumulate precipitation. And for this integration, have group partners in competitive with GFS, initialized with NSAP and GFS model. But when you look for the details, have a lot of things to improve. This is for 2 meters temperature. We have good metrics. This is compared with our station from GTS. Have some bias because in North Hemisphere have more observations, but it's just for give you some outlook how the model performs. And this is specifically for that case. In our results, looking globally at the precipitation, we have some bias because a lot of the model basically estimate well for the tropics, but the subtropics, the initial conditions is not well estimate. We have a lot of theories for that. But we have a barocline and very delicate, and small errors can propagate and create a lot of difference in the future, principally for this region, the cyclone and everything else. But GFS simulate very well with some days of here is more or less 5 days before the mode of the precipitation. Have 5 days before the start of more intense precipitation. But I get for the same period for United States, have some cold fronts in this period, and the model simulate well the partner. But for mid latitudes, not too well the high values of threshold, upper 100 millimeters here. And we test 2 meters temperature for North America too. It's very competitive. The principal difference here, we don't try replace the traditional data simulations just because this can complementary for the operation, because we need traditional data assimilation for train our model. But the time we gain, like we use a normal computer for opening how birth files, data need for simulate and run the model. We use less than 20 minutes for generating group 2 files. We increased a little bit because we're gonna have the surface variables too, but we gain with time. This is important for operation, and okay, need be tested with more case, but it's very important for operation have this time game. And with Mo, we can reduce this a lot because you can run every submodels and different GPUs. It's really easy to parallelize this kind of models. And summarize everything, for temperature, we have a small difference globally compared with the observations. Globally, we have superior precipitation skills. Our hypothesis is because they position well where is the tropical precipitation, because basically they look the satellite data and put there exactly where is the nucleus, and or this is our hypothesis. We gonna try this for operational testing in the future, because it's possible run in operational for simulation, day-to-day simulation. And we have a lot of things to improve here, like increase vertical levels. The resolution is 1 degree, is very low. With the model, we run at 30 kilometers, but the resolution here is 1 degree. And we're gonna improve that. And thank you for your attention. And thank you for my advisor support of work and the agencies support this work.
Say for each analysis you produce a sequence of analyses in time. For each of those analyses, what window in time of the observations go into that analysis?
For generation 1 analysis, like 0, I look the past 20 hours, each 6 hours with time step. It's like a 3 time step, but we test with 24 and we get a better result with 24, but it is heavy to train. But with 24 hours, last 24 hours, we have some gain. After that, we don't see much gains, but we need test.
There's a 24-hour window that you look back,
yeah,
and then you bin the observations into 6-hour slots within that window.
Perfect. Okay. Yeah.
So if you take one observation and just did the analysis with a single observation, how would the influence spread in space?
Oh, when you look just for convolutional, when it tests without time, just space, it's very you have an isotropical propagation of the information. It's not a too much.
And it would go across those areas you showed between the experts, that those experts don't have anything with localizing the effect of the observation?
Oh, every expert see the same time, same stuff, but we don't want to activate every expert for the same place. Yeah, they propagate, but we have here some entropy loss, and the difference between one expert and another is very smooth, because we don't want a very 1 or 0 expert. We want some smooth expert difference in the space, when you optimize, we choose some entropy distribution on target. It's not a too much high, not too much low. And for have this smooth propagation of the information in the space. Because
thank you.
Okay.
Sorry. I didn't mean to interrupt the speaker. And now he's gone. Okay. I'm done. Yes. Okay.
Let's move on. Next speaker, Rong Kong, also from NCAR. This will be remote talk about radar.
Yeah, can you hear me?
We can hear you and we can see your
Okay.
presentation.
Yeah, since I'm able to share right now, I'm gonna share by myself. The talk, my name is Rong Kong from MCube NCAR. The talk I'm gonna give today is about assimilation of radar reflectivity and radio velocity using the JDAL ETKF and the MPAS model, focusing on case study of an afternoon thunderstorm in Taiwan. I work with my advisors, Jake Liu and other MCube colleagues, and I would like to especially thank Dr. Guifu Zhang from OU for his invaluable suggestion and assistance. And this work was supported by the Inform project, which is a cross-lab collaboration on model and observation integration. Background and motivation. So the joint effort for data assimilation integration, JDA, provides a unified framework for atmospheric DA, but its radar operator currently does not yet support the dual polarization radar variables. And NCAR MCube has implemented a parameterized polarimetric radar operators, which was originally developed by Zhang et al. 2021 into the MPAS JDA, which support the reflectivity and the other dual polar variables and are compatible with both single and double moment macrophysics scheme. So to evaluate the performance of the newly implemented P-Pro operator, we conduct a case study assimilating reflectivity with the P-Pro and the radio velocity with the standard operator in JDA. Coupled with the MPAS model. And the assimilation of other dual variables is planned for future work. And we also, since the tangent linear and adjoint component of the P-Pro have already been integrated into JDA, and the next step, we are gonna test it for future use in the variational DA framework. First, let's take a look at the case. It's an afternoon thunderstorm event happened on June 24, 2022. Here it shows hourly composite reflectivity fields from 0 to 17 UTC. We can see start from 5 UTC, storm start initiate on the Taiwan island and keep developing in the next few hours. So we launched the spin up forecast from 0 to 6 UTC and conduct the data assimilation cycles from 6 to 12 UTC. That covers most of the storm development period. This is the MPAS model setup. We use the MPAS model with circular domain that covers the area centered over Taiwan island. We use 3 kilometer horizontal resolution with 66 vertical levels, convention permitting physical suite, NSSL double moment macrophysics scheme. The initial and boundary condition comes from the GFS forecast, and we use 30 ensemble members for ensemble forecast and DA. And we conduct 2 sets of experiment. The first is no DA. We launched the free forecast from 0Z GF analysis. And for the DA experiment, we first launch the 6-hour free forecast to 6 UTC and assimilating radar radio velocity and reflectivity data every hour for 6 hours. And we use a combination of RTPS and RTPP for inflation. Localization radius is 18 kilometer in horizontal and 4 kilometer in vertical. Now let's take a look at the operator. The parameterized polarimetric radar operator was originally developed by Zhang et al. 2021 and later enhanced with a melting model from Liu and Zhang 2024. And it was implemented by in the JEDA UFO by MQT, including the development of tangent linear and age inversions of the operator. It enables use the JEDA variational theory framework in addition to InKF, support reflectivity and dual pole radar variables, and compatible with both single and double moment macrophysics scheme. Now let's take a look at the operator. So this operator estimated the radar variables as a function of mass weighted mean diameter, and these functions are derived based on from the T-metric simulation, and the coefficients are calculated based on hydrometer categories and the melting fractions for different mixed phase species. This is a melting model. In Liu 2024, in this melting model, the mixing ratio and the number concentration for melting species are calculated using the geometric mean. This is shown in the formula. So the use of this geometric mean allows for a smooth transition between rain and frozen hydrometers during the melting process. Here I give an example of what's the reflectivity looks like after DA. So here shows the reflectivity observation and estimation from background analysis. And we can see the middle panel shows the background field. The reflectivity is generally underestimated, and some key storm features are missing or too weak. So after DA, the analysis is able to better capture the distribution and some storm convective storms in this area. This is from the first member and the first DA cycle. So when we examine the ensemble mean, we can see the background better capture the whole distribution because the averaging all the ensemble members, but still tend to underestimate the intensity. And in the analysis mean, try to capture some convective storm features, but still a little bit weaker than the observation because of the averaging impact. They try to tend to smooth out some convective storm features. So this gave the example what's the vertical cross-section of the reflectivity looks like. This is for the third cycle. The middle one shows the background field. We can see it still underestimated the whole distribution under the reflectivity curve. So after DA, the reflective curve is much closer, is more consistent with the observation. So when we examine corresponding analysis increment from this DA, we can see actually a lot of snow graupel were added to the mid to high levels and hail to the mid levels, and the rainwater added from the low to mid levels. So we can see it demonstrated the effectiveness of this DA process. Since we are also assimilating radial velocity in our DA, here I give an example of what the analysis looks like. This is the radar observation on 0.9 degree elevation angle, and the reflectivity estimation from the background mean and analysis mean. So we can see from the observation, we can see some inbound, outbound velocity contrast, where this signature is too weak from the background. And assimilating radial velocity helps to sharpening this contrast. Here I give some statistical verification result. This is the root square error for reflectivity. This is a vertical profile of the root square error from 6 to 11 UTC, which is shown on the left panel. We can see the analysis significantly reduced the root square error compared to the background. And this reduction is most obvious in the low levels where radar observation is more informative. And when we examine the average of the root square error, the time evolution of this, we can see the reduction is very consistent for all the DA cycles. And we can draw similar conclusion for the radial velocity field. And we notice there is a gap here because the radial velocity observation is missing on that time and at that level. So The analysis reduced the root mean square error compared to the background for all the levels and for all the time. Here we show the neighborhood fraction scale score for reflectivity verification for ensembles. It's verified against two threshold. The upper panel is 20 dBz. The lower panel is 35 dBz, and the left with two different neighborhood. And the left panel shows the 3 kilometer neighborhood, and right panel shows the 15 kilometer neighborhood radius. So we can see analysis is significant improve upon the background, which itself is superior to NOAA. And this improvement is most obvious for lower threshold and with a smaller neighborhood radius. And we also examined the 1 hour accumulated precipitation forecast for 9 and 10 UTC. At that time, the precipitation is most intense. We can see compared to the NOAA experiment, which is shown in the middle column, the DA experiment is able to better capture the intensity and the distribution of this precipitation band. This is a neighborhood verification for this 1 hour accumulated precipitation, verified against two threshold 5 and 30 millimeter per hour and with two neighborhood radius. Overall, the 1 hour precipitation forecast after DA shows improved performance relative to the NOAA experiment for both threshold and the neighborhood radius. So the conclusion is that the parameterized polarimetric radar operator has been successfully implemented to MPAS data. And we use a case study, and it demonstrated assimilating reflectivity with the P-Pro and assimilating video velocity improved analysis of convective structure and short-term precipitation forecast. And this improvement are consistent support by verification result. And the result confirmed the potential for P-Pro for effective radar assimilation within this MPAS data framework. So looking forward, we're gonna extend the simulation to additional dual power variables such as ZDR-KDP to further leverage the full capability of this operator and conduct a simulation experiment using the integrated tangent linear and adjoint component with the data variational DA framework and apply this system to multiple cases for broader validation. That's all I have. Thanks.
Wait. Oh, okay. Thanks for your talk. And I noticed that you're using the uniform mesh, and I'm wondering if we are using the variable mesh, is there anything need to be take care?
I do not use the uniform mesh. I use the variable mesh. It is rotated. It's 3 kilometer variable mesh, and we rotated and cropped to our domain.
Also, it's already a variable mesh.
Yeah.
Okay, thank you.
But our domain is very small. It's almost 3 kilometer resolution.
Last speaker, Sung Han, also from NCAR Cube, also radar DA related.
Hello, everybody. This session is really quiet. I guess everybody is sleepy. But as a last speaker, I probably can take as much time as I want. The title is today I'm going to talk about the advancing non-hydrostatic radar DA for the radar ensemble data simulation for convective scale forecasting using the regional MPAS. June Park has done all the experiments that I'm showing here today. And I just want to say thank you to all my amazing collaborators and also Gretchen, our lab director, for extra support for the computational resources. Okay. Okay, let me start with the challenges in the storm scale ensemble DA. So storms are fundamentally non-hydrostatic, as we know, with a strong updraft, downdraft. And the MPAS model is fully compressible non-hydrostatic model. And to be consistent with that, non-hydrostatic analysis is essential for storm scale radar DA and accurate storm forecast. For instance, to predict the convective initiation and storm intensity. Radar observations have like a highly nonlinear, non-Gaussian error statistic, like characteristics as we know, with the bounded values or the skew distribution, like in radar reflectivity. And also, we typically assimilate the clear air reflectivity to kind of suppress the spurious cells, right? Which has like a zero spikes in the distribution. And so like a traditional ensemble Kalman filter, here the ensemble adjustment Kalman filter, I can say, assume the Gaussianity and can produce unrealistic analysis updates. The storm scale ensemble DA means high resolution, rapidly updated cycling, like with a 5-minute, 10-minute, 15-minute, intervals. So it is very expensive to limit our ensemble size, meaning that it produces large sampling error that actually leads to noisy analysis typically. So today I'm going to briefly talk about, the radar DA in regional MPAS DART. The MPAS DART interface was built on the native MPAS mesh, both horizontally and vertically. And then the model prognostic fields are used as analysis variables. So there's no transformation, variable transformation, vertical transformation. There's usually the variable transformation requires a hydrostatic assumption. You don't have such a thing here. And MPAS DART supports a serial observation update, so you assimilate one observation at a time. So nonlinear and non-hydrostatic analysis increments can be built up progressively. And the MPAS DART is actually supporting multiple ensemble data assimilation algorithms, including non-Gaussian, bounded, and mixed distribution analysis using quantized conserving ensemble filters. That's what so today, my key question was, how suitable are traditional ensemble Kalman filter for radar DA at storm scale? And can we, and by how much, can improve radar DA performance using non-Gaussian analysis? So that's what I'm going to talk about today. So last year, NSSL picked up this regional MPAS DART for their one-on forecast system. Test in their one-on forecast system. So this is the configuration they set up. So using the 36-member ensemble, multi-physics ensemble analysis, followed by 18-member ensemble at 3-kilometer resolution, horizontal resolution. So this is a quasi-uniform mesh, assimilating radar reflectivity, clear air reflectivity, radar velocity, and goes cloud water path and surface data. So basically, they took the WRF GSI ENKF configuration for the filter as a filter design, and partly from WRF DART, I believe. And then they used this like a physics as summarized in this table with this enhanced microphysics, which is a 2-moment NSSL scheme. And okay. Let me move on to the next one. So this is what Yoon Hong showed me, and actually Newsred introduced that to me. So actually last year when they picked it up, the regional MPAS DART for their test in the one-on forecast system, I think that's part of their plan for a smooth transition to the MPAS JEDI. I was asked to update the MPAS DART for the regional MPAS with the radar DA capability. So that's what we did, and this is what they actually ran out of the box without with no tuning whatsoever. So on the right, I'm showing you the one they ran like out of the box, using MPAS DART compared to the left one, which is kind of best bet, I think their best configuration based on the hard type WRF using GSI ENKF, if I remember correctly. So like overlaid by the shade, the dark shade of which is the MRMS observation over 40 dBz. So you can see that the left one is almost perfect, but then the right one using the MPAS dart is quite noisy, right? So we were asked to help, to see if we can help reducing those kind of a noisy, analysis. And so June and we actually have done, a bunch of tests, right? I mean, trying to optimize the parameters. And this is the three frames here. So first one is the NOAA NSSL's MPAS 1 forecast, as a very first cut, right? Which was quite noisy. The left one is prior and then posterior on the right. So you can see that, at the prior, in the prior, it's already kind of very noisy, as shown in the light blue, all over the places. And so that prior was already noisy, and then posterior is noisy too. So we actually tuned a lot of parameters, and then finally we could make it much better compared to the MRMS observations as you see here. So here we still use the ensemble adjustment common filter, which is the default option in DART, and the Gaussian inflation. And we tested many things, and then it turned out that adding more levels for the clear air reflectivity observations was the working best. And then we also we adjusted observation errors as well. So as you see, the analysis looked good, but then when we check the following forecasts, they were not that good. So, okay, there's a room for further improvement, we thought. So then here comes the quantile conserving ensemble filter framework for the a nonlinear, non-Gaussian analysis. So this is basically a two-step approach. Because of for the interest of time, I actually took out almost all the equations here. So just to briefly introduce the concept of this approach, the first step is certainly we want to update the analysis variables. For this one, actually through the quantile conservation. So we compute the analysis PDF and then the CDF, which is a cumulative distribution function. So by inversing the CDF, the analysis in CDF, you can compute this analysis ensemble. So here the quantile of each member in the prior CDF is conserved. So that's why we call it quantile conserving. And the second step is that once we update the observed variable, we have to regress them, the analysis increments in the observation space to the model state variables, right? Unobserved variables. So that is done in the probability integral transform space. I really cannot explain all these details here, but I just want to point out that the regression was done in a space where the variables are transformed to be more Gaussian. And so that way we can handle nonlinear relationships between observed and the model state variables more effectively, and also kind of keep the shape of the analysis distribution based on this hydrostatic analysis increment. Okay, so QCF algorithm, there are different options within this QCF framework. We picked up two of them, bounded normal rank histogram filter, which is rank-based. So prior PDF is estimated using ranks of ensemble members and explicitly handles variable bounds. In this particular case, we set up the bound of the radar reflectivity as a 7 dBg, means that below 7 dBg is considered as a clear air reflectivity. And we also picked up the kernel density estimation. So this is another non-parametric estimation to estimate the prior PDF by summing kernels centered on each ensemble member. So this is purely data-driven without any prior assumptions about the shape of the distribution to build a smooth PDF from ensemble members. So this is the probability density functions. So radar reflectivity at the top, and then clear air reflectivity at the bottom for the three algorithms that I compared with. So EAKF on the left, and then a bounded normal rank histogram filter in the middle, and then KDF. And you can see that, so the light blue bars at the top panel is showing O-F. When I put this Gaussian fit curve, in blue, you can see that the radar reflectivity was almost Gaussian. As opposed to that, at the bottom, you can see that the clear air reflectivity, it's just basically the zero, right? So it's like a zero spike distribution, which is like a far, far away from Gaussian distribution as we see. So actually, this is again, the in a one-on forecast system configuration. So they are cycling like a 15-minute cycling so in this case, 4 hours, like starting from 15 UTC. And then, so this is at the top, I'm showing you the prior errors only, no posterior, because it's already too busy. So this is a prior bias, total spread, RMS errors in EAKF, those three algorithms. And you can see that because it's errors, right? So you can see that the blue lines for BNRHF and then the red line, those non-Gaussian algorithms produce the smaller errors in terms of a clear air reflectivity. So at the last cycle, at 19 UTC, I'm comparing this ensemble mean analysis increment at the bottom. You have to look very carefully, but so overall patterns look quite similar, I should say. So I put some, the histogram, the small subset figure at the bottom, lower bottom, and you can see that when we counted this analysis increment, the EAKF with Gaussian assumptions actually reached like 100 dBz as a maximum, of the increment. So if we compare those two, like a top and bottom figures, we can tell that, EAKF is noisier than the other two. So the non-Gaussian analysis seems to produce less noise, reducing the prior errors in clear air reflectivity means that they are more effective in suppressing the spurious cells, right? And then finally, this is the fraction skill scores from the 18-member ensemble forecast. By the time I want to point out that, in this, within this framework, we do the analysis using the native mesh of the model. And so starting from the analysis all the way to the post-processing, we have no regrading. We are just only working at the model native mesh or the coordinate, right? And so FSS was also computed at the native mesh, in the unstructured mesh. And this one is the column X reflectivity over 25 dBz. So in this particular case, I'm just showing you the FSS within the 60-kilometer radius. But we actually check this in all different, like a radius size and then, like over 40 dBz. And we also check the ETS. But, for the precipitation, this one I'm just showing you as an example. And you can see that, because this is a skill scores, they decrease over time. But after up to 2 hours, they look kind of similar. But then after that, the non-Gaussian methods in red and blue, they clearly outperform EAKF. And then after 3 hours, EAKF fall behind the others beyond ensemble standard deviation shown as a shade, right? Which actually expresses the one standard deviation, the ensemble spread. So this is the conclusion. EAKF still works well for radar reflectivity, which is almost Gaussian distribution, once the parameters are well tuned. But QCEF algorithms with a non-Gaussian assumption, or for non-Gaussian nonlinear assumption, improve the assimilation of clear air reflectivity, which is quite critical, it turned out, to suppress this, like a noisy analysis, and, for the erroneous convective cells. So, and in the 6-hour forecast from the analysis, the QCF methods outperformed the traditional ENKF, demonstrating their value for radar DA. And So now the final point is the kind of practical sense, right? So then you can ask, how expensive is that, right? So we actually check the computation time to run the filter at the ratio. And you can see that this was kind of surprising to me that compared to the EAKF, the bounded normal Rankine histogram filter was like almost half the price. So I thought, wow, this is impressive. Of course, this is also dependent on the localization and the configuration you are going to come up with, but at least this one was quite impressive to me. And in terms of so again, in a practical sense, this is kind of a simple and modular for the serial data assimilation and computationally efficient and usable in the operational system. So we'll be happy to collaborate with anybody who's interested in that. Anyway, thank you very much.
Session 3. Welcome everyone for the topic here on MPAS and NOAA Research and hopefully operations. So we'll go kick things off with our first presenter from NOAA GSL. This is going to be on our model development and forecasting activities using MPAS. I'd like to welcome everybody and introduce Clark Evans.
Well, thank you, Curtis, and thank you, everyone. It's a pleasure to be here with you all to share a lot of our exciting work utilizing MPAS as well as JEDI. There's far too much taking place at GSL to cover in one talk, and so I'm grateful that so many of my colleagues also have talks and posters coming up through the rest of this workshop. I'll try to highlight some of that work as we go through the presentation here. So let's see, doesn't look like we're quite advanced. Oh, there we go. All right, so at GSL, we're utilizing MPAS and JEDI to build what we believe are the next generation of operational forecast systems across NOAA. The initial target is for the second version of the Rapid Refresh Forecast System, or RUFUS version 2. And we're achieving this through a wide range of activities, including real-time regional and global forecasts, NOAA testbed evaluations. The two images there at left. Bottom left is from the WPC winter weather experiment. The upper left is from the hazardous weather testbed spring forecasting experiment. Purpose-built forecast systems, such as our work with the Hurricane Forecast Improvement Program in the upper right, among other applications, as well as advancing physics parameterizations, the bottom right showing some of our microphysics development. So I'm going to touch on a lot of these activities here in this presentation, focusing most on our real-time regional forecast systems in the development phase toward RUFUS version 2. So we have 3 separate real-time cold-started 3-kilometer regional MPAS forecasts, all of which use MPAS version 8.2.2 as their code base. Glad to see 8.3 come available. Now we have some extra work to do after the workshop to catch up, as well as physics advances developed at GSL. Our primary system and the focus of much of the results I'll present in the next few slides is our MPAS RUFUS-A system. This is initialized utilizing initial conditions from the RUFUS-A prototype that is currently being evaluated by NOAA for potential operational implementation later this year and into next year. We run this 8 times per day, and we initialize, as I mentioned, both the atmosphere, but also the surface and our aerosols from RUFUS-A. We also have 2 other systems. Dev2 is what we use for our physics testing. It matches RUFUS-A rather than Dev1 as listed there, apart from single physics changes. So for instance, right now, our current test is to evaluate some updated Graupel and Hale tuning parameters within our tempo microphysics parameterization. And then our older baseline is our Dev1 system, which is RAP initialized with aerosols coming from the MERA2 climatology. Provides us perspective with a different set of initial and boundary conditions on how our forecast systems are performing. We have incorporated a lot of the physics parameterizations that are being developed at GSL into our fork of the MPAS model, including the RUC land surface model. We also have the NOAA MP land surface model that we're starting with the version available in NCAR's release and working to reconcile features across the different implementations of that LSM. the MYNN surface layer and MYNN EDMF turbulence and shallow cumulus parameterizations, the Grell-Freitas-Lee deep convection parameterization. Bill referenced earlier in his talk, kicking off the workshop, the unified gravity wave physics that are now available in the MPAS 8.3 release supported by NCAR. We are using the authoritative MPAS version of RRTMG, and then our Thomson-Eidhammer microphysics parameterization for operations, or TEMPO. There's several talks coming up tomorrow detailing the latest and greatest with much of these physics parameterizations, and I'll be giving a poster as soon as I have the correct size poster for the boards, my fault, tomorrow afternoon on our physics integration work with NCAR to bring over many of these parameterizations for the community's use rather than our separate MPAS 4. So looking at some results, utilizing our in-house MATS verification system, focusing first on upper airfields. On the left is temperature, middle is relative humidity, relative to aircraft moisture observations. I'll go into more detail about that in a moment, and wind speed on the right. Our MPAS forecasts will be in the black lines on each of the next few charts. RMSE generally in the solid lines, bias in the dashed lines. For temperature throughout the profile, we have lower RMSE with better bias characteristics relative to the operational HER V4, as well as to the pre-operational Rufus A forecasts over a month and a half of matched evaluations. And for wind speed, much the same is the case. Reduced RMSE throughout the column with better bias characteristics. We're competitive on relative humidity, but you'll note that all of these are dry biased. One of the things that we've noticed at GSL recently through some work collaborative with the National Weather Service is that the observed Rawansan network, particularly the Grassans, tend to not be sufficiently responsive to sharp moisture gradients nor to higher values of moisture. So the story relative to radiosans suggests that we have a near zero bias. It looks fantastic, and we've done a lot of our development toward that over the last many months. But when you look at it relative to aircraft, which do not have those issues and are much more responsive, the dry bias emerges. So this will be one of our leading development tasks moving forward, but it is something that you see in all of the models and not just ours with this dry bias. Looking at the surface, competitive with HER V4 and with Rufus A. Not quite as good as what we saw in the upper air, but right there in the same ballpark. A little bit higher of a warm bias for 2-meter temperature. I will call out 2-meter dew point. There are significant differences in the diagnostics used between these models for computing 2-meter dew point. The MPAS Rufus A is much more HER V4-like as opposed to Rufus A-like, which utilizes an interpolation method that generally leads to much higher 2-meter dew points than what you would see on the lowest model level or throughout the boundary layer there. And that's ongoing issue of development for NOAA for that model. And 10-meter wind speed, very competitive biases there as well. If we look at some other fields, downwelling shortwave radiation, in part a proxy for clouds, better root mean squared error relative to HER and significantly better relative to Rufus A with lower biases, very close to zero, especially after the first 3 hours of the forecast. And then on the right, looking at composite reflectivity, I kept in the 0 hour. These are all cold starts for our MPAS forecasts. So there's no specific reflectivity information in the initial conditions. And yet, within the first hour, that very quickly responds to be competitive with or better than both HER V4 and Rufus A with much better bias characteristics. That bias line is around 1.3 to 1.5, whereas HER is up over 2.5 for these convective reflectivities of 40 dBz and higher. So a lot to like, I think, in our cold started forecast without the benefit of cycling with the latest versions of our physics with JEDI or any other system. One of the issues with Rufus version 1 has been its representation of deep moist convection. There was a NOAA tech note that came out in late 2023 detailing a lot of these issues and making the case for MPAS as the future dynamical core for regional modeling. This is an example from the spring forecast experiment a few weeks back, a meandering upper low in the southeast United States, moderate instability across the southern Appalachians and mid-Atlantic. And yet, despite that, within the Rufus and the top middle, you get widespread, very intense convective cores in this 20-hour forecast with intense updrafts on the order in the upper right of 20 to 30 meters per second. not really supported by the reflectivity observations from the MRMS system in the center of the image. And our MPAS forecasts produce reflectivity fields that look a lot more realistic compared to the observations, with updraft speeds more in the 10 to 20 meter per second range, more in line with what you might expect from that type of environment. These systems have been evaluated in a number of NOAA test beds, most recently the 2025 HWT Spring Forecasting Experiment. In the deterministic flagships evaluation, this was the 10th year in which it's run. The first 9 years, a version of her was top ranked in the 5-week subjective evaluations every single year. This year was the first year that a model beat it, and it was our MPAS forecasts. And it not only beat it at day 1, it beat it at day 2 as well. So I think a really promising result for MPAS, given that we are still 2 to 3 years away from a potential future Rufus version 2 implementation. A lot more that we can do to make it even better as we go forward into the late 2020s. But it's also been evaluated in the winter weather experiment earlier this year, helped us to identify some issues with the land surface model driver. Before this bug fix, we got too much frozen precipitation accumulation leading into accumulated snow in central Texas in this case. We took that information from the test bed, did development, put in a bug fix, and we're able to provide much better forecasts throughout the rest of the experiment. And then the WPC precipitation experiment for atmospheric rivers, a limited sample size, but our MPAS forecasts rated very highly in those initial evaluations. And we look forward to providing more data to the flash flood and intense rainfall experiment coming up in the starting next week. We also have several JEDI-focused MPAS forecast systems. Ming-Hu's presentation later on this afternoon will go into more detail about these. We have one that's focused on cycling tests, making sure that cycling mechanism with the model is working effectively. One that at higher resolution is doing some initial testing of 3D VAR and 3D ENVAR, first with aircraft observations and starting into surface observations now as well. And then one at 12 kilometers that's a little more advanced in the data assimilation that's been there so far. I'll defer to Ming's presentation for more details. Just very quickly showing some of the positive impact from this. These 1-hour forecasts in red are after 12 DA cycles as compared to a 12-hour forecast from the beginning of that cycling period. We see that the DA of just the aircraft data is significantly reducing the RMSE and leading to better bias characteristics for much of these forecasts here. We also have some real-time global MPAS experiments taking place. First, a uniform 15-kilometer mesh, and also EMC is doing some work with this mesh as well. This is once daily out to 5 days, cold started from GFS with a very high model top. This helps us test our physics developments for global applications and longer lead times. We also have this variable resolution 15 to 3 kilometer mesh where the 3 kilometers centered over North America, roughly from the Bahamas northwest toward Alaska. Once daily out to 24 hours, looking to extend that to 48 to 60 hours in the near future. This helps us test the scale-aware physics in a way that a traditional model with nesting would not allow us to do. You have a wide range of grid spacings across this domain, particularly across the variable refinement region. And it helps allow us to evaluate these against 3-kilometer regional forecasts. NCAR did a little bit of this with the spring forecasting experiment this year, and we're looking to begin more of that ourselves moving forward. Some of the initial tests, this is an example from late last week. Tropical storm Alvin in the East Pacific off the coast of Mexico fell firmly within the variable resolution portion of our domain. And yet, even in this 18-hour forecast, we see no noticeable artifacts in its representation despite that. We also have a number of special purpose or purpose-driven modeling systems. We have a 1-kilometer fire weather system focused on the Western United States that runs daily out to 24 hours. This has led to a lot of collaborative development between NOAA and NCAR. Bill referenced some of this with the lateral boundary condition change for these very high resolution applications. We had seen a lot of those issues in our developmental work here as well. This is an example from a couple of weeks ago over Southern California with the Jaw fire over 4,000 acres at the time and the associated smoke moving toward the east and northeast out of that fire. We also have a full aerosols model with multiple aerosol tracers, including from anthropogenic sources, smoke from wildland and agricultural fires. Dust is in process. We also have fine and coarse pollen. And Jordan Schnell's presentation coming up too after mine will go into more detail here. This is an example from late last week looking at the surface PM2.5 aerosol dry air mass across the United States. We have that available on our website as well. Last year, we participated in the Hurricane Forecast Improvement Program. Just a couple of representative examples from Hurricane Milton on the left, Hurricane Helene on the right, the two most impactful storms of the season. Despite cold starts from GFS, you can obtain an simulated Milton very close to the observed intensity with eyewall replacement cycles well depicted within the model dynamics. And the rainfall associated with Hurricane Helene was very similar to that which was observed over multiple forecast cycles. We'll be doing this again this year with a global rather than regional forecast domain. We've also done some horizontal grid spacing tests at 3 versus 3.5 kilometers as part of the spring forecasting experiment. Very little in the way of meaningful skill differences for reflectivity fields. So we're beginning a deeper investigation of surface and upper air fields relative to our existing 3-kilometer forecasts in the coming weeks as well. Big reduction in computational expense by 40% just from this half-kilometer grid spacing change. We also have the MPAS app. Janet Derrico gave a presentation or a poster last year at the workshop. This helps to manage a lot of our Hurricane Forecast Improvement Program project real-time forecasts. And we're working to build this out for other real-time and research applications at GSL as well. So to wrap up, we have quite a bit in the way of ongoing and planned MPAS development activities. Will Mayfield's presentation later in the session will talk a little bit about some of the stochastic physics capabilities that are being developed. Advanced physics coupling between different parameterizations, including NOAA MP and the MYNN surface layer, prognostic clouds between MYNN, EDMF, and TEMPO, and then further integration of aerosols throughout the physics suite. The implementation of the MPAS dynamical core in the UFS. We'll have more on the panel discussion or the discussion facilitated by Curtis and Bill later this afternoon. And Dustin Swales has a poster tomorrow. And then global storm scale or near storm scale experiments. NCAR being higher in the funnel than us. Your 3-kilometer global forecasts really drew a lot of attention in the community. We're just about ready to want to play catch up there as well. So 3 kilometers might be a little too far for us, but I think we can get close with our resources. So thank you all for your time and attention.
Thank you. One question here.
Looks like there's one from Cliff online. Yeah, so Cliff, that is the development cycle for Rufus versions. We think we're in a great place and our data are all available online for the public to see in preliminary and non-operational, non-decisional services. But we think we can make it even better in these next 2 to 3 years to not just lead to an incremental improvement over what we have, but I think more of a transformational improvement over what we have now to potentially inform even broader applications across NOAA's modeling suite.
Thanks again, Mark. I'd like to, I think, hand this one over to our sister laboratory from NSSL and give us an update on progress towards development of an MPAS-based worn-on forecast system from Younghang Wang. So welcome, Younghang.
Thank you. Hello, everyone. My name is Yunheng Wang. Today, my topic is progress towards the development of MPAS-based worn-on forecast system. First, I want to thank all my co-authors for their contribution. Okay. Yeah, the worn-on forecast is a high-frequency data assimilation and ensemble prediction system for severe weather events. It is developed to fill the watch to warning gap with probabilistic prediction of individual thunderstorms. The current real-time worn-on forecast system is run by NWS, and it uses the WRF dynamical core and the GSI INCAF data assimilation system to prepare for the next next generation of warm focus system, we explore the regional configuration with MPAS as a new dynamical core. The purpose is to demonstrate that MPAS-based warm focus system performance comparable or better than the current WRF-based warm focus system. Oh, sorry, I forgot to play. Oh, I forget play the. Okay, let's skip the animation. MPAS-based warm focus is designed to replicate WRF-based warm focus system as closely as possible, and it performs data assimilation with 36 ensemble members with multiple physics schemes, mainly the PBL scheme and the surface layer schemes. Oh, sorry. Sorry. This figure shows the MPAS based warm focus time chart. The system assimilated radar and satellite observation every 15 minutes and using the DART EAKF system. And additionally, assimilate hourly conventional observation at the top hour of each hour. It produces short-term 0 to 6 hour forecast with 18 ensemble members every hour. We developed the first version of the system in 2024 and make a lot of efforts to improve the system in 2025 as version 2 based on the problem we found with version 1. We test both versions using 6 high-impact cases in 2024. These are the paintballs of the analyzed composite reflectivity from 2 MPAS-based version and the real-time warm focus system. The RMS observation greater than 40 dBz are attached as black overlays. It is so that it's shown that the version 1 produced too many spurious storms, and the new version produced reasonable analysis, which is very close to the real-time warm focus system. Just as Song Yang have shown in last session, that's May 8th, 2024 is a more challenging case. This case also is a May 7th case. This is a 2-hour forecast. It shows that same feature, that the new version produces forecasts with less noise feature, and is closer to the real-time warm focus system. Again, the new version produces better UH forecast at 2 hours. It's very impressive for the system over the middle of Illinois and Indiana. The tornado and hail report are attached to the middle level UH at forecast at 2 hours. This is a grid-based verification. The left picture shows the EFS difference between the real-time warm forecast and the MPAS-based warm forecast, where warm color means the real-time warm forecast performs better, and the cold colors denotes weather systems that MPAS received higher EFS scores. The right picture shows the FSS values change with leading forecast hours. As it shown, the MPAS forecasts get lower FS values within the first 90 minutes. The next 2 slides will show the object-based verification for RMS object between 40 to 45 dBz. First, the top panel shows the POD, and the bottom panel shows the false alarm ratio. The dashed right line is for the MPAS MPAS-based system, and the solid lines are for the real-time one-unfocused system. As it is so, the MPAS-based system exhibits a higher POD, where it also generates a higher far values for all the forecast times. This page shows the total number of objects and the total object area, where the top dashed line denotes the MPAS-based system, and the bottom solid line are the real-time one-unfocused system. The black solid line is represents the MRMS observations. Obviously, MPAS predicts far more objects than the observations and the real-time one-unfocused system. One good thing is that the MPAS-based system predicts object area closer to the MRMS observation. As so in the right panel. This is a similar verification as before, but for the new version of version 2, MPAS-based one-focus system we developed in 2025. The new version performs a little better for smaller objects and earlier forecasts. Unfortunately, it is also produce lower FSI value for longer forecasts. Since they are just the preliminary results with limited cases, we are not sure that the percentile thresholds are properly picked when performing this evaluation. We plan to perform more experiments and compute the climatological statistics more systematically later. These are the object-based verification for MPAS-based one-focus system version 2. MPAS-based system still produce higher POD and far, but the far values at the early forecast hour are reduced significantly. And they are closer to the real-time one-focus system. The new version still produces larger number of objects. The top dashed lines are for the MPAS members with larger areas. One problem is that the MPAS forecast object area are now too large comparing with the real-time one-unfocused system. So conclusion and plan ahead. Our new version MPAS-based one-unfocused system eliminates some noise forecasts inherited in earlier version, particularly for early forecasts. Further improvement will be explored to match or our expression to exceed the performance of WRF-based one-focused system. In our near future is to continue to evaluate the MPAS-based one-focus system with high impact events from 2025. Eventually, we plan to make a transition to use the JEDI system to replace the DART data assimilation system we are currently using. Thank you.
Thank you. Questions for Young Heng?
I was wondering if you use the exact same physics in both your WRF and MPAS versions. It was the exact same physics.
Yes, we are using exactly the same physics, but maybe different version, package version. I forgot to mention for our version 1, we're using based on MPAS version 8.0. For the new version 2025, we are using the MPAS 8.22 version and use the GSL version with the updated physical package and adapt some new feature from the MPAS version 8.3 mentioned by Bill this morning, like the new math tools and the 16-point interpolation and W and the setting and the boundary zone, etc.
Interesting presentation. This war-known forecast domain is pretty small. I'm wondering, have you looked at the boundary conditions? For example, this issue, what we found at 1 kilometer MPAS runs is the vertical velocity along the boundaries has to be set to 0. Have you, do you think the boundary conditions impact findings?
Yes, since our war unfocused domain is limited, it's 900 by 900 domain. Larger boundary condition play an important role. That's why we only make a short-term forecast, 0 to 6 hour forecast. When we choose the domain, we always put the system, we look the outlook, convection outlook to choose the domain, make sure the system does not occurs or move out of domain. Another issue is our research, some research with WRF-based war-unfocused system has found that if we expand the boundary domain and the west boundary and south boundary, it will increase our evaluation scores. Yeah. Thanks.
One more question online. The MPAS first. Or doing speculation here.
We're still not sure. We are trying to understand the problem. Maybe it's related to data assimilation or the internal dynamics. We have make a lot of efforts to try to tune the dynamics permission, like the parameter for third order transportation mixing, etc. We have make a lot of efforts, but as you can see from my slides, our new version have improved over our earlier version, but it still have a space to improve. For the WRF-based war-unfocused system, it's have developed several years. We reach current status. Our MPAS system, we just start. I think we should need time to improve this system to catch up with the WRF currently. Thank you.
All right, our next presenter back to NOAA GSL, and this was alluded to earlier from Clark. We'll talk about NOAA GSL experimental aerosol forecasting in MPAS-A. Gordon Schnell.
Thank you. Thank you. Yeah, I guess I don't really need to introduce what I'll be talking about. So thank you all for being here in the middle of the afternoon session. So just to kind of give you a little lay of the land, the NOAA GSL air composition branch works with 3 different modeling systems. Starting on the left, we've got the WRAP-HER system that's been in operations since December of 2020. We have extended that to include chemistry from the WRF Chem chemistry packages, WRAP and HER Chem. The WRAP Chem has been running since 2020, not operationally, but in real time. Moving forward, a lot of you have heard today about the RFS A. Here I'm talking about the RFS SD. This includes smoke and dust based on the FE3 dynamical core. Of course, many improvements based on that. But today I'm going to be talking about the MPAS. We started working to include aerosols in the model this year with the initial porting of the RFS SD smoke and dust modules, as well as the pollen module from WRAP Chem. And so I'll talk about each of these a little bit. So our initial runs are either a 3 kilometer or 12 kilometer cut from the global mesh, so no variable resolution. So kind of taking, I guess, another step back, this is something I was hoping to kind of discuss with some people here in Laura's presentation earlier today. When it comes to deciding to add tracers to the model, there's a couple decisions that we had to make in terms of where to put them. We could add them to the scalar array such that they would just immediately be transported, but this requires some kind of fancy indexing, or not fancy, but requires some indexing so you can pass the chem array. Otherwise, we could create a new chem array, which we could pass around separately, do different sorts of advection, or even just different types of things that we could do to that chemistry array. And so ultimately, we decided just to stick with option one, include the chemistry in the scalars array, but we've been talking with Michael Duda today, and there may be even some extensions beyond option two. So stay tuned. The next thing we had to decide is how to update the tendencies. So in MPAS, a lot of the scalars are actually updated in a single routine where the tendencies are all collected and then those are updated in that routine. Didn't really make sense for us to do this with the chemistry because of how big the arrays can get. And so for now, any chemistry scalars that a physics scheme modifies, it's going to be modified inside that driver. And so we're not collecting the tendencies and applying them elsewhere. They're inside that driver, they're updated. And so I think this has some implications for a number of different things that I'd like to discuss at some point. So kind of bringing us forward, I guess, talking about the real-time runs that we have going right now. Primarily, it's a 12-kilometer resolution, CONUS plus 0Z init with a 24-hour lead time. The 12 kilometer is actually a cold start from the GFS, but we do have the 3-kilometer being tested that's actually using the MPAS RRFSA ICBCs. And so we don't have to do any extra work. We can just copy those over. In terms of the tracers that we've added, first, the smoke that I've talked about, we have emissions from the RAVE emission data set that's persisted from the previous day. And so we're not actually forecasting emissions, we're just using those from the previous day. Additionally, we're testing not just the forecast version of the model, but actually creating the emissions inside the model rather than doing them in a pre-processing step like we do in RFS. We've also implemented a residential wood burning module. We've not tested it yet or activated it, but we have set it up to be tested this winter that we're really excited about. Additionally, I mentioned that we moved the pollen modules in the RAP Chem into the MPAS. And so we have 3 intact tracers, tree, grass, and weed pollen, plus a ruptured component for each of those. And finally, the anthropogenic fine and coarse unspeciated PM. So don't delineate any sort of further than that, just these kind of primary emissions. Oh, the wrong way. So we do have a website set up for this. Here's from just a couple days ago. We've got the diagnostics on the left-hand side, very similar to a lot of the HER and other RAP models, if you've ever used those websites. One key thing is we do have this little real-time verification that would encourage you to check out not only just the MPAS, but we compare RFS and HER smoke as well to one another. So it's kind of neat to see that in terms of the air composition variables. I mentioned that we're working on creating the emissions inside the model. So in RFSD, the emissions are created offline prior to that forecast integration using some history of either FRE, FRP, and sometimes even what's been generated by the model, namely the hourly wildfire potential. On MPAS aerosols, we're trying to add some more flexibility where we can just provide the whole history of a lot of these diagnostics, and then inside the model be able to calculate the emissions at each time step. For example, taking into account the combustion phase that might produce more of PM than had it been a flaming phase. And so we did, create 2 different emission streams for that. Right now, we're just using that prescribed emissions stream for the real-time forecast until we can actually get the true forecasted emissions running. I mentioned that we're also adding this new smoke emission category. Recent work has found that about 20% of population-weighted wintertime PM in the U.S. Is caused by residential wood combustion. So we have smoke in our model. There's no reason why we can't necessarily add this to the smoke that's already existing in our modeling system. And so we've had some collaborators that have provided us with a 1-kilometer emission data set just over CONUS thus far. And so we'd have to work to get something over Canada as well. But we built that initial module to do those emissions based on a very simple parameterization that the smoke emission platform uses, if you're familiar with that. So some uncertainties with that, but we're definitely excited to test it. We also added the anthropogenic aerosols. So, with her smoke and RFS, you can kind of see we're always going to be having this bias, whether when we look at comparison to observations, because we don't have that anthropogenic emission component. And so we started to ingest the grapes anthropogenic emission inventory, emitting just PM2.5 primary and PM10 primary into the fine and coarse modes respectively. Grapes does have vertically resolved emissions up to about 20 different layers, but it's on a different grid than the MPAS is. And so right now we don't have that vertical interpolation done. And so this is likely leading to some biases because the WRF grid is much smaller than the MPAS, or fewer levels than the MPAS grid. There could be some other issues as well. So we're not counting out other things. The pollen module that we've implemented is based off of the pollen emissions for climate models. From Allison Steiner's group at the University of Michigan. And so this has been running in RAP Chem for about 2 years or almost 3 years now, since 2022. And so it works very similar to how a lot of biogenic emissions work. You provide the model with a potential, and then those are modified online by precipitation, wind speed, and sunlight. The primary mechanism that we're using in both RAPChem and MPAS is 3 different intact pollen types, so tree, grasses, and weeds. And then those can rupture and go into a single ruptured SPP, or a subpollen particle. And so these are really small particles that have been implemented or implicated in thunderstorm asthma, for example. We do have more granular emissions available for some intensive retrospectives, but we've just not added those tracers to the model yet. We have updated the land cover data sets, really expanding that geographic coverage. In the RAPChem, we really didn't have any emissions over Canada. And so, for example, the last couple of weeks here when we had the Canadian trees blowing up with some pollen, we would have missed that last year. We do have a real-time verification system, not just for MPAS aerosols, but for many of the models that we have running, as well as other models out there. For example, the UFS AQM here is being compared to the RAPChem and MPAS aerosols. As I mentioned, we have some work to do. MPAS is wildly over-predicting both PM2.5 and PM10. Not quite sure what that is yet, but we're excited to have some work to do, I guess. Similarly to the PM2.5 and PM10 from the anthropogenic species, we're also over predicting pollen, at least compared to RAPChem. They're using the exact same emissions, and so something is different between the two. We have been able to compare with some measurements by a company known as Pollen Sense. They've got a bunch of these little low-cost sensors around the country, and they provide us with this nice little interpolated map to be able to compare with, because there are very, very few pollen observations out there. So I'm excited to have this to compare with. So kind of just to give you an overview of what we've done here, we've created that separate registry to include all these new tracers, namely smoke from wildfires, as well as smoke from residential wood combustion. We do have the dust packages coupled as well. However, we're finding some issues with the threshold velocities and are not just turning it on yet. Pollen, as I mentioned, we have that tree, grass, and weed, as well as the subpollen particles. The sea salt routine has also been coupled, but we've not turned that on yet. Anthropogenic, I think I talked about that quite a bit. In terms of the physics, Clark mentioned it a little bit, but we do have plume rise, MYNN, EDNF, mixing of the chemical species, dry deposition, wet deposition, pretty much everything that you would need to perform a true simulation. Kind of moving forward, we have this current RFSD configuration that includes smoke and dust. This is kind of what we're running right now in the MPAS aerosols. But at a certain point, there's other experimental tracers that could be added. For example, there's a poster tomorrow talking about lake spray aerosols that I encourage you to check out. In that NOAA has a harmful algal bloom forecast, and it's something we could easily couple to this model. And so I think it's a really interesting kind of interplay between that. So I'll leave up some of these questions that I would love to talk with you now or in person later on. So thank you. And yeah.
Thank you, Jordan. Questions?
Excellent talk. Is it actually, it's really nice to see this bioaerosol work take off, in my opinion. For one, there's going to be probably some model intercomparisons starting off with bioaerosol capabilities. I assume you would be interested in taking part of that too.
Absolutely.
Yeah. I'll leave it at that. I have another question, but we can talk about it later.
Nice talk, Jordan. And questions. The first one is about this residential wood combustion, which could be quite important in northeastern US. So I wonder how well the current emission inventory represents emission from this sector. You mentioned NEMO at 1 kilometer, especially at this neighborhood scale. How confident are we?
That is not a question for me, honestly. That would be a question for Daniel Tong, I think. I'm putting it together at this point. It's not even something I've tested yet at all. You're right. At 1 kilometer, you're missing if that block doesn't have chimneys and the block over does type of thing. It's, you could be very, very different results. So I really don't know how well those are done. I mean, the spatial surrogates at some point are going to be wrong in places. I mean, is that uncertainty worse than the temperature dependency though? Some people don't burn wood when it's 50 Fahrenheit, some do type of thing. So I don't know where the uncertainty lies, I guess, between the two.
Thank you. Maybe we can talk to Daniel Tong regarding
Yeah, would love to.
Yeah. And the second question is about bioaerosol and in particular the pollen capability here. I wonder how likely can it be extended to simulate emissions from bioscience lab, which turned out quite important, especially after COVID.
Yeah, I mean, at a certain point, it just comes down to just describing the emissions. It's very simple to add a new tracer. I mean, we have to parameterize its dry deposition and wet deposition, but that's really about it. As long as I know the size of it, we can add it. And we have the computation to keep adding tracers, I guess, but yeah.
Thank you.
Oh yes, we do have mineral dust emission and transport. It's technically implemented. It's not running right now. Like I said, it's the Function emission scheme that's running in RFS. One of the threshold velocities is just not getting it's just not getting turned on essentially, and so we're not emitting dust yet. And so I just haven't looked into the details of it and what's going on. Got a couple of different modules to look at in the meantime.
Can you do pollen globally?
Yes, actually, Yingjiao Zhang is implementing pollen into the CSM. It's a little different though, because you have to use the MODIS land use types, and that gets confusing because of how the tropical needle leaf or tropical evergreen are different than the boreal evergreen. And so you can, but there needs to be, I think, some development in terms of the emissions of those, because they're not separated really in MODIS in the same way they need to be for the emissions.
Thanks again, Jordan. Okay, one more talk here from GSL. This is going to be on test and evaluation of MPAS JEDI for implementing in RFS version 2 from our Ming-Hu.
Hey, thank you, Chris. And it's clear what I'm going to talk about. And good afternoon, everyone. Yeah, let's go back to the DA and how I should move these slides. And okay, so we have a big group, actually data simulation group here in GSL, but we actually team up with EMC regional DA group. And also we work very closely with NCAR, MQ, GSSDA, and our sister labs like PSL and NSSL. So we are a big family, and I'm going to report results, the test evaluation results from GSL today. So focus on our results. And so we know what RFS is. So you heard about this section, and it's actually regional convection allowing deterministic and ensemble operation forecast system. I read through this, and the focus is its operation. So it has to target a lot of hazard weathers that has a long list. And also we have many downstream users. So that's why actually this system, if it the target of RFS is replace all operational regional operation system. So it has to technically meet all the requirements that current regional operation, many regional operation system provide. So at least very few, like domain and resolution, we run in 3 kilometer grid and covering North American domain. And we need to provide hourly forecast up to 18 hours, and every 6 hours at 6, 06, 12, 18Z, we need to provide 84-hour forecast. And we also need to provide ensemble forecast and to replace current regional ensemble forecast system. We have a Roofs version 1 under evaluation, which is built upon FV3 LAM system plus GSI. And right now we are working on Roofs version 2, which will build upon MPAS and JEDI. You already hear lots of good news about MPAS. Now let me share some good news with the JEDI. And first, actually, I want to show this diagram. It shows the Roofs version 1 data simulation, cycling, and strategy. We have a lot of highlights here, actually, but in this talk, I'm going to focus on the part of item 6, which is enhanced and tuned GSI and INCAF. I'm going to talk about enhanced and tuned MPAS. MPAS GSI for coupled with MPAS model. That's the scope of this talk. Talk about JEDI. So what we want from JEDI is MPAS JEDI, and we want to run MPAS JEDI with deterministic analysis, which is the 3D VAR, 3D INVAR, and hybrid 3D INVAR. And hybrid 3D INVAR is our target analysis method for deterministic forecast, for deterministic analysis. We also want ensemble analysis, which is LETKF and LGETKF, and we are testing that. So we are using a lot of observations. So we have a long list of observations we want to test and evaluate. At least part of the observations here, I ran out of space, so I just end up there. And bottom line is, we want to use all observations that are available for us that benefit for our operation forecast, operation data simulation system. So with that, actually, we built up 3 real-time testing system, which is MPAS Dive 3, Dive 4, and the corners 12 kilometer domain. We are now using MPAS Dive 3 real-time to test model cycling interface. I'm going to explain that a little bit. It's running over corners 3 kilometer domain. And our Dive 4 is also running corners 3 kilometer domain, and we are right now testing 3D INVAR analysis with global ensemble forecast. So we are not running ensemble forecast for this version, but we do use the global ensemble forecast to run 3D INVAR. And we are running aircraft observations with this Dive 4. So we have this corners 12 kilometer. You will see why we have this one. It's cover the corners 12 kilometer domain. And we are running 3D EMR system. This time we're using Roofs ensemble forecast. Because we have to run 30-member ensemble forecast, 30-member ensemble forecast, so it costs a lot. So we are not be able to using corners 3 kilometer domain to do this kind of test so far. Now, actually, this test we're still using aircraft data, but we certainly we just added the meter stations into this one. We also set up retrospective experiment. It's cover the period from May 6 to 13, 2024. And right now, actually, most of our retrospective experiment are conducted based on our code base baseline version 2.00. And I want to say, actually, our current test strategy is very simplified cycling system. We are doing regional hourly cycling, and so we have to test the MPAS JEDI over the hourly cycling with regional. So we cold start our model forecast at 0 and 12Z. We do 12-hour forecast. Then we hourly cycling our system from 1Z to 11Z and from 13Z to 23Z actually. So there are 11 data simulation cycles. And after this 11 data simulation cycle, if we compare 1 hour forecast against the 12-hour forecast, which is from 0 and 12Z cold start, that means actually we can compare actually to check what's the analysis does, what's the impact of data after 11 data simulation cycles. So you will see lots of comparison between 12-hour and 1 hour. Here is the first example is this left figure. You can see this red line is 1 hour forecast and the blue line is 12-hour forecast. That's just, I said actually 12 forecast is cold start from 0Z and 12Z. 1 hour forecast is from 11Z and 23Z, which is 11 cycle after the 11 cycle. The dive 3, we did not add any DA there. So it's just cycling without DA. So we stop model 1 hour forecast, restart with 1 hour forecast. But after these 11 cycles, we got almost identical results, right? So that means we can keep cycling model without changing the results simply because of the restart model. But our target is actually after we're adding data simulation, the forecast is improved. That's the right figure shows. There's lots of lines. The dashed line is background. It's 12 forecast without any DA, but all solid line is a certain kind of data simulation impact. So we have blue line to show our 3D ENR analysis with the aircraft data. It's improved, right, compared with the dashed blue line. And the red line improved further, right? This is 3D VAR with the aircraft data. And the blue line is best. It's a hybrid 3D ENR with aircraft data. Those results are from Ruth Verman. That means it's the GSI analysis with all this data. And we want to repeat the similar, we want to achieve the similar positive impact with the MPAS JEDI. So first test we did is MPAS JEDI 3D ENR analysis with aircraft observations. And the figure I show is up air MPAS and bias profile for MPAS. We are our real-time dive 4 real-time forecast. It's 1 month from May 2 to June 1st this year. And we can see actually the up row actually shows the verification against the sounding. And the bottom row shows the verification against AMDA or aircraft observations. So I will explain why we do these two observations at the same time. And again, when you see the red line, which is 1 hour forecast, that means actually the DA has the impact with this forecast. And the blue line is without DA impact. So the solid line shows RMSE and the dashed line shows bias. There are lots of details you can check, but at least when you check the left column, which is temperature, you can see there's a consistent improvement from the DA, which means the red line is better than the blue line, right? And the wind shows the same story. There's a consistent improvement from bottom to top, actually, because of the data simulation. And there's mixed results in the middle RH. When you check the up panel, you can see there is a slightly negative impact from the DA. But if you check the low panel, middle, actually, there actually slightly positive impact from DA. This caused because of the sounding observation itself has the dry bias, which I think the Clark explained that much more clear than me. So we, at this moment, we trust the DA like verification against aircraft data more than the sounding data when we talk about the moisture verification. But temperature and wind give us the consistent results, either observation, if you're against either observations. So we got pretty good results, positive impact from the aircraft data with the 3D ENR. And we do have another system running like corners 12 kilometer, right? So we have run our own ensemble forecast, our roof ensemble forecast. We do same 3D analysis with the same aircraft data, but those two tests has running on different grid. One is on 12 kilometer grid, one is on 3 kilometer grid. There's always question, is 12 kilometer grid good enough for this kind of a test? Because we are actually working on convection scale, but at least for the conventional data, I think 12 kilometer is good enough. This just shows the same verification for 1 month between depth 4 and the corners 12 kilometer domain. And there's a lot of details, but so the same red line is DA impact and blue line is without DA. But the difference is actually the solid line shows depth 4, which is corners 3 kilometer domain. Dashed line is corners 12 kilometer domain, it's 12 kilometer. So we don't need to pay attention to details, but at least you can see the dashed line and the red line are very close to each other. That means actually we got the similar results, scientific results, and over the 3 kilometer domain and over the 12 kilometer domain. So that's so because we ran most of our ratios over corners 12 kilometer domain, we need this kind of confirm that 12 kilometer grid still give us good enough scientific results. And here is another story about our hourly cycling, because we do our cycling because we have hourly observations, and we do hourly because the near forecast is better than the longer forecast, which is shows in this figure. The blue line still is 12-hour forecast, cold start without any D impact. Then the red line shows 1-hour forecast, and the orange line shows 2-hour forecast, and the green line shows 3-hour forecast. The short forecast is better, right? The red line better than orange line better than green line. That's actually why we do hourly, because we always integrate or use the grid latest data to improve the short-term forecast. So our forecast always gets the best forecast, short-term forecast. That's the experiment from our MPAS GNI 3D analysis with aircraft observations. All these results is matching to our background experience and knowledge from RAP, HER, and ROOFs version 1. So here is we talk about 3D environment. Now I'm going to talk about 3D analysis with aircraft observations. So this top row actually shows the similar verification results, which is up air like RMS and bias profile for the 3D VAR. This is from retrospective experiment. And we can see actually the red line 1-hour forecast and the 12-hour forecast is blue line. So what we are looking for is the red line is better than blue line. We can draw this conclusion from temperature and wind. And RH is mixed. So it's clear that 3D VAR does not give us clear-cut improvement when we compare with 3D VAR. But the history is actually, we spend a lot of efforts to get there, actually. So how we get, the key is the static BE. The key is the static BE. So our colleagues spend a lot of time to generate this static BE from 1 year GFS forecast using NMC method. And then she tuned this BE based on the GSI static BE. So finally, actually, we got at least a positive impact from this static BE so far. It's not good enough, because if you compare with the two low panel, which is temperature and wind, same forecast, I only show the RMS E profiler. Both are 3D VAR, and one from GSI, one from GNI. So dashed line from GSI and the solid line from GNI. So if you carefully compare with red dashed line, you can see red dashed line is much better than solid dashed line. And red dash in terms of wind, red dashed line is consistent better than solid red line, red dashed line, solid dashed line. That means GSI has much better static BE. So we still need to either tune our static BE based on the bumper method, or we can directly using static BE from GSI to improve our 3D VAR. And so it's lots of efforts to tune static BE, and we already happy with current status. So we go ahead to run this hybrid 3D VAR analysis with the current static BE. It's not optimal, but it's good enough to do this kind of test. So there's a lot of figures. Still, blue line shows the background without DA, and all the green line and the orange line and the red line shows different kind of DA analysis method, like red line 3D VAR and orange line hybrid and green line 3D VAR. The story is here that orange line is the best actually among these three analysis methods. That's why we spend so many time to do 3D VAR analysis, 3D VAR analysis, and the fundamental of the target is actually running the hybrid analysis, so we can get best analysis results. Okay, so we started to doing MPAS observations, test evaluation recently, and here is our very preliminary results. We start adding the MPAS stations to our real-time dive corners 12 kilometer system after May 15th. And this is a time series, RMS and bias. RMS is solid line, bias is a dash line, and still the red is 1 hour forecast and blue is 12 forecast. We basically, we expect red line is better than blue line, right? And if you compare the status before the May 15th and after May 15th, we can see the MPAS station does give us a slightly positive impact to the surface forecast, to the surface. But this is out box. We use the whatever we have inside the JEDI, and we have a long list of what we should do to improve the surface data assimilation based on our experience from Raptor and Roofs version 1. So quick summary, and MPAS JEDI system was tuned and tested for our Roofs version 2 application. And we have MPAS JEDI 3D VAR analysis with aircraft observations, and we can see consistent, significant positive impact for temperature, wind, and even slightly positive impact for the moisture. And 3D VAR analysis with aircraft observations also actually shows the slightly positive impact, and for the temperature and the wind. And we start to test the MPAS stations, and the first test does show a slight positive impact to our surface, near surface temperature, moisture, and wind field. There's a lot of things to do, either tuning, develop, test, evaluation. So like how to get better static BE, how to improve the ensemble forecast to get better 3D VAR analysis, and there's also surface DA cloud, and I can go on a long list, but we got a pretty good start, and we'll keep working on all these techniques. Hope we can get the Roofs version 2 ready as soon as possible.
Thank you, Ming.
Thank you.
I think for the sake of time, we're going to move on to our last presenter. So thanks again, Ming. So our DTC colleagues are going to give us an update on stochastic physics and MPAS and transition into the UFS with Will Mayfield.
Thank you, Curtis. Hello, I'm Will, and today I'm going to give kind of an update on our implementation of stochastic physics for MPAS, and that being kind of a step towards transitioning it into the UFS. This is a developmental testbed center project that was co-led by myself and Jeff Beck, and conducted by our team from NCAR and NOAA Labs. So to give a little bit of background to this effort, I think it goes back till about something like 2015, I think is when stochastic physics went into the HER. So at that point it was implemented for the work model, and then I've listed here some other more recent projects that had to do with getting stochastic physics into the FV3, leading up to our current effort where we're trying to put it into MPAS. We've had a lot of contributions and fruitful collaborations over those years that we've continued to have. So the main goal of this, or I guess the main idea is like that the Rapid Refresh Forecast System version 2 is planned to be based on MPAS, and the convection allowing ensemble component of that requires some kind of model uncertainty representation. So that's usually done through initial condition perturbations or DA-based methods, and then through things like stochastic physics, which can put in perturbations throughout the model integration. And through some of those past efforts, we've found that the behavior of the models under stochastic physics perturbations can be somewhat dichord dependent, both on our experiences with WRF and FV3 or through what we've seen in international models that have implemented stochastic physics. And so we've so far been working on the implementation, but we also think it necessitates some testing and evaluation to try to figure out what is the proper kind of, how do we configure this thing once it's put in. So the implementation then is part of the steps to facilitate including the MPAS into the UFS, which is a major goal. And with that, it would provide the community with some uncertainty representation mechanisms. And here on the right is just like some of our past efforts looking at various stochastic physics schemes and their effect on things like convective events, or looking at it in like combinations of them and different configurations of them for in like kinetic energy spectra. So what we've so far done is, or what we started with, was just compiling the MPAS code while including the UFS stochastic physics libraries, which we've now done on both some NCAR and NOAA systems. What this allowed us to do was to make calls to the stochastic physics library to initialize and then advance the pattern as the model integrates, and ultimately to apply it within stochastic physics schemes. This image to the right is what the pattern might typically look like for a global simulation. And then the kind of, it's this random pattern with a certain level of smoothness and other properties. And we implemented a number of nameless options to be able to configure that. So things like the magnitude, which you can create multiple patterns and have them be combined arithmetically. And then things like a pattern update interval, because we found in previous models that updating at every time step can be a little too computationally costly. So that was a successful mitigation of that in the past. And then the spatial and temporal decorrelations of the pattern, and things like tapering and a logistic transform for the SPBT. So we implemented all of these options, and then we've been checking to see that they're working as expected. So far, so good. Some of this we've done by comparing to how they behaved in FV3, not necessarily saying anything about like what came out of the model, but more like, was the pattern, did it look the same? Did it kind of go into the schemes the same? So on the right, just saying, we looked at a correlation coefficient of the pattern at time 0 and then later, and saw that it decayed similarly between the models, and looked at a lot of other things to say, we do think that the pattern is there, that it's working as expected. And so then we decide that we think it's ready to put into as perturbations. The schemes that we're doing that for are the physics tendency stochastic perturbations, so SPPT, and then we're still kind of working on the SCEB and SHUM schemes. Here on the right is an idea of what it looks like to have the pattern evolve over model integration. I think this is for hours 3, 6, and 12. And then on the right is the 500 millibar temperature, just we turned on SPPT and we looked at differences turning it on and off, and from this we concluded, yes, as we integrate it, the perturbation is going into the physics tendencies, and then we're seeing a difference come out. And if you look closely, maybe you can like say, okay, the pattern looks to be showing up, and I don't know how the quality of this perturbation yet, but it is a perturbation, and it's being put in the place that we intended it to, is our conclusion. So we want to look a little more deeply into that. We're looking at kinetic energy spectra to get an idea of kind of the profile along wavelengths, especially early in a forecast like that these perturbations are producing. And then I'll go to the next slide, which has some of those types of plots and difference plots to show that the only thing we've really noticed so far in both a global and a regional test case is that it seems like for SPPT at least, the perturbations are having an impact that's a little weaker in MPAS than FE3. Again, not saying that's good or bad, just that it's seems to confirm our idea that this might be a little dichord dependent on how it comes through. We can only really speculate on why that is. Maybe it has to do with the effective resolution or something, or maybe some dichord experts can tell us if they have any ideas. And so from here, we're going to move on to doing some full-scale ensemble tests, where we're going to look at enough data to get some statistically significant results for a variety of ensemble metrics, and then try to say, you know, we'll test a variety of configurations, combinations of schemes, and get an idea of what's kind of working and what's not when it comes to trying to produce an ensemble using stochastic physics that can provide a good amount of skill. And the end goal of that being that we want to have like some recommendations for configurations coming out of this. So I'll summarize with kind of going over some of our impacts here. We've hooked up the pattern generator, and we're hooking up some of these so-called ad hoc schemes. And then, and with this being kind of one step towards being able to facilitate MPAS going into the UFS, which I know we're going to have a discussion session about soon after this. And then we want to get a general understanding of MPAS and how it behaves under these kind of perturbations. And and then once we've got this kind of working and everything, we'll have the ability to put it into relevant repositories. So the UFS stochastic physics one, and then we'll be listening closely in discussions of what MPAS model repositories we'll be able to, or how we'll be able to get these contributions made. And then we have some ongoing collaborations. At NCAR, that Judith Berner and Ihan Chen are working on the SPP implementation. We'll be able to connect the pattern generator that we've got running with MPAS with them. And then I know that there's some parallel work at GSL working on it, SPP. And then we're hoping to do some work on more in-depth testing and evaluation with the stochastic, like the parameterization perturbations at some point. So that's all I have. Thank you for your attention.
Thank you, Will. Any questions for Will? I've got one for you. Are we going to have the ability to throttle how often we apply the stochastic perturbations during the model advancement? It's some nameless control thing.
Yeah, that's the like interval of the update of the pattern, because that's the part that seems to be costly, is advancing that autoregressive process. Every time step seems to be a little too much.
Exactly. Any other questions? Nope. All right, thank you again, Will. And let me extend my appreciation to all the presenters of this session. Thank you all.
Well, here we are, the last session of the afternoon, just us between now and beer. So, and thank you for getting through all this day. It's been a long day. It's been a really, a lot of really great presentations. And as you saw in this last session, there's a lot of work going on in MPAS development over in NOAA. Our colleagues, both here across town, down in Norman. Lou's been sending me storm pictures, live storm pictures from down there. So they've got interesting weather going on. And also some work at EMC that you didn't hear about. And you're going to hear other talks and see posters describing this more. Now, we're kind of at an interesting point here in that we've had the experience of having WRF move into this HER configuration and be used there. And that was done by taking the community release of WRF and doing a few modifications and tunings, and boom, it went into operations. With MPAS, as you can see, the current work's going on in the community release of MPAS, in which a lot of work's been done that still has to come back to us, and we're working on that, and we'll be talking about that. But also, it's going into the UFS. The dynamical core of MPAS is going into the UFS for the operational applications. So it's a different landscape that we're facing in terms of how we develop this together, even though the various pieces are going to be used in different places. And kind of how to help potentially optimize that, or how we might deal with that, is what we think we'd like to hear today from the community, because ultimately we know that you would like to get access to these advances, and we'd like to support them to you. Of course, there's support in the community release of, for example, NOAA Physics, which is coming in directly, but there's also support of MPAS DICOR and the UFS. So it's a much different world that we're evolving into. So to start that off, I asked Curtis, who was gracious enough to co-host this with me, to send me a slide-ish or so describing what's going on, which you've heard a lot of it, and he's going to present those, and then there's a final slide with a few questions maybe to kick this off. So I'm sure you'll get through your slide-ish very quickly.
All right, thanks, Bill. And yeah, I just want to quickly sort of lay the groundwork for where we're at in NOAA with MPAS development. So I'll start with the first of sort of two tracks here, and the fact that we have tracks is certainly food for discussion. And this is with the standalone MPAS development that's taken place in NOAA over the last really 3 years. This started with NSSL spearheading some testing of MPAS 3-kilometer CONUS configurations. Those largely were derived from RAP, or should say RFS, or HER initial conditions, and similarly drew from these physics suites, or circa that time frame, sort of pre-2020. And they also had one physics variant, the NSSL microphysics, in one of those MPAS configurations. Those were tested in the hazardous weather test bed spring experiments over several seasons, certainly informed the direction for NOAA in terms of moving toward MPAS for RFS. That led to the white paper that came out about 18 months ago. And then they've obviously more recently been focusing in on war on forecast development with MPAS. GSL's also obviously become very invested in the MPAS development. And over the last 2 years, a lot of this work has taken place first in the GSL repositories, but then obviously made available in the UFS fork of MPAS. And we're going to talk more about that, I'm sure, coming up. But, you know, as was highlighted in the talks in this last session, there was a lot of development going on by GSL testing the physics, the data assimilation, even different MPAS releases from NCAR, and putting those all together with things like the RFS initial conditions, which seem to be quite skillful at this point, and bringing those together for testbed evaluations, which we're also seeing some of the fruits of that labor now with Clark's and I think Adam's presentation tomorrow. And then bringing the physics into the UFS community MPAS fork, as well as the gravity wave drag parameterizations into the NCAR MPAS repository. The other thing was I highlighted the DA cycling with 3D and bar, should be bar, not burr. And then we tested some resolution sensitivities for forecast performance with a varying, 3 to 3.5 kilometer mesh spacing, as well as some of these other grid configurations that were highlighted earlier today, with either fixed global or variable meshes, as well as looking down at even finer scale mesh for fire weather applications. So all this has been going on largely with the standalone MPAS configuration. So the other track that I think is germane to the discussion is the use of MPAS in the UFS, the Unified Forecast System, which NOAA is shepherding along to sort of incentivize community contributions that will hopefully help realize improvements in operational modeling systems. And several steps there have already been established for this integration of MPAS as an option in UFS. Generalization of the atmospheric component to UFS atmosphere, or ATM. And there's several other underlying steps that have taken place, including the forking of the MPAS model code for the UFS community space in GitHub, getting the CMake building capability going for MPAS, get a stub for the atmospheric driver, and this will help obviously with the interface to the CCPP compliant physics, ESMF grid component, it can be called, in the UFS ATM, and the NOAA cap that will help facilitate running that grid component. And then on the physics side, generalization of the physics, refactoring so that we get the tendencies and not just direct updates to the model state, along with the stochastic physics pattern generation within the use of the MPAS grid. Obviously, we had a bit of update on the stochastic physics work here in this talk from DTC and Will. But there's a lot that needs to be done to get this into integration to the UFS to fully realize that vision. So there's a long list of to-do items that still exist here. This is going to include more testing of the parameterizations with the tendencies to finalize that. There's a lot of code conversions of different vertical coordinate systems, the array direction indexing. Again, this is the flexibility we would need to have a more generalized driver in the UFS. Variables associated with the lateral boundary conditions are needed for the limited area applications. On the physics side, transition the stochastic physics code from the standalone into the UFS infrastructure. That includes some of these other ad hoc schemes, as well as, again, keeping the CCPP-based physical parameterizations, keeping those updated. And there's obviously more than one repository where these potentially reside that we need to keep those synced. And then there's pre-processing and post-processing questions about which utilities we need to bring into the UFS infrastructure or into UFS utils specifically, things like RAVE for processing of satellite data information, for smoke, fire weather prediction, the grid generation tools, of which many were discussed here today for MPAS, and then on the IO backend side, how we want to handle that, with which utilities convert MPAS it, what type of write component capabilities are going to be needed for interpolation, asynchronous IO, et cetera, as well as the post-processing, whether that's inline or standalone. So I think both tracks have questions about ongoing support for MPAS. These questions can stem from, on the personnel side, having sustaining long-term sufficient expertise in the DICOR and capacity for NOAA and non-NOAA development and maintenance. Obviously, code management. We're talking about, again, an ecosystem of repositories here on how we would handle that with the MPAS DICOR, including other hosts in the UFS. The development obviously needs for facilitation of future operational implementations, which is really the, many ways an target goal for UFS is to realize these innovations, these modeling system capabilities in an operational environment within the National Weather Service, among other stakeholders. And then lastly, I will mention MPAS optimization. I think there's a desire to obviously focus in on computational resources needed to run MPAS, its performance relative to other modeling systems and other components, data assimilation, et cetera. And that often comes later after you get the fundamental capabilities established for any software system, is to make it run efficiently and quickly. So I'll stop there and turn it back over if you want to prompt some questions. Yeah.
Read it. You can read my one slide. We want to open this up to comments and questions. And my understanding is that people in the virtual world can actually speak to us. And should we have them like raise their hands or something? Or okay, so those of you out there that aren't here, you can raise your hands. So floor's open.
Okay, I got it. So I have a question, Curtis. When do you think, I'm guessing from your summary that MPAS will be available within UFS through making available as a NOAA component? What's the timing or you have any clue of that?
So the question is the timing of MPAS integration in the UFS through a NOAA approach, which isn't the only way to do it, but that's one we've laid out here. Obviously, questions on terms of timing, it's a function of resourcing and funding, and we don't have all of that in place at this point, although there's quite a few possibilities for support to keep the momentum going and work through that list. If I had to take a hand-wavy estimate at how long it would take to realize that capability, that full integration, I might say a year, but that's there are certainly error bars on that.
All right, thank you.
And I'll ask others here that want to chime in or respond to some of these questions, feel free to speak up and get in line on this. So I think Leisha's probably going to have a response.
Your response was good. I was going to say something else. So you rattled like a very long list of things that we need to do to get the MPAS working in the UFS. I got even tired, like just, oh my God, we have a lot of work. But we need to recognize that a lot of this work is also necessary if we're going to use the standalone MPAS, right? So for example, things like pre-processing tools to interpolate whatever data to the MPAS native grid, it doesn't matter, standalone or MPAS in the UFS, we need to do that. So I think it's good in the discussion, like to deconvolve those two things, like what do we need that's really for the UFS or what we need for the standalone. And then I think code development that we need for both options, we need to abstract out of these modeling systems, so as much as we can modularize things so that they can be used for MPAS at the UFS, but also serve the broader community who might be using MPAS standalone. We should be doing that. One more thing is, I think in the area of physics, that's especially where we want to do that. So the more we can abstract our physics schemes into their own, like modular, say, code repositories or infrastructure, the easier it will be to serve this physics, both to standalone and MPAS in the UFS. So I think there's some software architecture questions and decisions that we should be making at the onset of this to make it more impactful for any use of the MPAS.
No, I agree with just about everything you said, if I understand it. And as you appreciate, the gravity of drag scheme that just came in, that's providing the template to get these other schemes in. And we want to move quickly on that because we realize that we haven't moved that quickly on the NCAR side, and we need to move more quickly. So we are certainly going to put some effort to do that. And I think this is going to be a big gain for us because the physics developers largely lie outside of NCAR, mostly in NOAA. So agreed.
Real quick, there's been someone online with their hand raised for a bit, so I'm going to unmute him. It's Cliff.
Yeah, hi.
Why am I not surprised? Okay.
Okay. Can you hear me?
Yes.
Okay. Well, my central question is the big question, and that is when is NOAA going to take on MPAS for the global model? I mean, they made the decision at convection allowing scales. I mean, the future global modeling will be at that resolution. So has the decision been made to go to MPAS to replace FV3? And if it hasn't been, when is that decision going to be made and who's going to make it? I mean, this is very important. What's the answer?
Well, I can give you some information. I don't think I can give you the answer you're probably looking for. I don't know if we even have EMC representation online. So I'm gonna a couple things in terms of the adoption of MPAS globally. One, obviously we are underway with some testing and evaluation of MPAS at that scale. I think that's going to help inform where we're at with respect to MPAS compared to the current GFS, GEFS configurations. So I think there's a lot of momentum right now to look at it for that application. There's definitely needs coupling wise to get in place to really reproduce the desired capabilities for the global solution. So coupled modeling is a very big deal for that scale. So we need to make headway on that front with MPAS. So there's certainly some work to do, legwork to do on that front. But in terms of sort of checking the box that, okay, I think that's the direction that NOAA is going operationally for the global prediction system. Again, I think in the end, that decision ultimately lies with EMC. But I think we can inform that decision with a lot of the testing and development that we're doing right now. So I can't give you a definitive answer on that. I said I'd like to have our weather service counterparts help speak for what that might look like in terms of a timetable, but I don't know if we have their representation, and that's again an unfortunate aspect of us having to be mostly remote for this proceeding this year.
Guess to build a little bit off of what you just shared, Curtis, for the community's benefit, EMC is at least MPAS curious. They are running some experiments with global configurations of MPAS out to 2 weeks lead time. There is interest if there is support in considering physics implementations similar to what you see in the operational GFS within MPAS in some form. And so I think right now, EMC sits very low in the funnel in terms of close to operations. I think it's incumbent upon us who are higher up in the funnel, research, universities, NCAR, down to a place like GSL or NSSL, to continue to demonstrate the viability. We have the opportunity to inform, as Curtis mentioned, potential operational implementations through the work that we are all collectively and individually doing with MPAS. So I view this as a very exciting time and a very exciting opportunity to continue to deepen our working relationships and just build next generation forecast systems that, as we say in GSL, deliver solutions defined very, very broadly. But I wanted to speak a little bit about the physics, this question you have about NCAR support for community use of NOAA physics. And I think it's pretty straightforward following from the discussions that we've had at GSL with you all, Bill and Michael at NCAR. When we're looking at NCAR supported physics used kind of as a suite, that a lot of our physics work is developed such that the physics work best together with each other. MYNN EDMF works best with tempo. A lot of our extended physics developments are going to further or deepen those connections. I think it becomes a little thornier in this idea of mixing and matching physics that's been common in the WRF era. Less so in the MPAS era, just because there's not as much in the way of physics available, but is still an approach that is used in operations to generate ensemble diversity and ensemble spread. So I'm not sure what the right answer to that is, but I think that's perhaps one area that requires some further consideration of what does the suiting look like for MPAS, and what does the communication look like in terms of what physics should people be using amongst the various ones that are available there. And I think NOAA physics in the UFS probably looks very similar to what it does now. And I think that's mostly a NOAA and NOAA affiliates issue, especially through CCPP. So I'll stop there in case you all want to add anything or say, no, that's not right. I see it differently. Just intended not to be prescriptive, but hopefully ignite that discussion.
No, it was by design. We didn't bring in too many physics into MPAS. And I agree with focusing on suites. Absolutely.
So I'm going to ask a question about something I don't see on this slide, which is the CCPP. So one of the things that I associate with NOAA physics is the CCPP physics package. And right now, CCPP is part of the UFS. It's not part of MPAS. We're coming up with a solution of moving things to submodules so we can kind of bridge the gap. What would really ultimately bridge the gap and make this development a lot easier is if the CCPP was part of MPAS. And that would allow this development to be a lot easier. And I know there's no plans to do this, but I'm just kind of curious if there's any wind behind the sails to potentially do this someday so that we could have a way to run NOAA physics in standalone and NOAA physics in line with MPAS.
So our thinking on this is that if NOAA were to implement this and contribute it back, we'd look at it closely. There.
To make one comment at least, going back a little bit towards Cliff's question too, I mean, one thing that is really going to be important too, with respect to implementing into the UFS, we have to make sure we can even run this thing with the same stuff that EMC can run it with. Aerosols is one thing, looks like that's pretty close, at least from Laura's talk, also from Jordan's talk. Ocean, what's going on with respect to ocean work? And I don't know, that's a question maybe for Ligia too, if this goes into UFS, does it mean it automatically then will work with the ocean model there?
Automatically is a big word, right? But there is infrastructure there to connect. So the Earth system models components in the UFS all are ESMF components that have a NOAA cap. So we would need to develop a NOAA cap for the MPAS-based UFS atmosphere. With the work that Curtis mentioned that has already been completed, there is pretty much initial structure there. And there is already 90% secured funding to continue the development of the NOAA cap for the MPAS atmosphere in the UFS. So I think it's a matter of doing this development and we can get there. I know that there have been over the years concerns about SMF coupling infrastructure between atmosphere and ocean for high resolution simulations and whether we can do that in a way that's computationally efficient. And I don't know the answer to that for very high resolution couples.
Yeah, that means even more so, going back to Cliff's question, that if EMC ever is thinking about changing the model in the next 10 years, they should start thinking about that now.
So I'd like to say a few words about coupling to an ocean. Our preferred solution 7 or 8 years ago was to avail ourselves of that within the community Earth system model, CESM. You saw some results from CESM today, and that's the result of almost 8 years of work. And you saw a lot of the good things or things that have been advanced. You didn't see so much of how many things still don't work and the scaling issues that are still out there. A lot of the UFS infrastructure is shared with CESM. So there's still for us questions of whether it will scale to high resolution, let's say high resolution atmosphere, 3 kilometer global, in addition to eddy resolving ocean, which is in that same ballpark. So right now, I don't think, for example, MPAS and CESM is going to satisfy our needs. It's actually pretty clear it won't, at least anywhere in the near term, if ever. Will the UFS provide that capability, coupling to an ocean at scale, given it uses a lot of the same infrastructure as CESM? And I think these are the kinds of questions we'd like to see answers to, or at least be explored further. Because I will say the UFS is a different implementation, maybe a cleaner one because it's a more recent one, whereas CESM was developed, so geez, that infrastructure goes back 25 years almost. So now there's a lot of unknowns as to how to get to these coupled model configurations at the scales we like to run them for weather prediction. But perhaps the UFS will allow that, but we get everything that's in the UFS. So we need to see exploration of that space. And there's some that's already been done, I know. So maybe it might work, but I think we need to see that demonstrated so that we could say that, yes, this can provide for the community needs in that area.
I have a question also following Curtis's presentation, where he mentions this need for optimization of the MPAS performance. So my question is about the GPUs. I'm not an expert, but I have been hearing contradictory sometimes opinions about the GPUs. For example, DOE, as you know, many years ago, probably actually decided to move completely to GPUs. But then I'm hearing is that's still taking time. But all the model codes, this E3SM is now being written in C++. And this is not just, in my opinion, technical kind of details. This has huge implications for the code development, physics, etc. So, and besides that, we also know that, okay, there are tools like CUDA where you can use Fortran to run these models on GPU. But do we have like maybe NCAR has a vision on GPU? Is it the way to go, or we are still trying to figure this out?
Okay, if NCAR has a vision, a clear vision, I haven't heard it, I would say. But I think that's because we really don't know the best way to take optimal advantage of these GPUs, the best coding styles. And so all the different organizations have been doing different things. You mentioned DOE and their SCREAM model. Wow, if you're a scientist trying to work with that, I've just heard nothing but complaints. But it does go fast. So it does integrate fast. Is Michael Duda around here? Because he's the one that's been working on the GPU port to... Did he just go, oh, no, there he is. Okay, so he didn't escape. Maybe you want to say a few things about our vision?
This is for tall people. Let me adjust this. Speaking for myself, I don't have a vision. I think we're taking a very slow and cautious approach to porting the code to GPUs. As Bill showed in the presentation earlier today, we focused on the die core first because that's code that we own and we can do whatever we want to it. My experience so far and extrapolating a little bit is that right now you could ultimately get higher throughput on CPUs. So for lower MPI rank counts, the model will run faster on GPUs, but as you scale the model out, the GPUs, I think, get a little bit the occupancy gets lower, and so the overall performance doesn't quite scale out. So ultimately, if the goal is to run the model as fast as you possibly can, I think right now CPUs are your best bet. Maybe not from an energy perspective. That's a lot of rambling in a way of saying I don't think we have, some grand plan of where do we want to be. I think the landscape is evolving, and I think we have to take a pragmatic approach and do a little bit here and there and see where it takes us. Maybe these GPU things will fall out of favor, and then we won't have to think about them anymore if we're slow enough. I don't know. I'm joking about that. So I don't know. That's all I have to say. I don't know if Sam or anyone else wants to comment on their experience with GPUs and WRF.
If you're trying to yeah, I'm seeing the same thing. If you want to go as fast as possible, CPU is always gonna make sense. But if you're looking for really high efficiency and you can get away with using the minimum number of GPUs, then it can be a lot more cost efficient. So
Do the developers have to recode the code in Python?
So that is probably another interesting aspect of this is this is easier, right? So we've so far been working with OpenACC directives in part because we wanted to preserve the original Fortran code and to decorate it with some directives. If, as Bill mentioned, if you've ever looked at any of the DOE's EAM XX C++ code, they show one loop in Fortran, and then they show the loop in heavily templated C++, and the latter is almost unreadable. And that's for me as a software engineer. I can't imagine what a domain scientist would think of that code. So I think there is some benefit to the directive approach, even if it leaves a little bit of performance on the table. Our honest experience has been that OpenACC is a bit limiting. There's pretty much one compiler out there right now that deals with OpenACC well for Fortran code, and that is the NVHPC compiler. And in case we're being recorded, I'll just say that those compilers can be a challenge to work with, the NV Fortran compiler, and it does pay to continually update the compiler. So I think we see maybe ultimately the OpenACC approach as a stepping stone to moving towards OpenAP offloading. The hope is to get broader compiler support so we're not tied to a single compiler, and so that bugs in that compiler, I'm not saying there were any, but if there were, they don't hinder us and hold us back. So yeah, there is some benefit to readability of the code.
I'm going to add one comment just on the computational efficiency front. And I'm glad that we're doing these tests right now. I mean, it's an aspect of MPAS with the mesh where you get a more dense packing of the grid cells than you get with a lot of other rectangular modeling systems. And I think looking at these 3 and 3.5 kilometer cell spacings is one of the ways in which we can realize, I think, some efficiency without really compromising forecast accuracy. And so I think that needs to continue to be explored for a variety of applications, let alone what we're looking at 3 kilometers. But I think that is one of the avenues for resource savings. And I think we saw earlier today was a 40% savings going from 3 to 3.5 kilometer mesh. So one of the many, I think, aspects here that we can try to take advantage of with the MPAS design.
Well, I'd like to start by thanking both NCAR and NOAA to organize this excellent workshop. So glad to see we can still discuss science and focus science and during this critical time. So my question is regarding the resources. And the science plan looks great, fantastic. We got great talents here from NCAR, from NOAA, from community. And how can we gather resources to achieve what we envision today under the current funding situation? And if it turns out to be very limited resources, do you envision any potential merging of the two pathways here, MPAS A versus UFS?
Okay, I'm not management, so I'm going to defer to Curtis on this.
Our session ending now?
We have heard a lot of depressing news about the budget cut. It's very significant at NCAR, NOAA, and EPA, all those national laboratory.
Yeah, there's a lot of uncertainty budget wise. I think there's, we see information indicating funding cuts, but a lot of this isn't set in stone by any means at this point. But we know we're facing some challenging times here with resourcing. So in terms of consolidating development paths, I think that as I said earlier, for getting, I think, MPAS potentially in place for all the applications regionally and globally. Again, as I said before, I think coupling, we need to get to the solution for that that's efficient, but that meets the requirements for coupling across their system components, ocean, et cetera. That may be a vehicle in which there is some natural convergence of development efforts down the road. So I think, maybe with the fiscal constraints that happen sooner rather than later. But again, I hate to get too speculative there. We know there's going to be challenges coming. We don't know the specifics, I think, at this hour. But that's something to keep thinking about if we have to make some tough decisions.
Well, thank you. And also I heard about potential reorganization happening. And so at some point, it would be great to discuss those potential merging effort, coordinating across other federal agency, including EPA effort on MPAS CMAQ. Thank you.
I have a question about the post-processing. And we will regard us and pass the regional model as well. And because in our policy, we will like the GRIP2 format. So I'm curious that NOAA will have the utility to transform the MPAS NetCDF file to the GRIP utility, or it's possible to release that. Yeah, I have the question that is currently available for the MPAS of the GRIP2 format.
Well, he's running to the microphone. I could say yes in general to the answer to that, but you want to get specific in terms of utilities that we're using and can make available.
I think maybe this time I will hold it up after Michael brought it lower. So with our NOAA activities, we do have a program called MPAS that Larissa Reams developed during her time at NSSL. One of the challenges with that is that unfortunately Larissa was one of those who was lost in late February with the federal employee terminations. And so there is no specifically defined support for MPAS. That is a tool that converts the MPAS output to a regular mesh in NetCDF format that is then suitable for post-processing with UPP, the Unified Post Processor that NOAA does support. So the support for that is based at EMC. So there are tools available through NOAA to result in a post-processed GRIP2 formatted MPAS output file that anyone could download and compile, especially on NOAA RDHPCS systems, but I think also on NCAR's supercomputing resources as well. But I think as one of Curtis's slides alluded to, what that looks like in the UFS future is still uncertain. And then there's the NCAR tools like Convert MPAS that maybe won't get you GRIP2, but maybe could get you NetCDF that you could then use something like WGRIP2 to convert over to a GRIP2 formatted file, at least as a starting point, or even reading it into Python and using one of the many tools there to output into GRIP.
And if you want to pass along the information of where that is, we can always put that up on the MPAS webpage as an available utility.
Absolutely. I feel confident about what the UPP one would look like. The MPAS one, let's have some talks inside first.
Just want to make maybe a comment or two on your first question with the NOAA support for community use of the NOAA physics. I think just to be clear, there's MPAS atmosphere. We also have a UFS community fork of MPAS atmosphere, which I think is being conflated a bit with UFS that has the MPAS dicore in it. But ultimately, from the physics standpoint, our goal really is to have a submodule of our physics in each of those systems that's the same version, right? So the thing I think we haven't thought a lot about from the community use side is that as soon as people start using your physics, they want to change your physics, right? And so how do we get those changes back into the repositories to be able to propagate to these different systems? And I think we need to have a good governance system for our physics that we haven't had in the past, even back in the WRF days when you have embedded physics. People can sometimes just jam things in and the developers don't even know that it happens. So, I think that's one step we need to go forward where I think we're lagging a bit is in governance of the physics. I just wanted to mention that.
And hopefully maybe we can address that more quickly than UFS governance.
Yeah, right. Well, anything less than what, 3 years, 4 years?
Yeah, I think we are wrapping up probably because people want beer. Me too. But I just wanted to say, we've talked a lot about and resources came up, and yeah, it's a challenge right now. But I think what we're talking about here, and I'm really excited about, is we are looking at our opportunity we have right now that we kind of need to be more collaborative, but we also need to really lean into being nimble, and so we're talking about solution spaces, whether it's ocean coupling or acceleration or other things. I think we need to hold on to what we really do well, which is try out different things and learn new things, right? We don't actually know what the right solution is for some of these spaces like coupling, but let's admit we don't know and be able to be open to trying different things and listening to software engineers and also the scientists' needs in the capability space. I really think there's a thing that I'm seeing more happen in the community, but I'd love us to even do it more, is to admit when, we don't have the solution, we're not sure what the right thing is, but let's all work together. That's a thing we're really good at, or trying stuff out. So, and being able to say, you know what, that wasn't working, let's shift to a new thing. So I think there's a lot of, we agree on the vision that we want to get to, but exactly how we get there, that should be a flexible space where we learn from each other. And when I say we, I mean everybody, not just NCAR and NOAA, but the entire community that's here today. That's how we'll really succeed. So let's, commit to communication like we have today. This has been a wonderful day. Thank you everybody for being here and everybody online. And let's have 2 more days of this and keep up the great work, everyone. Thanks.
Well, with that, I think, oh wait, there's going to be a last word from the virtual world.
Yes, Lou has his hand raised.
Okay, Lou, you're holding us up for beer, so make it good.
Look, I'm sorry I missed the first part. We were dodging tornadoes here in downtown Norman. No, go forth and drink beer. I'll talk to y'all later. It really is late. I've had my hand up for a bit, but I think I'll let Gretchen have the last positive word, and I'll just say, go have a beer for me. Thanks, y'all.
Okay, thank you, Lou. I'd like to thank everyone today who spoke and contributed and everything, and hopefully we can keep this going. So let's thank everyone one last time. Do we have an announcement?
So folks, if you need directions to Rayback for the happy hour, you can scan the QR code right by the doors, both entrances, right, Neely? And the other thing is, Neely wanted us to know that there will be